Good morning, everyone. Please take your seats. We are going to start the second lecture on the mini course on cooperative games with Professor Pradeep Dubey. Before we start, let me read some information. Este evento está sendo transmitido ao vivo e gravado pelo YouTube. Ao permanecer no local, o participante declara estar ciente de acordo com a captação e utilização de sua imagem e voz na transmissão e na gravação do evento. In English now, this event is being broadcast live and recorded on YouTube. By remaining in this venue, participants acknowledge and agree to the capture and use of their image and voice in the broadcast and recording of this event. We have one novelty here. There's a microphone there. So the idea is that the mini course is going to be interactive. So if you have questions, don't hesitate to ask them. Don't wait until the end of the mini course, okay? So that said, Professor Dubey, please.
You can hear me clearly at the back? Okay. Well, first of all, if you don't ask questions, I will be very confused because either I'm being totally clear or totally unclear. And normally things are in between, so it will really help me. Please feel free to ask questions. It's very strange to be talking without you asking me questions. So I encourage you. What I want to talk about today is core and the Shapley value for cooperative games, especially in the context of what is called convex games. So these are all technical terms. The core we have encountered already in the last lecture. I'll remind you of it, the main idea of a core allocation. But the Shapley value is a new thing. And you know, when I was doing my PhD, Shapley value was the hot topic. Almost everybody I knew was working on the Shapley value. Aumann and Shapley were writing a book called Values of Non-Atomic Games, which led to several people doing PhD thesis. So anyway, and then the Shapley value became a sleeping beauty. It has been woken up by a Prince Charming, which is called machine learning, big data, and is suddenly very active again. And I want to flash applications for you. Here is recent applications of the Shapley value. I'm just going to ask you to see the headlines. Healthcare, early detection of improving heart failure prediction models. Okay. So this is healthcare. There are many things here. All this should be available to you. Cybersecurity. Yeah. Then finance and banking. Then corporate governance and management, education and policy, legal and economic analysis, manufacturing, environment, interpretable machine learning for air pollution prediction, interpretable machine learning for water quality prediction, and so on. So lots of big data. People are finding the notion of Shapley value useful. In fact, I have a younger daughter who works with Amazon in Manhattan. And she one day said to me, people are talking about the Shapley value in the meetings that she attends, and what's it all about? So I hope to give her this lecture when I go back to New York. But let me now start. So I escape. Now trying to escape. No, sorry, I'm so inept at this. I want to switch to that. How would we do it? Oh, okay. Page 1. I want to go back to. So I'd like to give you a bunch of examples of what are called cooperative games with transfers or side payments. And then, okay, so I go back. So I want to just give you a few examples just to get the ball rolling, and then we'll discuss. You've already encountered what is called the core. The idea is that people cooperate fully to make the cake as big as possible, but then the problem arises how to divide the cake. And if the division is not done thoughtfully, then the cooperation might break down, because some dissident coalition will form who will say, no, we want to break away, we can do better on our own, and the cooperation will fail. So in order to sustain cooperation and make the cake as big as possible, you have to be very thoughtful about how to divide it so that it sustains, so that the cooperation is sustained, so that no dissident coalition forms and breaks away. That's the idea of the core. And when we discussed two-sided matching or the housing market, we were thinking about the core. What we call stable allocations were basically the idea of coalitional stability. Okay. There is a completely differently conceived solution concept called the Shapley value, which you haven't heard of, but I showed you its applications. So my hope today is to define the core again, repeat its definition, and then define the Shapley value, and then discuss the connection between them. Okay. So it's good to start with some examples. I'm now describing some terminology. So players. In this example, there are 3 players, 1, 2, 3. Many coalitions, which is a subset of players, can form, and I have listed them all. 1, 2 is the coalition consisting of players 1 and 2. The order in which I write their names is not important. It's just a coalition, a subset consisting of the 2 players. Well, if there are 3 players, there are 8 coalitions. I've listed them all. One of them is a funny thing called the empty set. But it's not really there, but it's convenient to have a notation for it. Okay. Now, we think of a game as follows. For any coalition S, we want to describe how much, let's use the word money. Okay, so the coalitions can make money, and everybody loves money. Okay, and money can be transferred between people. So I'm going to think of it as games with money. So a coalition S, we want to ask how much money can S make on its own, regardless of what the people outside S do. So the idea is the players in S have decided to cooperate. They can't count on people outside the coalition who may do what they want. They want to ask how much money can we make for sure? How much can we guarantee to ourselves? That's the idea of V of S. Okay. And in the examples that I write, we'll use this notion to define the game. So to define a game, for every coalition S, we have to denote, we have to sort of say how much money they can make, which is called V of S. Here is one example. 3 players, Mr. 1 owns the tract of land where he's doing farming, and he can earn $10, $1,000 or something. Mr. 2 and 3 don't have skills, but they don't own the land. They need the land to get their skill to work. So in this example, 2 can run a motor garage if he has the land, and then the land will earn more, it will earn 20. 3 can run a motel on that land and it will earn even more, 40. So now what is V of 2? What can 2 guarantee on his own? Nothing, because he needs the land, it belongs to 1, and 1 is not part of his coalition. So I hope you see now how I have got these numbers based on this text. Any questions? So if 1, 2, and 3 get together, then the land can only be used either for farming, which earns 10, or for a motor garage, which earns 20, or for a motel, which earns 40. There's no multiple use of the land. So therefore, they should run a motel and earn 40. So do you see the way I'm defining the game, the V? All right. And the question is, well, to make the cake as big as possible, they should get together, all three, 1, 2, 3, and earn 40. The question is, how should they now divide it among the 3 players? Here's another example. There's a source of power, and 1, 2, and 3 are cities, and the power has to be supplied to the cities, and the grid for transmitting the power is denoted by those lines. Each transmission line costs something, and so these numbers in red are the costs. Now, I'm going to make the assumption that in order for a line to go through a city, you need the consent of the city. Okay? So let's look at what is V of 2, 3. 2 and 3 form a coalition. Mr. 1 is not in the coalition. Therefore, they can't use the transmission lines which go through 1. Now, what can 2 and 3 do? Well, they can build a connection between them and the source of power. And the cheapest connection is go from the source to 2, that costs 20, and from 2 to 3, that costs 5, right? There's no need to have, the cheapest efficient connection will be a tree with no cycles, which connects the coalition to the source of power, and which does not have any links going through the cities outside the coalition. So that's what they can do on their own, and that gives rise to a game. I have written minus because these are costs. Again, the question is that they will construct the most efficient tree, which is going from the source of power to the city 1, then from 1 to 2, and 1 to 3, and then 3 to 2, and that costs 20. That's the efficient outcome. How should the cost 20 be split among the 3 cities? That's the question we are asking. Okay, so the grand coalition forms, and this is the best thing they should do. However, when you want to think about how to divide this so that the grand coalition forms, you have to think of what the counterfactual of what all the other coalitions could do. You know, the grand coalition is center stage. All the other coalitions are waiting in the wings. But they are very relevant for defining how to divide the proceeds from full cooperation. Okay, so that's the question. I'll give a few more examples. This is from a course I teach to 4th year undergraduates at Yale every spring semester. So some of it maybe, I'll flash past some of them. I don't want to go too fast or too slow. Here, one more game. There are here 8 players. So the number of coalitions is 2 to the power 8, which is quite a lot. 256 coalitions can form among the 8 players, right? You see that because, you can identify a coalition with a string of zeros and ones. If a person is in, it's 1. If it's not in, it's 0. So now you ask how many strings there are. And so the first place can be filled in 2 ways, 0 or 1, the second in another 2. So 2 times 2 is the way to fill the first 2 and so on. So 2 to the power n is the number of coalitions that can form if there are n players. The number of coalitions, it can grow very fast. Now, these players are transmitting data to a destination, and the links are over here. They can transmit data only according to the links that I have described. These are the links that can be made. The square boxes with nothing in them are stations which boost the signal and pass it on to the destination. So what is the cost of a coalition? Well, you just think of the cheapest way for the people in the coalition to transmit their data to the destination. So here it's very simple. From each transmitter, this could be their streaming video data or any kind of data to the destination. For each transmitter, there's a unique path from where he is to the destination. So if a coalition forms, you have to look at the union of the paths from each of them to the destination. That defines all the links that they need to use. Of course, there are economies of scale, because if 1 and 2 and 3 are transmitting, they can all use the link which the cost 2. These are setup costs for the links, not variable costs. It doesn't matter how much data is going on it once it's set up. So is it clear how I have defined the game? Okay. A special case of this game is the airport game, on which Thompson and Littlechild, or Littlechild and Thompson, sorry, have wrote a paper about Birmingham Airport. And this is a caricature of the actual model. They have a paper in management science. The idea is this: a runway has to be built, but the users are 2 small planes, 1, 2, which need a small runway, 1 medium-sized plane, which needs a runway which costs C2, a little bigger, and 4, 5, 6 are jumbo jets. They need a big runway, which costs C3. Now, if the big runway is built, all can use it, okay? So we now ask, how should we split the cost of the total runway among the different sized users? So you see, we can again think of a game. If you think of the coalition 1, it only needs to build the small runway by himself. It's cost C1. 1 and 6, because 6 is there, will need the biggest runway, which both can use. That costs C3, and so on. Do you see how I have defined what coalitions, the costs that every coalition would incur if they had to build a runway just for their own purposes. And so we build the whole runway, and how should we divide the costs? So this was the paper, the article that they wrote. It's a special case of the transmission game I described earlier. So now on this right-hand side, I have described a very simple transmission game, okay, where the 4, 5, and 6 are data transmitters at the top, and then the connection is they go to 3, and then 1 and 2, and to the destination. The story is completely different for what is in black. It's completely different for what is in green or blue. I can't tell what it is. They are 2 different stories. However, the cost structure that emerges from those 2 contexts is the same. And therefore we say, if you can solve either, you solve the other. Actually, when game theory all began, people thought of V as the characteristic function of a game. A game is something else. It's the whole context. And V is the cost or the financial structure which arises from the game. So in the old terminology, the black and the green would be called different games, but they give rise to the same V. Okay? This distinction got lost. I'm going to come to this later. Maybe Shapley, by the way, when he wrote his paper, he wrote an axiom. This was when he wrote a working paper in the Rand Corporation in 1950. And the axiom was, the solution of a game should depend only on its characteristic function. Today, this sounds totally bizarre because we think of the characteristic function as the game. We have identified the two. I want you to remember that we shouldn't, and I'm going to use that fact much later. Okay, so I hope you are with me that here are two different games. One is a transmission game, the other is an airport game. The airport game is in green or blue, and the transmission game is in black. Two different games, but they give rise to the same cost structure. So we are going to say the solution should depend on the costs of coalitions. Don't worry about how they arise. And that's a very big assumption. Okay. Here is something which I'll pass very fast. This is for, there is a landlord and there are 7 workers. And the output of the land depends on the number of workers. It's given by this monotonic function f, and f can be concave, convex, or both, some increasing function. And the question is, how should we, if the efficient thing to do is to produce as much profit as possible, how to divide it? There is a whole class of voting games, and I'll just describe some of them. The first one is the British Parliament. The Labour Party has 48 members, Conservative has 49, and Liberal have 3. Now, on important issues, there is something called the party whip, which obliges all the members of the party to vote the same way. And therefore, we can think of each party as a player. And now, player 1, which is the Labour Party, has 48 votes because there are 48 members who can all be told to vote the same way, whatever is the consensus in the party. So there are 3 players. Player 1 has 48 votes, Conservative has 49, Liberal has 3. And we want to say that to win on any issue, you need simple majority, so that's 51. And then you see that any 2 will win, all 3 will win, anyone by himself loses, so the characteristic function is defined below. Another example is voting among stockholders in a corporation, where it's $1 one vote, not one man, one vote. Each shareholder has as many votes as his shares. Okay, so here are N shareholders of a company. The first one has W1 shares, the last one has WN shares, and we define the voting game among the shareholders as follows. Q is some quota, and a coalition wins if the total shares held by the coalition exceeds the quota, and it loses otherwise. So here, V of S, I'm writing the number 1 to say that it wins, and 0 to say that it loses. But these numbers have no meaning. I could have said it's blue if it wins and red if it loses. Okay, so forget even the numbers. So now we could ask, how much in such a voting game, what fraction of voting power is held by a player? Think of red and blue coalitions. So we don't know what is voting power in such a game. Huh? And the game that I will analyze for you in a little more detail is the Security Council in the United Nations. There are 5 permanent members: China, France, Russia, UK, and USA. And there are 9 non-permanent members, right? 6 to 15. And the coalition wins if it contains all the permanent members and at least 4 or more non-permanent members. So this is a voting game. I have written 1 for a coalition who wins, 0 for a coalition that loses, but please don't take the numbers 1 and 0 seriously. Coalitions which win are blue, coalitions that lose are red. We have a declaration of what are winning and losing coalitions, and I want to ask, how much voting power, what should we mean by voting power? I want to ask, how much voting power do permanent and non-permanent members have? We are going to actually be towards the end solve this. Okay, so one notion which we already encountered before is the core of a game. So you have a game V. If it's a voting game, think of 0 and 1 for a while, but I'll discuss this later. Let's think of games where coalitions make money. And generally it is the case that if you put together 2 disjoint coalitions, S and T, and join them to make a bigger coalition, then what that big coalition earns is at least the sum of the 2. Why is that? Because remember that's called super additivity. And why should that hold? Well, I said, if you recall the notion of V of S, it's what S can guarantee no matter what players outside S do. If that is the definition, then when the big coalitions forms, they can pretend to be 2 different coalitions, right? And then by acting as 2 different, that's one of the options they have. By doing that, they would earn V of S and V of T. So since that's one of the options, they can't earn less, at least that much. Okay. So mathematically, we may or may not need that super additivity, but it's a normal thing to assume. And then the question is how to divide V of N among the players. Well, suppose there is a division X, which is a vector, prescribes how much of Vn Mr. 1 is getting, that's x1, and so on. Well, then the sum, this just says we are dividing V of N among the players according to X. It's proposed as a division of Vn. If there is a coalition who is getting less under the proposal than what they can guarantee to themselves, then they will walk out and say, no way, Jose, we'll do it on our own, because they could earn more, and that the extra could be divided among them, everybody would be better off. So this is, we say in this case that the coalition S will block the proposal X, okay? It will be a dissident coalition, it will walk out. And that leads us to define the core of a game to be all those divisions which cannot be blocked by any coalition. That's the definition of core. You see, don't think of core as a solution. Think of a core as a collection of solutions. Each point in the core is a solution. And we collect all those solutions, but people often talk of the core as if it is a solution. That's not the case here. Okay, it's a collection of solutions, and it may not at all be equitable. So I give 2 examples. Here is a game. It's completely symmetric in the following sense. The way to describe the game is each coalition of size 1 gets 0, all coalitions of size 2 get half, and all 3 together get 1. If you hear my words, all the players are symmetric, right? You can substitute one for the other. Their names don't matter. And therefore, the equitable thing to do would be to divide 1 equally among them. However, here are points in the core. Give half, half, and 0. Half to 2 players and 0 to the 3rd player. Each of them is in the core. Okay? But it's not equitable. So we have some lurking notion in our minds of fairness or equity that's not reflected in core or stability. All right. By the way, the core, if we look at the definition above, is a convex set. It's a finite intersection of half spaces. It's not just a convex set, it's what is called a polytope, a very special kind of convex set. I won't bore you with the geometry, but it has the property that it's like a triangle, 3 vertices and all possible combinations. Each vertex is a vector, so think of n dimension. It's the convex hull of a finite number of vertices. That's what the core is. But I'll go to that at the end. Right now, we just observe that it's a convex set. So any weighted sum of these solutions will also be in the set. One of them is 1/3, 1/3, 1/3. And there are many others. So there are many, there are lots of points in the core, lots of stable divisions of V of n, and each one is coalitionally stable. Only one of them look equitable to us in this case, which is respect the symmetry and divide it equally. There may be nothing in the core. I'll leave that example. And in voting games which I described, something is well known. Only if there are veto players, that is to say, players without whom the coalition cannot win, as in the Security Council, only such games have non-empty cores. And so general philosophy is that political games which are most voting games without veto players, the core is empty, and in economic games, the core is non-empty. Now, I want to turn, so I've discussed what the core is. We discussed it last time. I have given the definition here. I want to turn to what should we mean by an equitable solution or a fair division. And that will lead to the Shapley value. So here is, by the way, no questions so far. Eh? Yeah, thank you. Yeah. No, I haven't defined the convex game. All I have said is, for any game, the core is a convex set. If it's empty, it's still a convex set. Because the convex set said if, blah, blah. And if there's nothing, it's convex. Have I answered your question? So I have not talked about any property of the function of the game V. I have said if there is a core, it has to be convex. Okay, let us think now completely differently. This is the work of Lloyd Shapley. So he says, let's think in any game, okay, of a solution concept, a way to divide V of n. So given the game V, I will describe I'll denote its solution by phi of V, or phi of V, which is a vector, giving phi 1 of V to player 1 and phi n of V to player n. Well, the first thing is that it should be feasible, and so you can't give to the players, if you divide a cake, then you can't give to them more than there is. But don't waste it. So let's say that it should be equal. And so this is efficiency. They could throw some of the cake into the sea, but we are saying that would be inefficient. So we say that the total cake, V of n, should be divided without wastage among the players. And that's this axiom. Okay. Lloyd Shapley called it efficiency. What else can we say? Well, we could say that if two players have this, so we want non-discrimination. So we want what a player gets should not depend on his gender, age, ethnicity, or anything. The only role of a player is how he appears in the characteristic function V. And beyond that, all other characteristics of the player should be irrelevant. Now, how should we say, given this non-discrimination, how should we mathematize it? When should we say that two players are symmetric in a game? Suggestions? Their role in the game is the same. Yeah. Very good. So if I hear you, I'm not wearing my hearing aids. They stopped working. I have to go back and buy them. But I think I'm trying to read your lips. I think you are saying that the way a player exists is through the characteristic function. So you are saying that if I take a coalition which contains player I, but not J, and I remove I and put in J, the coalition should be getting the same thing, right? And this should, so that's the natural idea of two players. So I repeat what you said. We'll say two players are symmetric or substitutes if whenever when you substitute I with J in a coalition S that contains neither, their role is the same, so their effect is the same, so it should be the same V of S, right? That's your, okay, you are absolutely right. So this is a second property that Lloyd Shapley introduced. It's called substitutes. Symmetry. Here is a third idea, which is very simple. Suppose we are playing a game here, and John walks in, but he has no role to play in the game. He's there as a decoration. He doesn't affect anything. I want to say that then he is irrelevant. How should I describe that? How should I describe that a player is just a red herring, a decoration, has no role in the game? How would you like to say that mathematically? Yes. Yeah, yes, very good. You are on the button. So, I'll make this assumption, Shapley rather. A player will be called a dummy if he is playing no role in the game, and which is to say what I wrote. By the way, if I is already in S, that's a tautology. The left-hand side is V of S, so it has content only if I is not in S. But that's the third assumption. Two players who are substitutes should get the same, no discrimination or symmetry. A player who is irrelevant, who's just there doing nothing, should neither incur a cost nor a benefit. He should get zero. Right? Dummy. So these are three axioms, and please observe these are local axioms. They talk about a game. Up till now, I have never put together two games in the axioms. Now there is the last axiom, which is, in my opinion, wrongly called additivity, but let me describe it and then talk about it. I want to, given a game V and another game W, I want to define formally the game V plus W. And it's defined as written above, that in the game V plus W, a coalition gets V of S plus W of S. Okay, that's a definition. Okay, and the axiom is that the value of a player in V plus W is his value in V plus his value in W. I want to discuss the content of this axiom. So I'm going to do it this way. There is a game being played, and the players are sitting in New York. Okay, and the players are 1 to N. They are the real players in the game. They run a business which operates in New Delhi and independently in Beijing. Each player has an agent of his, one prime. Player 1 has an agent 1 prime in Delhi and 1 double prime in Beijing. These agents simply obey their masters in New York. Now, this company whose headquarters are in New York is earning money from both Delhi and from Beijing. And the money it earns in Delhi has nothing to do with what's going on in Beijing. This is something I'm imagining. It is irrelevant to ask, is this real? Does this happen? That is a question which is irrelevant right now, because the purpose of the Shapley value is to describe all the solutions to any game that could be played. It could be played on some planet, not on Earth. Anything which is logically consistent and playable is a game, and the ambition of the Shapley value is to tell us how to divide the proceeds of that game. So the game it has nothing to do with what is relevant or what is practically happening here. Anything that could happen is also something we want to solve. Okay, so I'm developing a story. The story is of such a company. Now, so if they fully cooperate, what they could earn is V of n plus W of n. The problem is how to split it. So there is two things they could do. One is they could go to the court in New York, and the judge will ask, what's the problem? And they'll say, here is the situation. This is what any coalition of us can earn. So they'll describe the game V plus W, which is the game in New York, to the court in New York. And the judge will say, here is the solution. Okay, so think of the Shapley value as something that the judge decides. Now, instead of going to a judge in New York, they could instead tell their agents, go to the judge in New Delhi and go to the judge in Beijing separately. Then the judge will rule phi of V here, phi of W here. So I want to say that the law should be consistent between Beijing, New Delhi, and New York. And the way to say it, it doesn't matter whether you litigate here and here separately or you litigate here. And so that's the axiom. So I want to think of it as consistency, not additivity, though mathematically it looks like additivity. Am I making sense? Huh? I'm telling a story. I'm trying to justify the axiom. So if we accept these four axioms, then there is a lovely theorem due to Shapley, published in 1953, but he wrote a paper on it in 1950. And it says that there is one and only one way to define for every game V a solution. So we want a solution for every game V on n players, not just a particular game. Yeah. We want to solve a game that could possibly arise on Earth or some other planets somewhere else in time and space. Any game V that could arise, we want to be able to say, what is its solution? We say that this solution concept should satisfy the four axioms I mentioned. And Shapley's theorem is there is one and only one way to define this map, and it is given by here. So what it's given by, it has a formula. So not only is there a unique map, but we can write a nice formula for it. Now, for the formula, I'm going to tell you a fairy tale, which you must not please take seriously. There is a formula. I could tell different fairy tales and describe the same formula in different ways, but I have to describe a formula, and so the formula is this. Imagine that the players enter a room one by one. So with 6 players, I'm looking at the case where player 2 enters first, then 1, then 5, then 3, 6, 4. Okay? That's one order in which the players can enter a room. And as they enter a room, each guy we ask, what does he bring to the table? So if you look at player 5, before he enters the room, the size of the cake is V of 1, 2, because 1 and 2 are already in the room. Now player 5 enters. So before he enters, this is the size of the cake. After he enters, this is the size. So his contribution, or what he brings to the table, is the difference. If it's negative, he's causing harm. If it's positive, he's causing benefit. So what a player brings to the table is what he should get in this order, right? So for any order, I can look at the marginal contribution of each player. Now, the Shapley value formula says, please look at all possible orderings and give to a look at the contribution of a player, John, in all the orderings and take his average. All orderings are equally likely. That's the formula. But the formula, the story for the formula, the fairy tale I told you, has no meaning. There is no room. Players never enter it. There is no order. It is just a formula dictated by the four axioms. And to remember the formula, yes, please.
Okay, so about the first three axioms, it could be replaced by one, simply that if in a game where a certain number of players are in the coalition, then they get some utility, otherwise they get zero. In this, we should share them equally.
Yes.
If you have this plus additivity, these two axioms define
Sure.
already
So
the same.
what you are saying is absolutely right. You are saying, suppose you have a game in which where we can partition the players into two sets. First set, all are dummies, and the second set, all are symmetric. If the game has this property, then you should take the total and divide it only equally among the symmetric players and give nothing to the dummies. This follows from efficiency, symmetry, and dummy axioms. So we want to isolate the main concept behind each. And so the one reason to separate it instead of putting it the way you did is to simply emphasize the ideological content of no discrimination and the irrelevant players and efficiency. Okay, it's we are saying the same thing. I'm speaking in English and you're speaking in Sanskrit, but we are saying the same thing. Okay, I have just elaborated what you said. I don't know if I have answered the question, but you are right. Okay. In fact, I will use what you said when I give the proof. Okay. So this is the theorem of Shapley, and I want to prove it. So I'll just show you one example. Here is a game with three players. So there are 3 factorial random orders in which they can enter. Let's look at the random order 2, 1, 3. Well, I looked at the contribution of player 1. What will it be? He enters second. So his contribution, before he enters, it's V of 2, which is 0. After he enters, it's V of 1, 2, which is 4. So his marginal contribution is 4. And so I computed the marginal contribution of each of the players. Then the Shapley value formula says add up all the contribution of player 1 and take the average, since each order is equally likely. And this would be the Shapley value of that game, right? Just illustrating how the formula works. All right. Escape. By the way, how much time have I used up? Huh? 47. Okay. I never know. So now I don't know how to bring this into shape. What do I do? I clicked Control L. Yeah. So let me write the formula. So forget this page completely. So I want to describe the formula in one go, and it's like this. Let us partition all the n factorial orderings as follows. I'm going to look at all the orderings which have the following property, that before player I enters, the coalition of the people in the room, the predecessors, is some fixed set S. And then I enters, and then the rest enter. Why is this a good way to look at it? Because in all such orderings, the contribution of player I is the same. It's V of S union I minus V of S. Okay? So now we ask how many such orders are there? Well, the people before him, capital S, its cardinality will be denoted by small s. they can enter in S factorial ways, and after him they can, because he's not there, so the players after him is this, they can enter in so many ways. So you can take any ordering here and combine it with any ordering there. So the number of orders of the type that I described is S factorial times n minus 1 minus S factorial. In all of these, Mr. I's contribution is the same. And that gives me a formula here for the Shapley value. Okay. Any questions? All right. I want to now compute the Shapley value for the Security Council. Okay. I think it's quite interesting. Before I prove Shapley's theorem. And so let's try to, so one thing is clear in the Security Council game, that all the permanent members are symmetric to each other and the non-permanent are symmetric to each other. Therefore, all the permanent members will get the same, all the non-permanent will get the same. And the total that they get, since we are asking, total is 1, a winning coalition gets 1 right now. It's enough to find the Shapley value of one player, either the permanent or the non-permanent, and then we'll know everybody's Shapley value, right? Okay, because, okay, so I'm going to try to compute the Shapley value of China. And so we try to do it, and we say, so now one thing happens in these voting games, which is, I forgot to mention. In any order, there is one player only who makes a contribution and the rest gets 0. Because as the coalition builds up, it's losing, losing, losing. At some point, it will become winning. And after that, it will remain winning. So the guy whose entry converted the losing coalition into winning, his contribution is 1 and all others are 0. So in any order, there's exactly one player who hogs all the marginal contribution. He's called a pivot in that order. So we are now going to ask, to compute the Shapley value of China, how many orderings are there in which China is a pivot? So what must happen? Well, if China has to convert it to a winning coalition, all the 4 permanent members should be present before him, because if any permanent member is missing, even after China enters, it will remain losing. We want to ask, when is it that China, by its entry, converts a losing coalition to winning? So what must be happening before? There should be 4 permanent members and at least 4 non-permanent members before China enters. So I want to try to compute it. I say, fix a set of k non-permanent members, any set, okay, where k is at least 4. Okay, so here k is any number. Then the players before China would be k plus 4. I'm fixing a set of size k of non-permanent members. So the number of such orderings for any fixed set of size k is k plus 4 factorial times 10 minus k factorial, right? For k non-permanent members entered before, so this coalition, the predecessor set has 4 plus k people. They could be permuted in k plus 4 factorial ways. The ones after is 10 minus k. So this is the number of orderings for a fixed size k. But the number of sets of size k is 10 choose k. Therefore, we have to now look. The value of China is, so I first computed that and then I wrote the formula, and it becomes too much. I can't even compute it. I just can't compute it. But there is always 2 ways to look at a problem, one complicated and the other simple. And I want to tell you this famous story you must have all heard of 2 trains which are approaching each other at 20 miles per hour. You've heard this, and they are 100 miles apart. And a crow is flying from one engine to the other at 30 miles per hour. And the question is, how much distance does the crow fly? It keeps flying till the trains collide. And this question was asked of mathematicians and physicists, and the mathematicians said, very interesting. First, it will fly so much, then on the way back so much, then so much. They develop an infinite series to compute. Physicists always gave the answer very quickly. They said that the trains are, each train has to travel 50 miles, right? And so they're moving at 20 miles per hour. They'll collide in how much time? 2.5 hours, right? Am I doing it right? And the crow is flying at 30 miles per hour for 2.5 hours. So it's 30 times 2.5. That's the distance the crow flies. The infinite series is very long, and looking at it another way is very short. So when this guy went to John von Neumann, he thought for a second and he gave the answer. And then the guy said, you are the only one who thinks like a physicist. He says, what nonsense. No physicist could sum an infinite series so quickly. So he did the infinite series in his head. That's the story all made up, because John von Neumann was very fast, apparently. Another one which I ask you, also two ways to look at it. Here is 2 cups, one with tea, the other is coffee, filled to the same level. You take a spoon of the tea and put it in the coffee. And you take a spoon of that mixture, it need not even be homogeneous, and put it back in the tea. And you 20 such round trips. And then you ask, is there more tea in the coffee or more coffee in the tea? Well, you can try to look at this series of how much transfers are taking place, but that will become complicated. You can look at it another way, which is, let's look at it after the 20 round trips. Now, since there is look at the tea. Some tea has left here, maybe 0, maybe something. Well, since the volume is the same, whatever tea has left after 20 round trips, that much coffee should have come in to keep the volume the same. And therefore, there is as much tea in the coffee as coffee in the tea. So I gave you 2 problems where if we look at it one way, it's almost impossible to solve. And if you look at it another way, the answer leaps to your eye. Similarly with the Security Council, we were doing it wrong. Let's instead compute the Shapley value of India, which, though it has the largest population, is still a non-permanent member. China always blocks India. So let's compute the Shapley value of India. Which are the orderings in which India would be pivotal? Well, for India to be pivotal, exactly before India, there should be 5 permanent and 3 non-permanent members. And in any such ordering, there will be 8 before India and 6 after India, non-permanent. And so that will be 8 factorial times 6 factorial once you fix the set of the 3 non-permanent members. How many ways can you pick them? There are 9 of them because India is out. Its position is fixed. 9 choose 3. So that's the Shapley value of India. Now we know even that of China as follows. So I computed this. It comes to 4 over 2145. That's the Shapley value of every non-permanent member. And there are 10 of them. So together they have 40. The rest is divided equally among the permanent members, according to the Shapley value. You see how little power Brazil and India would have as non-permanent members. In the game, UN Security Council, we could also solve, supposing you change the rules and said, instead of 4, all 5 permanent and 4 non-permanent, let's make it 6 non-permanent. You'll improve the value of the non-permanent, but very little. If you say all are required, then everybody becomes symmetric. Okay? So I leave this as something for you to think about. Okay? So we solved the Security Council. Okay. And so all 10 non-permanent members have 1.86% of the power, and the rest is split equally among the 5 permanent members. So they are almost powerless according to this notion of voting power, which the Shapley value talks about. Now, how do I get out? How do I get out of here? Escape. Sorry. And meanwhile, while we are fixing this, is any questions so far? 3. I want to open. Yeah, I want to open this now. 3. Okay. Yeah. Now you see these are repetitive slides because I lost one, then I made it again, then I lost it, and I made it again, so I'm going to skip. Yeah, now 1 second. Let me try to solve this one for you. Just a second. How do we solve the Shapley value of this game? Maybe I'll do it later, or have I done it? It's 256 coalition. Looks impossible to solve by brute force. But there is a way to think about it, which will make it very transparent. So for any edge over here, let's say the edge whose cost is 20, I want to imagine a game on all the players as follows. In that game, a coalition gets 20 if it has somebody in it has to use that edge, and all the otherwise its cost is 0. So I associate a game among one for every edge over here. Do you see how I have defined the game? Take any edge, and I have to tell you what the game based on that edge is. Okay, so for any coalition, if somebody in the coalition has to use the edge, they incur the cost. If nobody in the coalition uses the edge, they incur 0 cost. This is a game in which all the users of S are symmetric, all the non-users are dummies. So this is a transparent game. Divide the cost of the edge equally among the users. That's what you get from dummy and symmetry in the game among all the players, which is based just on one edge. All right, but the whole game is just the sum of such games. Therefore, by additivity, the Shapley value says take any edge and divide its cost equally among all the people who use it. And we've got the solution using the axioms, using the axiom of dummy, symmetry, and additivity and efficiency. If you don't think of it that way, if you don't imagine a game among all players, this is an imaginary game, they are not playing it, but we're going to imagine a game based on an edge, one edge, and ignoring all the other edges. And the way we imagine the game, I repeat, is a coalition gets the cost of the edge, has to suffer the cost of the edge if one of them uses it. And otherwise, the coalition gets 0. That is a game which is not being played, which we are imagining, based on an edge. And then the real game is just mathematically a sum of such games. So according to the additivity axiom, we should simply solve each of these imaginary games and add up. Now, in each imaginary game, you split the cost of that edge among all the people who use it equally. And that's it. So we now know the Shapley value of this whole complicated game. Okay. Okay, now I am thinking, if I have time, I'll now give Shapley's proof. How much time do I have? By the way, am I going too slow? Huh? 6 only. I can't give the proof with any feeling in 6 minutes. So I'll just describe the roadmap of what we'll do next time. We are going to ask, first we are going to prove Shapley's theorem. Second, I want to ask, when is it, so it'll tell me what is a fair division. But what is fair may not be stable, it may not be in the core. So we want to ask, for what kind of games is the Shapley value, which is an equitable solution, also in the core, which is stable? Okay, so when do the two ideas meet? And a nice class of games, which, by the way, the transmission game and the airport game all are part of this nice class, is games which are convex. Okay, so I'm going to, the idea of convex is increasing returns to cooperation. The idea of convex is that if you are a player and you join a small coalition, you have some contribution. If the coalition is enlarged and you join it, you make a bigger contribution. That's the notion of a convex game. The more the merrier. Increasing returns to cooperation. Such games often arise. There's a lot of cost allocation problems give rise to such games, especially if there are multiple users of the same facility. You have economies of scale. So such games will lead to what I'm going to define to be convex games, and then we can show something another paper by Shapley. This whole lecture is about Shapley. He showed that in such games, the Shapley value is not only in the core, it is in a sense that Newton defined a center of gravity of the core. Newton defined for a bunch of particles rigidly connected to each other the notion of center of gravity way back in the 1700s. We are going to show that this is the center of gravity of the core in a very precise sense next time. So it's not only in the core, it's very centrally located in the core. So that will be, so what I'll do next time is, let me describe the roadmap. I would like to prove that the Shapley's theorem, and also what I just said, that for a large class of interesting games, the Shapley value is in the center of the core. Then, my last lecture, I have some work I have been doing very recently, which is to discuss, can we define the Shapley value in games where all coalitions don't form? Games with incomplete coalitions. And I'll give some examples. So in that case, by the way, the random order formula makes no sense whatsoever, because in any ordering, if you want to compute the marginal contribution of a player, you have to know what the coalition before him gets, but that may not be feasible. Or after he joins, then the coalition that forms after he joins may not be feasible. So if you have incomplete coalitions, even the formula for the Shapley value, which by the way I don't take seriously because people never enter a room in any order, there's no room. But the Shapley value, the formula doesn't work. So can we think of the Shapley value of games with incomplete coalitions, and where in the real world are some interesting examples of this? So that's some work I have been doing recently. I hope to finish writing the paper when I go back to Stony Brook, and I'd like very much to present that in my last lecture and get some feedback from you. So that's the roadmap that I have in mind. Okay. Cooperative games is a very big field, so I had to pick a few things to talk about. And I think we can stop for today. Any other questions, comments? I think let's use the 5 minutes for any comments or questions you might have.
Thank you very much, Pradeep. Very nice lecture.
Thank you.
You talked about your example with a cup of coffee and a cup of tea.
Yes.
And
yes.
I wondered about how the Shapley value helps in answering the question.
Well, I was only drawing a very high-level analogy by saying that if you look at the Security Council problem from the right angle, right way, you'll get a quick solution. And if you try to look at it through China, it becomes very complicated. If you look at it through India, it's very simple. That was all. So it was an analogy that was saying two ways to look at the same problem. One which makes it hard to solve, and the other which also solves it the solution is very simple. And often there are many problems, at least in mathematics, which have this property. Look at it one way, it's very hard. Look at it another way, it's much easier. I don't know if I have answered. So in both these examples of the crow and the cup of tea, there is a hard way to look at them. Yeah, which von Neumann did for the first one. Yeah, that's all I meant. So it was a little relief in the middle of all this math to tell you these two puzzles which we can give to our friends who don't know math. And if they don't know math, they'll probably solve it faster. Maybe. Any other questions? Well, thank you for coming, and we will continue.
Professor?
Yes,
May I?
please.
I see the Shapley value as a way to consider the inside and outside options of players in the game. And do you see any connection of this Shapley value with other solution concepts as the Nash solution and the kernel, core, things like that?
You mean how to connect it to the Nash bargaining solution?
Yes, exactly. Because it also, in my point of view, it also considers the outside options of players and what they can bargain surplus, right?
Well, let me take it as homework and think about it. And we can all think about his question, which is there a connection between the Nash bargaining solution for side payment games and the Shapley value? They both respect symmetry, for example. But let's think about it. I don't know offhand any paper which discusses this point. It's maybe a paper you will write.
I
Okay.
hope so.
Yes.
With you.
I'll be happy to listen to you and discuss it with you.
Okay. Thank you. Any more questions?
Okay.
Okay, so
So we call it a halt for today. Thanks.
yeah.
Mano, vai, para. Deixa eu ver. Depoimento. E o professor Aumann não vai entrar agora? Professor Aumann. O professor Aumann. Tá. Sim. Hello, Professor Aumann. Are you hearing me?
שומע אותו.
מה?
הוא שאל אם אתה שומע אותו.
Do I hear you?
Yeah, do you hear me?
Yeah, I heard you, but I didn't. I didn't know you were talking to me.
Oh, we will start briefly. They will let you know, okay?
Okay, do you hear me?
Yeah, we do.
שומעים אותם טוב.
You hear me?
Yeah, we do.
Okay, good.
משהו בעיה. נעשה את השאר?
מה?
נעשה את השכין share?
כן, share.
צריך לשתף, לא?
עוד לא. למה אני... זה שמה. אוקיי. הסקרין שייר נעשה רק באמצע דבריי, או אחרי שאני אומר משפט או שניים, נביא את הסקרין שייר, כן.
Thank you. That's my Hebrew. That's all of it. Hello. Does this work? Good. Bob, do you hear me? Roger here in Sao Paulo. No sign. He doesn't.
Okay. Hi. Good morning, Roger.
Good. Yes, and I see, now I can see a small picture that probably you can see of me. Good. So, Bob,
Hi, Roger.
Bob, you go first with 10 minutes.
Shmuel.
We'll get the high sign when we can start. The Poisson arrival process is like it 4 per minute.
מה? אני כאן, אני רואה את מיירסון.
לא שומעים אותם קצת, יש ניתוקים.
מה? איפה אתה באוניברסיטה? מה אני אגיד? אני לא אל תשאל אותי. אני האדם האחרון שאתה צריך לשאול בנושא. לא, אצלי לא היה בעיה. זה לשלוח לך את ה...
Bob,
אני ראיתי את מיירסון, אבל אמרתי בוקר טוב, אבל הוא לא הגיב.
Somebody should admit Elon Kohlberg. We have the privilege. Admir Elon Kohlberg. Obrigado. Bob, I arrived late, so I missed your talk yesterday, but absolutely everyone else heard it. And Pradeep has a question about why people reject insulting offers. Did I get that right? Good.
I do what?
Why people reject citing offers?
Anyway.
Okay. Are you asking me a question, Elon Kohlberg?
We haven't started yet, but I'm forwarding a question to you from Pradeep Dubey, who's here in the audience, from your talk yesterday.
Roger, are you speaking, or who is that that's speaking?
This is Roger Myerson speaking in Sao Paulo.
Myerson. Okay, yes. Now what's your question, Roger?
Well, this is a question from Pradeep Dubey, and you can answer it now or later, but in a few seconds we'll start the session for official. But while we haven't started, we're not messing around here. Pradeep Dubey said to me a question he had from yesterday, which I missed because I was still coming in from the United States of America. He had a question about why in bargaining do people turn down insulting offers that still would have given them a positive payoff? And I could answer it later, but I want you to know that's just part of it.
Insulting offers.
Yes, like the five,
all right, the
five and the
people because they are used.
No,
to
wait. I've already. Of course, just a minute.
You missed the answer. You missed my
Bob,
answer.
Can you hear me?
I can hear you, not very clearly.
Okay,
yes.
Yesterday you.
I hear you now, but Roger, let's discuss that later. Let's get on with this thing. Okay. We can have a Zoom session or a phone call, but let's get on with this session.
Let's get going. Yeah, no fooling around.
Roger, do you hear me?
This is Roger Myerson in Sao Paulo, and I hear you, Bob. You are. Whenever you want, you can. Let's just get started. It's time. This is a panel organized by Yair Tauman, who isn't here, and I volunteered to be on the panel at the last minute. And it's about is game theory useful for real-world conflicts? And we have the first 10 minutes for Professor Robert Aumann speaking to us from Israel. Bob, the floor is yours. Bob, your time is up. Just go now. Start. Hello. All right. I am proud to introduce the man who needs no introduction, Robert J. Aumann. Sir.
ישראל, אני יכול רגע לבדוק משהו?
מה?
אני יכול רגע לבדוק משהו?
כן.
צריך גישה למחשב.
מה?
צריך גישה למחשב. רגע. ננסה לסדר את זה, שתוכל לשמוע אותם. מה הבעיה אצלנו? או אצלהם. אתמול לא הייתה בעיה.
תודה.
טוב, הבעיה אצלנו. סליחה. תלוודא שזה לא אצלנו.
כן, מרל.
Can we start now? Hello. And now, Robert Aumann will speak for 9 minutes.
Roger, you want to let Neyman is the host is not letting Neyman into the session.
I have no control over that.
Here he is. Here he is. Okay.
Okay. Okay, you're on. Bob, man who needs no introduction, Robert J. Aumann, great game theorist.
Okay.
Your presentation begins now.
I don't hear you. Roger.
Begin. The floor is yours, sir.
Michael here.
יש להם בעיה בסאונד. רגע בדקתי, זה לא אצלנו.
Okay. Who wants to go first? Abraham, do you want to go first? I know our plan was that Bob would go first, but if you would prefer, if he doesn't want to go first, you can go first. Okay.
Roger, do you hear me?
Bob, I hear you very well. I would love for you to go first.
Abraham, do you hear me?
Yes, we hear you.
Yes, I do.
You do. Roger, do you hear me?
Yes.
But we don't see the slides. I don't know if Roger is talking.
All right. When it's my turn, I have a slide I want to post. Does anybody else have a slide they want to post? Our agreement was that Bob would go first, and that's not the appropriate thing to do, but perhaps okay. But Bob, I am not. The screen shows that none of us are muted now. Professor Aumann, do you hear us in São Paulo? This is Roger calling. Okay, I better start. I know the plan was that I would go in the middle, but I guess I go first because nobody else is on. Would somebody please post my slides? It's not going to happen.
Tell him he's breaking up.
The good news is we're not in conflict here.
I can't make out what you're saying. But if you're saying so.
Roger, we cannot hear you and we don't see the slides.
Yeah, I don't see slides either, but I do hear you both very well. And but 5 times I have introduced Bob Aumann and asked him to start speaking. It is time for Bob Aumann to take 5 of his 10 minutes have gone by. But I guess one of us can take that out of our time. All right.
And Robert, can you hear us?
I think if someone would send a text message or something to them, I don't know how. Do you understand why they don't hear me? These gentlemen here. Am I not speaking loudly enough?
No, you are.
I cannot hear you.
All right.
I mean, I can hear an occasional grunt, but I can't make out what you're saying.
Please speak. Your turn. Okay, let's. Bob, speak. Yeah. Bob, please start now.
I can't read it. I can't read it. It's not, it's in the shade. It's not lit. Please.
Pradeep? Okay, Bob.
Then after him, you can talk, and then Roger, we can hear you.
Bob, Israel, they suggest that you start talking.
Bob, please start now. Start now. Okay, I'll start now. Okay. Okay, fine. I'll do a share. Address. This?
PowerPoint, yeah.
Huh?
Yes,
On the PowerPoint.
yes,
Yeah, okay.
yes. Share down at the bottom.
Yeah. Okay.
Again. Another
Um,
click.
make it large and make it okay. Okay, so war and peace, what can game theory teach us? Okay. So let's see. Now, what is game theory? Okay. Well, this whole workshop is about game theory. So I'll try to sum it up in one word, and one word is incentives. Okay. Now, the truth is that not all of game theory, but a lot of game theory is about incentives. Okay. So we're talking about war and peace, and what can game theory teach us? So what are the incentives? What are the incentives for peace? You make concessions. Is making concessions a good idea to achieve peace? Well, let's look at not theoretical game theory, but practical game theory, history. Practical game theory is history. And Munich in 1938. Now, you remember in 1938, most of you are too young to remember 1938, but maybe you read about it in the books. In 1938, Hitler was trying to annex a good part of Czechoslovakia. And there was a meeting in Munich between Chamberlain, the Premier of Britain, and Daladier, the Premier of France, and Hitler, the leader of Germany. And Hitler insisted that he gets his way. And Chamberlain and Daladier asked him, "Is this your last demand?" Okay. And Hitler said, "Yes, it's my last demand." So they said, "Are you willing to sign an agreement to that effect?" He said, "Yes, I'll gladly sign an agreement." So he signed an agreement, and Chamberlain went back to London and told the House of Commons, told the British Parliament, "Yes, I have brought with me peace in our time." Now, what he brought with him was war. And the war broke out in a year and a half later. Okay, a year and a half later. This was March of 38. September of 39, Hitler invaded Poland because of the concession. The concession, a one-sided concession, not necessarily both sides make concessions, but a one-sided concession is a mistake. It deceives the enemy, the other side, into thinking that you are that you will make more and more concessions, and it leads to war. It does not lead to peace. Hitler really thought that there was going to be that England would not respond, and England did not respond, and Hitler invaded Poland on September 1st, 1938, and it took Britain 2 days to respond, to declare war on Germany. This was on September 3rd, 1939. Sorry, not 38. September, Hitler invaded Poland on September 1st, 39, and Britain declared war on September 3rd, 39. And the reason is that Chamberlain really did not want to go to war at that time. And his cabinet told him, Neville, if we don't go to war now, then you are not the Prime Minister of England. Okay, you are not the Prime Minister of England. But Hitler really thought, he was convinced by the concessions that England made in Munich, that they would not go to war. And they would not go to war. Okay, let's go to the next item. Disarmament. Will disarmament peace? Is that an incentive for peace? And the answer is no. It's not an incentive for peace. Concessions are not an incentive for peace. One-sided concessions. And disarmament, one-sided disarmament is not an incentive for peace either. And the Cold War proves that. There was a lot of pressure in the United States to disarm unilaterally and destroy our atomic bombs and leave Russia with its atomic bombs, leave the Soviet Union with its atomic bombs. And there was a young idealistic students held demonstration demanding one-sided disarmament. And what kept the peace was, what kept the Cold War from going hot was that both sides had nuclear arms. Both sides had it. And that is what kept the peace. So concessions brought war, and the insisted that the United States did not disarm unilaterally, kept the peace. Okay, so disarmament and concessions are not incentives for peace. What is an incentive for peace is illustrated by the Pax Romana. The Pax Romana is a period of relative peace that lasted in the first 2 centuries AD. The first 2, approximately, it actually is from 27 BC until 190 AD. It was the Pax Romana, the Roman peace, which is 200 years of relative peace in the world. And the motto of the Romans at that time was Si vis pacem para bellum. If you want peace, prepare for war. If you want peace, prepare for war. Okay, and even in Israel, this is not understood by everybody. I once gave a lecture, unit of the Israeli army, and I said, develop this weapon in order not to use it. In order not to use it. That's why you develop the weapon. You develop weapons in order not to use them. If you want peace, prepare for war, okay? Because that gives an incentive to the other side not to attack you, all right? Now, another example, an example of this is Switzerland. You know, I go with my grandchildren and my great-grandchildren. I go every, I take one descendant at a time, one to Europe, usually to Switzerland or to France, or tomorrow I'm going to the Azore Islands with a great-grandson. And I go one-on-one, just and me, so we really get to know each other. And once I was with a grandchild in Switzerland, and there was a fighter jet of the Swiss Air Force fighting, screaming above us. Okay, we were in the Alps, we're climbing a mountain. Okay, we were, and my grandson said to me, he said, "Grandpa, what is that plane?" So I said, "It's a fighter plane of the Swiss Air Force." So he said, "Why do the Swiss need fighter planes?" So he said they have been at peace for over 400 years, okay, including World War I, including World War II. If they have been at peace for over 400 years, why do they need fighter planes? Yes. So I said to him, Nave, that's his name. You know why they have been at peace 400 years? It's because of that fighter plane. Okay. It's because of that fighter plane. That is, they don't need, because they are prepared for war, and that is why they are at peace. Okay? That's Switzerland.
Thank you.
Now, I will end up with some local affairs, okay? The Iran-Israel confrontation, okay? So in the last few weeks or months, yes, there's been a very much disquiet, yes, in the Middle East. And the United States is bombing Iran, and Iran is bombing the United Arab Emirates and Qatar and Jordan and Kuwait, and Qatar, but Iran in the last couple of months, Iran has not bombed Israel, has not sent missiles against Israel, has not sent what's it called? Unpiloted airplanes, has not attempted to attack Israel from the air. And you know why? You know why? The reason is that they are afraid, because if they are going to bomb us, then we will really let go against them, and their attacks against us, I won't say they don't cause any damage, but they cause generally very little damage, and our attacks against them hurt much more. So game theory teaches us incentives for peace is, to sum it up in terms of the Pax Romana, si vis pacem para bellum. If you want peace, prepare for war.
Yes.
Thank you very much.
Thank you.
Obrigada.
If my slides could be put up, that'd be great. Thank you.
Thank you.
I'll take my time right away. Bob, you spoke very persuasively, of course, and of course I agree with all the principal applications of game theory you described. And indeed, the 1938, I'm going to jump to the middle of my slides when they appear, to strategic deterrence. On the middle of the first slide when it shows up. Anyway, thank you. Strategic deterrence is really, we are game, by the way, it'd be nice if this was such that we could see the other speakers. Yes, thank you. The organizers have given me a note here that I should ask you to increase the volume on your computer so that you're able to hear me. Thanks. So indeed, you have taught us, you have reminded us that, for example, a key lesson from 1938 Munich negotiations was that it is dangerous to appease a militant adversary, because that may just encourage him to even greater demands. But Bob, we are game theorists. When we are game theorists, one of the things we do is look at every conflict situation symmetrically from every situation. The basic principle that has to be remembered is that strategic deterrence depends on two parts. There is a promise and a threat. The threat is, we hope, off the equilibrium path, as Switzerland has shown. The threat is the threat to be a dangerous adversary in case our enemies cross some red lines that we draw. But if they don't cross the red lines, we're supposed to not do the same thing to them, but we're supposed to have a promise of better behavior, of being a good neighbor. Now, one of the things we should remember as game theorists when we put ourselves in our adversary's shoes is that our adversaries are also thinking that it is dangerous to appease a militant adversary because it may just encourage him to greater demands. And therefore, if we truly want peace, yes, as you say, we must prepare for war. We must be prepared, have the capability to deter violent attacks by violent counterattacks of our own. Unfortunately, nonviolence is not an equilibrium in the world we live in. However, we also must make credible that if they do appease us, because that is what we want when we draw lines, we say, we want you to stay on that side of these metaphorical lines and behave better towards us, and in return, we will stop beating you up, and instead we will treat you much better. And that is something that typically, when there is a history of adversarial relationships between two peoples, the credibility of those promises is seriously in doubt, and costly signals are needed to try to begin to convince our adversaries that it can be safe to appease us, that accommodating our demands is not like accommodating Hitler's demands in 1938, because our adversaries have also read the history of Munich 1938, only they think that we look like the Hitler in that story, even though we don't feel like that. We feel they're wrong, but we need to prove it to them, and that may take costly signals. Certainly, a surprise attack that murders the leadership of a nation is not the kind of signal that's going to increase their confidence in our promises. So it was extremely costly in terms of the credibility of the promise. So please, I don't understand, let me say, game theoretic rationality is an assumption which should be true of everyone. I will make an empirical observation on the limits of game theory, which is that people seem to be much more ready to understand the importance of the credibility of their threat than to recognize also the importance of the credibility of their promises. Now, for weak nations, it's the credibility of the threat that's the hard part, because the weak nations, when they get into conflict, are going to suffer the most. But it's the stronger nations, Israel, for example, being strongest in its region, and the United States being at least recently the strongest nation in the world, until recently. For the stronger nations, what's much more difficult is convincing potential adversaries that you would not just use your ability to beat them up even when they accommodate you. And therefore, it is the stronger nations which have particular need to focus on the credibility of their promises, on costly signals to show that they abide by international law as construed by some jury of the world. So that's point one. I've got a few minutes left for this game theory, so that's my answer to what needs to be added, I thought, to your presentation, Bob. The most important thing I want to say to this audience in game theory is that, yes, game theory has something to say about real-world conflict. I think a very good place to start, obviously, by the way, Schelling's Strategy of Conflict, the crucial chapters 1, 2, and 3 are available. They were published and are on JSTOR. So in case you don't, buying the book is always a good idea, but you can get them if you're from JSTOR in PDF. And of course, one of those chapters that begins with the question of limited war, understanding limited war as an understanding, and that they're about commitment and coordination. Jim Fearon's 1995 paper in International Organization on rationalist explanations for war is by far the best place to begin. And what he does there is he takes on a variety of well-known explanations for the origins of war in the political science literature, and shows how in a game theory context they can be understood purely in terms of basically moral hazard and adverse selection constraints that prevent the peaceful equilibrium from existing. Now, let me say, and by the way, if you want to do research in this area, a good place to start also would be to download Jim Fearon's recently published survey in the 100 Years of Game Theory volume, which gives his survey of the literature up to today, up to 2021 when his paper was written. But let me say one of the questions for example, in Fearon's paper is this empirical regularity that civil wars tend to last longer than international wars, and ultimately the explanation, to give in one line, I don't have, is sovereign moral hazard. When we're in a civil war, whichever of us wins is going to take one side ultimately has to take control of the next nation, and under traditional rules of Westphalian sovereignty, that means whoever gets control of the nation has no laws restraining them from beating up on the losers, and therefore it's hard to make a credible commitment to share power within a nation. Whereas in international law, in international forum, the alliances of other nations can help to make credible a restraint. The fact that the Russians think, for example, that Ukraine should be part of Ukraine, that Ukraine should be part of Russia, makes it harder for the Russians to credibly, and that Putin has betrayed the Chechens, for example, after a peace treaty, makes it harder for Russia to commit itself to not use any peace, like Hitler used the agreement in 1938, and simply go forward. You reject. You're afraid that concession now will just be used against you, and therefore you can't make peace. What I do want to say in general is that Fearon's paper in 1995, it includes, he says, you should understand that there are two major questions in game theoretic questions about war. One is about the onset of war, and the next one is going to be about the duration of war. I would like to observe. I have a paper on game theory in the First World War where it's about half about understanding the First World War from game theory. And Scott Walford's book is by the way, a textbook on game theory where every chapter is introducing a concept of game theory with an application in World War I. And by the way, they're in both his logical, pedagogical order for game theory and also in historical order, which tells you he had a lot of examples that he could shuffle up his deck. But anyway, I want to observe that Fearon says, when we're studying war onset, our methodology should be, if there is any peaceful equilibrium, where a Nash equilibrium of the game, where they don't go to war and avoid the cost. First of all, war should be costly for all concerned. Otherwise, the model, it isn't war. War is something that is costly for all concerned. And if that's not true in your model, you're not modeling war correctly. So if these costly equilibria of war are avoidable, there are Nash equilibria where we avoid war, then we should assume that the concert of nations will find a way, the diplomats will find a way to avoid war in a way that is credible to all parties. But that's not necessarily true in models of war duration. In models of war duration, so in models of war onset, we assume that the parties are initially at peace, and peace, by definition, means that they share a way of a focal arbitration procedure to avoid the inefficiencies of war, to focus on equilibria that will avoid the inefficiencies of war. But the methodology that game theorists should bring to the analysis of models of war duration, where you start with parties that are already at war, you must not assume that if there's a better equilibrium, they will find it, because by definition, they have rejected all of the mechanisms of arbitration. And now each side is afraid, if I conceded to that we would just go to an equilibrium in the subsequent peace where I was viewed as a loser, and I'll suffer even worse. So therefore, I must continue to pay the cost of war. The last thing I'd like to say, turning over the time, is in the models of war duration, there is a fundamental mistake in the basic model of war duration is the war of attrition model. And I'll simply say that in my paper, there's a section, I have a second slide. If I had time, I would have gone through it, but I don't. Maybe if I have time later, before our time is up, I could show it, to explain why the models of war duration have the war of attrition model, which is our basic model of why wars can, obviously it has efficient model, there are also efficient equilibria where one side just surrenders right now, avoids the cost of war. The problem is each one is willing to keep fighting because they're afraid that if they said anything other, that they would be viewed as losers and suffer a worse peace. But the models of war, the war of attrition has bad comparative statics. Nobody can take it seriously because if you increase the cost of conflict for one side, the other side has to increase its probability of conceding in order to keep the side that has higher cost of conflict willing to keep fighting. That's nonsense. If suddenly it becomes more costly for the Russians to keep fighting, that doesn't increase the probability of the Ukrainians conceding in the next week. So what's going on here? The answer is the model is too stark. If you just acknowledge that one of the things that wars have are battles, battles are like, we call them sunspots in general economic models, publicly observed random variables. And if you put into an interpretation that there is a small positive probability that the next battle will be interpreted as a decisive victory for your side, and that the other side will then focus on the equilibrium where they surrender and are expected to surrender, and therefore they might as well surrender now rather than fighting and surrendering next period, then with that, you can get the right comparative statics. And so I've tried to lay that out, and I hope that game theorists who study war duration will use models where the battles are recognized as sunspots as they truly are, and then we can have models of war duration that we can be proud of. I'll stop there. Abraham, the floor is yours. Abraham, do you hear me? Abraham, if you have slides, let us know.
We can't see it.
Abraham, you're on. Okay.
Okay, I see. Okay, let me try to share.
I think you're on, Maryland.
Yes. Can you see my slides?
No.
No.
No. I was emailing the slides to the organizers, so maybe they could start with the first slide. How do I do it here on my computer?
You have to do share.
I do share.
Press on share at the bottom.
Oh, yes, okay.
Not connected to them.
Can you see it now?
Yeah.
Okay.
Yes.
Okay.
Okay. Yeah.
So we heard two giants on the topic of game theory usefulness for real-life world conflict. And I couldn't hear exactly Roger what he's talking. I could hear Bob Aumann. So I would assume that Roger was trying to identify specific features of war and peace by some game theoretic models. And if you try to identify a specific feature, it is very advantageous to have the most simple model that explains it. And Bob was talking about general principles that game theory are teaching us. Few such general principles. I am a theorist, so what I am going to present is my angle on those conflicts and mediations, my view, which are stemming from work that I am currently doing or that I have done in the relative past. And The umbrella model that I always have in mind for analyzing conflict is stochastic games with asymmetric information, either discrete time or continuous time. The strategic situations and the players' informations evolve over time. The evolution of the state, by the way, the first thing, as is in war and in any other conflict, the evolution of the state is affected by the agent's actions and also by exogenous shocks and randomization. Players may differ in information, beliefs, objective, and assessment of the outcome. The relevant players are often government, coalitions, organizations, or other collectives, and the fact that they are collectives puts sometimes in some doubt our pure equilibrium analysis in games. I will mention a few theoretical themes from my past and current work that may be relevant to such situations. And here are the three themes that I want to mention. One is the sunk cost principle. The intuition that past costs should be ignored after the current state incorporates their strategic consequences, information, beliefs, reputation, credibility, domestic constraint, and focal equilibrium selections may be misleading. And I'll be giving a talk on this topic later this week in the conference. The second one is robust optimization in stochastic games. Strategic recommendation should not depend too delicately on the evaluations of future payoffs, either horizon or the discounting or other impatient valuation criteria. We usually work in game theory with the finite horizon or discounting, but there are other impatient valuation criteria that we should consider, and no on a small model change. This matters especially when the players are collective decision makers. And if we think on wars and peace, it's usually the decision and the preferences of each agent is basically the preferences of a collective. And these things should be taken into account. The third theme is the study that Kohlberg and myself carried on cooperative strategic games. And this question asks how cooperative outcomes are derived from an underlying strategic game. Feasible threats are coalitional. It means the threat on Iran could be by Oman and Afghanistan and the US and Israel. So it's coalitional. And every coalition may have strategic threats where the effectiveness of a coalition threat depends on the relative magnitude of the injury it would inflict on its opponent and on the coalition itself. And these variable threats affect the bargaining out. Now, in terms of, if you look on the umbrella of this type of topics, and you look, for instance, on robust optimization in stochastic games, you realize that there is a difference between equilibrium or extensive form correlated equilibrium. And in extensive form correlated equilibrium, you could think of a mediator. But in the cases that we have in war and peace, it is very difficult to find a mediator. I think that Roger would suggest to build some world committee that will be the mediator in war and peace. But in order to be such a mediator, they should basically jump between the two sides and transfer information from partial information from one to the other. But this is impossible. Where would we find, what kind of objective mediator could you find now for the US-Iran war? So looking at those studies, I don't have a solution to war. I don't have how to suggest to prevent them. You know, some principles are clear, but it's very difficult to say exactly what to do because of all these type of uncertainties. I must say that here we are speaking in a game theory conference, and I have some experience with consulting to some decision makers in various forms. And sometimes I'm telling them the basic ingredients of the game theory that we are considering. And in our community, it will be seen as a trivial advice. Just consider it. It is obvious to consider it, but they are very surprised and very happy with this advice. They don't game strategic game theory, and they should think so. Okay, and I think that we are almost over time. I'll open it now to the general discussion.
Bob, okay, thank you. Bob, is there something quick you want to say? I could make some quick responses to Abraham.
Could you hear me?
Can you hear me, Abraham?
Yeah, I can hear you.
Great.
So I say that
I'm
we are
not
over
sure that
time.
Roger
Let
can
us
hear
leave
it.
it now for the question for the audience or for the other participants in the roundtable.
I would like to speak if I can. And
Roger, we cannot hear you.
I am very sorry that apparently the organizers have not tied my microphone into the Zoom call. My remarks can be heard in the hall. I wish that the organizers would find a way to put this into the Zoom call, because evidently Bob and Abraham can hear each other. Let me just say on the sunk cost principle, this is something that economists understand and game theorists need to disabuse them of. The precise reason why the sunk cost principle does not apply is because when there's a history, I paid this cost in the past, and you want to make an agreement that we just ignore the fact that I've paid this huge cost. If I agreed to that now, we would go into a focal equilibrium in the future where everyone looks at me as a loser and figures that they can cheat me of everything. So it is precisely to avoid the inability to defend one's own property that when property rights are in question, as they are in mortal conflict, that's when the sunk cost principle does not apply. Because people need to get compensation for their sunk costs, lest they be denied the credible ability to defend property in the future. On robust optimization, I want to note that the models of the repeated games with small probabilities of errors found that actually the most robust models were the nice ones, the ones where the threats are minimal, because if you make violent threats that are too strong, then you deter the other side from threatening when they're not sure whether they've really seen a provocation or just a measurement error. I think the most important thing you said, Abraham, is that feasible threats are coalitional. If you will read the United States Defense Strategy report from last October, it is based on a well, I think extremely misleading, ill-founded theory of an extreme Westphalian theory that every nation has to be on its own, and the reputation for responsible leadership of coalitions is not power. The truth is, big nations are powerful because they have internal coalitions, because they've organized a set of trust within a large group of people in the big nation. And that same principle doesn't stop at what we recognize borders. It's all social phenomena. And yes, it is vitally important to recognize that it's building broader networks of trust in your leadership that makes for power. And responsible leadership requires a reputation for not turning around and trying to take an Arctic island from a country that's put its people at risk for the defense of your nation in a mission against Afghanistan, for example. And finally, it is hard to find a mediator. One of the best examples, in 1916, Woodrow Wilson offered to mediate between the Central Powers and the Allies in World War I. And everybody who recognized that to put Woodrow Wilson in as the mediator between Germany and Britain and France was to give the United States a position of power, because of course mediation in real life is power, and that's why international conflict, we should not start with an assumption that there is a trustworthy mediator, that to do so would be to miss the point. It is true that for some small wars between two countries that happen to be within one larger hegemon's sphere of influence, then the hegemon often comes in and indeed mediates and can settle those disputes, help to settle those disputes. But I agree 100% that the models of mediation that I studied early on were models which involves putting a lot of power in the hands of a mediator, and that the assumption of such a mediator should not be made lightly, and certainly cannot be made in a conflict that involves the most powerful people in the nations in the world in a struggle for global mastery. With that, I think we must turn it over. Thank you to my colleagues. You can't hear me, I know, but we appreciate it. I've tried to thank you, and we're done. Oh, yeah. Pradeep, I think this is yours. I'll take my things off. Pradeep, Dubey, the floor is yours. I don't understand why they couldn't hear. It wasn't just Bob, neither. They couldn't hear a word I said.
מרלה, אתה שומע אותי?
אני שומע, כן. אני חושב שעכשיו מתחיל מיני קורס, שאנחנו גמרנו את הסשן.
מה? גמרנו, כן?
אני חושב שכן, כן, כי אני רואה את ברנרד שהוא נותן מיני קורס אחרינו.
אוקיי, בסדר. אז בואו, אז להתראות.
להתראות ונסיעה טובה.
תודה רבה.
שינית את מסלול הטיסה או אתה עדיין כרגיל?
מה?
אתה עדיין דרך ליסבון או שינית משהו?
אני נוסע דרך ליסבון, ועקב הדברים שלך אתמול, אני שיניתי את התוכנית לחזור מליסבון, ואני חוזר דרך פריז.
אוקיי, יפה.
עקב הדברים שלך.
לא.
אני חוזר דרך פריז. אוקיי. תודה רבה על
ההערה. לא דבר ונסיעה טובה, נסיעה טובה.
תודה רבה.
Okay. So, should I just start or what? I mean, isn't that the current program saying? So where is my? So where is my stuff? This work Stengel. It was the von Stengel folder yesterday on this.
Oh, it should be. Did we copy the folder? Oh, we did copy yesterday.
Yes.
Oh, no, we
come on, do it in our menu. There's a folder. Take the entire folder.
Okay.
Von Stengel.
Sure.
The entire folder.
No problem.
So is it now? Is it? I mean, am I talking now? I mean, according to the board.
E2 teste, E.
I mean, there are many choices, you see, 4 of them. When you pull this down, there's
No.
I mean, there are many choices, you see.
Inject. E2 teste, A. E2 teste, A. Injetando. Som 2, teste A2, ei. Som 2, teste A2, ei. Ok. Não.
So it would have worked with that one?
Aqui, fala com ele já. Você quer que eu teste outro também aqui, Edu? Pode testar.
Teste rei, teste som.
Colocar para testar, pode falar.
Você colocou já? Não.
Já?
Teste som, teste.
Colocar para testar, pode falar.
Não. Você colocou já? Não.
Já?
Teste som, teste.
Entendeu? Não sei porquê, lá não estaria. Ok? Qual que é a apresentação dele?
Mas ele vai marcar já.
Okay, I can deal with this. Yeah, thank you. Is this important, my recording or not?
No, actually it's recorded.
Yeah, it's. But now we don't use Zoom anyhow, correct? We don't use Zoom.
No, you can. Oh.
It's just for my presentation. I need the microphone. It works, right? Yeah?
Yeah, it does work.
Okay, good. I just need to find my. Yeah, I'm standing in front of the microphone, so that's. Yeah.
I wanted to know if do you want time warnings or?
I mean, when am I meant to stop? I mean, now I have.
You can take the full time I was supposed to begin.
It's 50, 70 minutes normally, right?
Yeah.
Yeah. So 1:15. If I start now, I'm not sure whether I start now.
Yeah, I can introduce you.
Yeah, or yeah. Why not? Let's do that. Okay. But then the students, the students should come in, right?
The students are mostly divided between the two.
It's just with the big semester. Anyhow, that's good. Yeah.
Hi everyone. We're about to begin. Just so you know, this event is being broadcast live and recorded on YouTube. So by remaining in this venue, participants acknowledge and agree to the capture and use of their image and voice in the broadcast and recording of this event, okay? So I'm pleased to announce Professor Bernhard von Stengel from the London School of Economics for our mini course.
So thank you for joining me. I mean, I mostly see the more senior people here rather than the students, but so let me recall what we did yesterday. We started with, the main problem is to find Nash equilibria of a two-player game. And the main story that I present is in the two-player case, because that has a very nice linear structure, which is represented by these polytopes. And the basis that we're looking at is a two-player game with two matrices A and B for payoffs to player 1 and 2, in red for player 1, blue for player 2, M rows and columns. And you might recall that we, introduce here inequalities. So for saying
for instance, this is essentially the upper envelope of payoffs to the other player. So if you have y1 and y2 as strategy probabilities for player 2, you get these expected payoffs for these rows, 0, 6, 2, 5, 3, 3. You get an upper bound. I mean, u has to be greater than or equal to these expected values. And we know that when these inequalities are tight, meaning hold as equations, they represent best response payoffs here. So for instance, 1 and 2 here are equal, and then they can be played in equilibrium and they therefore have these labels. So remember, the main story was that the numbers the labels represent pure strategies, which in equilibrium have to have probability 0 or be best responses. That's why I have to be present. And we can convert this to a polytope by, I was a bit rushed yesterday, but what's the idea? We divide each inequality here, for instance, on the right by u. So if u is positive, that will not change the inequality. So we have new variables, which I call, say, for instance, y1 is equal to y1 bar divided by u. And this ratio of it's essentially when u is positive, a bit bigger than 1, it shortens y, but the ratio between yj and u is the same as the ratio between yj bar and u is the same as the ratio between yj and 1. So that means essentially the polyhedron is projected into this line where the height of the payoffs is now equal to 1. In other words, I've normalized the payoff to 1. I lose one variable. The dimension of the problem is reduced by 1 because I don't need the u anymore. And at the same time, I sacrifice the equation that the probabilities sum up to 1. They're just being renormalized. So this gives us this nice representation of a polytope, which is just a bounded polyhedron, meaning it is defined by inequalities, but it's bounded because we assume A and B are positive just to get the positive payoffs. Not a big restriction. And now we have what we call complementarity, which means these first m inequalities, let's say xi is greater than or equal to 0 for each I is equal to 1 up to m, or one of the two inequalities has to be tied to get an equilibrium. Either xi is 0 or the corresponding payoff in row I is equal to 1. So the complementarity, also introduced here by this orthogonality, means that we have an equilibrium. So to repeat, the equilibrium problem is just a problem about labeled polytopes. Labeling means a tight inequality gets the corresponding label. So that's what we're looking at. And I also said briefly, a good way of looking at these paths is to think of them as a single polytope, which is the product of P and Q, by introducing a set of all inequalities for k, which is m plus n variables, which are just these probabilities or the corresponding slacks. And then I have a single expression that says z greater than or equal to 0 is orthogonal to c times z is less than or equal to 1. So these are the orthogonality means one of the labels has to be present. So I show this just for a little example because I will use it again a little bit later in 3 dimensions. And then I have 3 inequalities. The blue ones are the negativities. The c set less than or equal to 1 is the inequalities for a certain matrix. And now the algorithm that we looked at, the Lamke-Hausen algorithm, was meaning we drop one label. So in this case, we have 3 labels. We have the origin with labels 1, 2, 3, which are all 0. If I drop label 1, I only have labels 2 and 3, and that defines a set of edges between these, which defines this path. So 2 and 3 are here, and then they connect this thing to the equilibrium that I actually find. So now what I want to do is I want to show you how this is algebraically implemented. A good way of introducing this is called pivoting. Often this is done with tableaus and so on. You might know it from the simplex algorithm for linear programming. It's very, very similar, except that we don't have an objective function that we maximize or minimize, but we have instead this complementarity rule, which says if a leaving variable has a certain subscript, the next entering variable has the same subscript. That's exactly this changing the facet when we take the next edge. So here's a way of writing that down. We have this orthogonality condition, and now we introduce a slack variable s, a vector of slack variables that says instead of saying c z is less than or equal to 1, I say s is non-negative and c z, I'm saying z, that outs me as living in Britain rather than z. Okay, z, cz plus s is equal to 1, that's the same thing. And orthogonality simply means that either Zi or Si is equal to 0. Okay, so that's what we need. And now almost complementary means that we can sacrifice one label where this equation does not hold. So when Z is 0, we have it. So we traverse, these almost complementary edges, meaning all complementarity conditions hold except for L. And if it does hold for L, we have an equilibrium. So we start with Z is equal to 0, S is equal, the slack is the all one vector minus the expectation, so it's initially all equal to 1. And here this is the example for the specific, in fact it's a symmetric game if you wish. We're looking at equilibrium of a symmetric equilibrium of symmetric games. So we have what is called a starting dictionary, which is a representation of these equations in equivalent forms. So when you do row operations of linear systems, you essentially rewrite the system in an equivalent form. What is the form? You have a certain set of variables that are called basic. They're on the left-hand side. They depend on the non-basic variables on the right. And now we change that system. So here's in our example how the system looks like. S1, S2, S3 are given by 1 minus 3 times Z2 and so on here. So this is just the matrix C applied to the system. And now I start, what does pivoting mean? I maintain these equations by increasing and looking at the dependency. So if I increase Z1 here, you see that S1 doesn't change, but S2 and S3 do change. And if Z1 has reached the value 1/3, S3 becomes 0. So that's the point. That's what is called the leaving variable. And now I'll just rewrite this system in terms of Z1. So I bring it on the left. I just substitute it then. So I write here, Z1 is, divide everything by 1/3. And I get a new system, which is simply obtained by changing this equation here, such that Z1 is on the left-hand side, and then using the corresponding expression for Z1 and substitute it into here. And then I get a new system where the basic variables are now S1, S2, and Z1. Sorry. It's the same system. This is very important. It maintains everything we know about the system without, but there's a corresponding solution, which is when the corresponding variables on the right are all 0. So this is exactly the pivoting step that I had here. So the new solution is when all these other variables are 0. What does it mean? They are tight. There's Holder's equalities, and they define these facets of the polytope. Okay? And now what is so this is just rewriting the system. And when I now, and it can be done by algebraic manipulations. And if I now, what do I do? Well, the rule was we had left S3 was leaving the basis. So this is the duplicate label in our picture, because now you see that 3 is appearing here twice. That is S3 is equal to 0, and this is Z3 is equal to 0. They're both on the right-hand side. And instead of now, if I would increase Z3, I would just go backwards, but now I'm increasing Z3, which is just the change of the entering variable. So now I increase Z3, and you see what happens. It's very easy to see what happens, because the only thing that depends on Z3 is S2. So once Z3 has become the value 1/6, you see that this becomes 0, and so we have a new system, and then we just rewrite this one equation, and that's all. And that is the new system that I have here. This is the next step. So in this way we go on. Now the next entering variable is what? Well, S2 has left the basis. So now Z2 is increasing here. And you see that what is happening here when Z3 has reached the value 1/6, Z3 will be leaving again, which is, we hit this equation there, and so on. So it's just an algebraic manipulation. It's very easy to implement in any dimension. You don't need to draw any picture. It's done automatically, and this is the way the algorithm progresses. It's a bit, we could go through the details here, but this is the idea. You just rewrite this algebraic system. And that's how it is. Once the variable that has left the basis has all indices as Z1, here 1, 2, 3, we have the final solution 1/6, 1/3, 1/2. And you see that the decision variables, which are the probabilities, are just Z1 and Z2, which then get normalized because they sum up to 1/2. You have to multiply them by 2 to get the probabilities that represent this equilibrium. Okay, so there is a straightforward implementation. Now, one interesting feature, but I think I skip it for time, is if you have an arbitrary polytope, maybe I say it briefly. The main story about Equilibria in two-player games is that this is a labeled polytope problem. What do I mean by that? I have a polytope which is defined by certain inequalities. They all have labels. I look for completely labeled vertices, which are ones where exactly dimension many equations hold tightly, that have all the labels. And I walk along this polytope by, dropping the duplicate label that I find until I find the missing label. This is it. In fact, it's even sufficient to have a single polytope with that property, which I can then convert to a game. I will say a little bit about this in my research talk this afternoon, where we use this, exploit this fact. So we can have, this is what this is about. An arbitrary polytope here, I've flattened it. It has a bunch of labels, and I actually can turn that into a proper game such that the equilibria of this game are exactly the completely labeled points, except for the completely mixed one, which is the artificial, the all zero one, which is the artificial equilibrium. So there is a nice way of polytopes and games. This is it. Mathematically, this is the structure that we're looking at. So we can talk a lot about interpretation, economic, and so on, but mathematically, labeled polytopes are the story about Nash equilibria in two-player games. Okay, let me skip that because it takes a bit more time. So I want to also mention that we have degenerate games where the rule, what is the next leaving variable, is not unique. We can achieve that. Let me explain how that works. Here's an example, just a little example what could happen. Suppose I have here a little system and I let Z2 be the entering variable. Now you see, meaning I increase it until one of the variables on the left-hand side that depend on this become 0. And you see, once I have reached the level 1/3, both of these variables become 0. So when I do that, I have to decide which variable to drop, which is not unique. And that could set up the, upset the algorithm. So what do I do? And this is a standard technique that you might know from linear programming if you have some familiarity with it. It's called lexicographic degenerate resolution. And now I will explain it in general terms because then it's indeed easier to understand. We have a linear system AX equal to B, X non-negative. Now the A is not our matrix A, it's a general system. And this is generally converted to a problem of finding basic solutions by taking certain basic columns of A, meaning linearly independent ones, that defined by a certain subscript, a subset of the columns. And let's call the other one the set N, the non-basic ones. So I rewrite the system as AB times XB plus AN times XN is equal to B. It's the same system as before, just I've sorted the basic variables to the front into the system AB, XB. And then the way when we do these algebraic manipulations is, it's written in this form. What is actually happening, I say these are the basic variables depending on the right-hand side B minus the non-basic ones. And now they are multiplied actually with the inverse of the basis matrix. So that I see here the basic variables are inverse of the basis matrix times the right-hand side minus this system here, which has the non-basic variables. This is exactly the dictionary that I showed you in an example before, okay? This is an equivalent system to the previous one, where the basic variables are the dependent ones on the non-basic ones. And if I set the non-basic ones to 0, I get the so-called basic solution with it. And if that is non-negative, it's called a feasible solution, which is the thing that we are iterating through. We try to maintain these basic feasible solutions. This is standard fare, for example, in the simplex algorithm for linear programming. So, and now comes the trick. The problem is, in certain cases, when you increase a non-basic variable, it could happen that more than one basis variable becomes 0, and then it's not unique which one should leave the basis. So we do this by perturbing the right-hand side B by adding a vector, I call it epsilon star, which is Now, the vector epsilon star is actually without the first component, epsilon, epsilon square, and up to epsilon m in each row. So I add epsilon, epsilon square, epsilon, and so on to B, and you'll see shortly what that means. So in other words, I multiply an extended matrix where B, followed by the identity matrix, is multiplied by this vector of all epsilons. The first column, 1, is actually the coefficient of B, right? That means simply it's B. That's this, I mean, if this epsilon was 0, it would just this. But if epsilon is positive, I mean, I have here the identity matrix, which is added to this. Why am I doing this? So this is just adding the perturbance to B. So that's what I'm doing here. And now that simply means that you look at this system here, because this is the original column of the right-hand side, followed by the inverse of the basis matrix. So that nothing else has changed. Now, non-degeneracy means that, so I can prove, and I'll show you briefly why, that if I make epsilon positive and small enough, this right-hand side will never have a 0 entry. Never. Why? Because, let's look at an example here. So suppose the inverse of the basis matrix has these entries. And what I want to claim is that this thing is always positive. And how can I identify this? This is the question. Well, suppose there is a 0 entry in the first column, which is all that matters. If the first column is non-zero, positive strictly, I don't have degeneracy. Degeneracy means that some basic variables are value 0. Now, the first coefficient that you encounter, which is non-zero, should be positive in each row. Why? Because when you then multiply it with this vector epsilon, you realize that this epsilon here dominates clearly anything that comes behind it, if epsilon is small enough. Even it's minus 100 times epsilon square, because epsilon square is a magnitude smaller than epsilon, because it's multiplied by epsilon, even if this is a very large negative coefficient. So in other words, to guarantee that this thing for sufficiently small positive epsilon is positive is the same as saying this system here, this matrix here, is lexicopositive in the following way. It means that in any row, the first non-zero entry is positive. That's it. That's lexicopositivity, and that is maintained. That is then guaranteeing that the right-hand side is always positive. The only case where this could fail is if you had an all-zero row. But you cannot have an all-zero row because this is the inverse of a basis matrix, which cannot have a 0 row because it's regular, right? So this row will never be 0, and you can maintain that property with a suitable test, which is called the lexico-minimum ratio test. I mean, to identify, and you maintain that property throughout. And the beautiful thing is about this is you don't need the epsilon at all. All you need is the inverse of the basis matrix. And even that you don't need to store explicitly, because the original system had here, having an identity matrix in the first place, because these were the slack variables. So in other words, the columns of the slack variables are exactly the columns of the inverse of the basis matrix. So you don't need any extra information. You just need to process your system intelligently, and then you maintain lexicopositivity. And we have actually implemented this, and it works beautifully, and guarantees that you never need to worry about degeneracy. So that's the way to solve this. There is a second aspect to this. It's also an implementation aspect, but it's something that is very much overlooked, or not that well known, because in many software packages you need floating point numbers. They have the problem that, especially since we're dealing with small quantities, that they're sometimes not clear. They introduce rounding errors. And the way to avoid them is to use exact arithmetic, meaning you will compute with actual. Now, the normal thing would be to introduce fractions, which then preserve equality all the time. I mean, everything is precise as soon as you start with integers. And here's a trick which is also not very well known. It's called integer pivoting, has been rediscovered many times, which actually avoids the use of fractions. It's something that goes back to the 19th century. I have not found the original source, allegedly due to Sylvester, but it's a beautiful system that you should also know. I mean, know that it exists, and it's as follows. So the idea is to maintain actually an integer system rather than a fractional system. So to repeat, this is a numerical problem which we have also solved, which is in particular important when you have degenerate systems, and so to be always precise. So how does this work? Here's an example. So very simple example, 2 rows, 4 columns. And what does it mean to have an basis matrix? Is you have some subset which represents essentially the identity matrix, right? I mean, which we have here, for instance, the slack variables. And now we let the Z1 entering the system means that we want to now convert this column to a unit vector. How do we normally do this? Well, we divide this row by 7, and then we multiply 4 times that row from this row, so you get a unit vector here. This, however, introduces divisions. In floating point, they would be bad because they introduce rounding errors. We do something else instead. We multiply the first row with the pivot element, as it's called. So this becomes 28, 21, 7, 0, 7. And now we multiply 4 times that system from the previous system. And then now we get a new basis, which is 7007. And now the 2 basic variables are S1 and S2, and the non-basic ones are Z2 and S2. So what have I done? I have now, the basic solution is Z1 is 1 over 7, and S1 is 3 over 7. You just store the coefficient, the 7 here. Okay, so we just sacrificed a single increase in the size of the system. Now we do the next thing is where S1 as Z2 ends at the basis, so we make this the unit column. Well, the trick is as before, you multiply this row by 13, you get 91, 26, 0, 13, and so on, and now you multiply twice that system from the bottom row in order to get a new system, which is this, 13, 7, minus 4, 3, and then this bottom row. And now the problem with this algorithm, and quotes, is that if you keep multiplying integers with rows, the numbers grow and grow and grow and grow, and they would become very bad indeed. So how do you solve this problem? Now look at the bottom row in this system. Do you see something in that row? Can you see the bottom row? Do you see a common denominator, a common factor? 91, that's not a prime number. So everything there is divisible by 7. I can divide by 7. And I get a new system which has 13, 0, 13, 0 here. And that is the main trick of integer pivoting. You can divide by the previous pivot element without remainder, and it always works. It looks like a miracle because these numbers here are not divisible by 7, right? I mean here, 26, 13, and so on. But after this operation, it does. And that way the system keeps small. And what's the trick behind this? The trick behind is actually you implement Cramer's rule. Not sure I have a slide on this. No, I do. Essentially, this thing, this 13, and in fact the 7 here as well, is the basis, is the determinant of the original basis. So this is 1, 0 is the determinant 1. The new basis here has columns Z1 as 1. So the determinant, if you do it in the right order, 1, 0, 0, 7 has determinant 7. And when you look at the left 2 columns, which are now the basic and the final one, Z2 and Z1 in that order, because that's the order in which it's written down. Well, you can look at the determinant here. It's 8 minus 21, it would be minus 13, but you have to exchange the 2 columns. The 13 is exactly the determinant. So essentially, I have used Cramer's rule, which says look at the determinant of the basis, and then look at the right-hand side, replacing the columns of the respective variables for the values of these variables. And beautifully, you can implement this without ever dividing. I mean, you know the division is always work. You never need fractions. The problem with fractions is when you add 2 numbers, you have to cancel the fraction afterwards, because otherwise it keeps growing and growing and growing. And cancellation requires to identify the common denominator, the common factor in numerator and denominator, which uses for these big integers that you use the Euclidean algorithm. If you would use exact arithmetic with fractions, you would be spending 90% or even more and more and more of your time, depending on the size of the system, by just canceling fractions, entirely avoided by this system. I use it for big games. Well, 200 by 200, there's never a problem with size or with speed. Implementation of multiplying big numbers is now automatic and implemented in, for instance, Python. It works really, really nicely. It's just an implementation detail, but once you know what is going on, you can do very well in solving these problems, knowing, I mean, a little bit of linear algebra. So that was the key point of the end of, I mean, this part about the Lemke-Hausen algorithm. So I will now move on. So, I mean, believe me, this is nice stuff. It's a bit algorithmic and it's linear algebra, but it's really nice. So let's now go to some generalization of this. And it is an extension. You see the name Lemke again. Al Roth told me yesterday that he had a job offer under Lemke's job. It almost went there, but then he went to Illinois instead. So he knew this was his first academic job. But it was, Lemke was in New York, upstate, the Rensselaer Polytechnic Institute in, I think, Troy, New York, upstate New York. Not a very famous university, but that's where he was. So this is about the tracing procedure. And this is a generalization of the Lemke-Hausen method, which is known for so-called linear complementarity problems. And the key idea, this is not a long story, you see 15 slides here, is that you, this is what is also called a homotopy method, which is also similar to what Lemke-Hausen does, which has the feature that it can be implemented in a very similar way to Lemke-Hausen, and then it also has a very nice game theoretic interpretation. So let me start with, I mean, maybe the game theory is more interesting, but let me also describe first the technology behind this. So one way of looking at it is, for instance, at symmetric cost games. So instead of looking at payoffs, we look at costs. So that's easy to do by just make everything negative. And now let's make it, after you've done make all the costs turned into negative numbers, make them positive again by shifting them. So suppose you have a positive matrix M, which you try to minimize. And now I have an unscaled vector Z, which I will scale to become a probability vector. If I then say I try to find a symmetric equilibrium of this symmetric cost game, that's essentially the same as saying I find non-negative Z such that mz is greater than or equal to 1. This is the normalized cost to 1. And being it complementary, meaning in the sense that z times the difference, so mz is greater than or equal to 1, so if I subtract 1, I get a non-negative vector of slacks. And I want to make sure that whenever z is positive, zi is positive, the corresponding slack is 0, or vice versa. I mean, if zi is 0, you can have a positive slack. Why am I using this particular representation? It has the advantage, if you wish, that you don't have a trivial solution when z is 0, which I had when I have payoffs rather than costs, because z equal to 0 is not a solution to this system, you see, because that inequality is not true. So all the solutions here will be actually equilibria. The disadvantage is that I now have again an unbounded system, because obviously z could be arbitrarily large. So we have, when you look at this, this is a big quadrant, and then I have some inequalities cutting off, orthant of the mz. So I have to worry about infinite rays, as they are called. But at least I don't have a trivial solution, z equal to 0. So that's a different way of looking at it. And any game can be phrased in such a way. That's what I said here. It includes that 0 is a solution. And here, this is the problem that I mentioned. So now a linear complementarity problem generalizes from this. It says we have a linear or an affine function. We have a matrix M, a square matrix M. We have another vector Q, which was actually the -1 vector in the previous case, but it's a general vector. And I want to find a variable Z such if the dependent variable of slacks is introduced here as W, I want to make sure that they are orthogonal in the sense that they're complementary, meaning Zi and Wi times the product is 0. One of the components has to be always 0. So that's what is called an LCP. There's a whole literature on this, starting actually with Lemke's work, which has many other applications other than just the games that I just looked at. And there's a whole book on this. A definite reference is Kotelpeng and Stone, The Linear Complementarity Problem. Now, here is the way to solve such a linear complementarity problem, and it has the nice advantage that it will have a game theoretic interpretation, and this is what is called Lemke's algorithm. So before we had Lemke-Hausen, what we're now doing is we're introducing a new degree of freedom into the system, which with Lemke-Hausen was done by dropping one of the complementarity conditions. Here we keep it. We keep Z is orthogonal to Z but we introduce a new column, D. That's the standard notation. By the way, this is one of the features of LCP literatures. Q and M are always there like that. And D is this extra vector, which gets a new variable Z0. And obviously, this is just the same system if Z0 was 0. So the idea is that I can start with something where Z0 is non-zero. And the idea is that I have a D which is positive. I didn't say this. You make it very positive. And if Q has negative components, otherwise W equal to 0, Z is equal to 0 is already solution. We now increase Z0 in such a way that we make it strictly positive. And the smallest value that achieves this, so that becomes what is called the primary array. So we have Q plus D times Z0 greater than or equal to 0. It's a long thing because D is positive, Z0 can be arbitrarily large and would be fulfilled. And there is a point where this is tight. So this is the primary array, and once Z0 is made small enough so that at least one component of W is 0, the others are non-negative, I have a starting and initialization of the system here. Okay, so now Z0 is in the basis, and Wi has become 0, so I can move it to the right-hand side. So essentially what I pivot out, Wi, Z0 is in, and now what do? I have Wi and Zi is 0, so now Zi can increase exactly as before. So we have these complementary variables. One of the two, Wi or Zi, if they're both 0, either of them can be increased. This is like the room in my castle where I have two doors that I can now run around. So again, a very simple algorithm. After this initialization step, I always use the complementary variable of Zi or Wi to make this the new entering variable. Let me show you this on a example. We start with infinity, where Z0 is arbitrarily large, the primary array. At some point, maybe W3 becomes 0. Now I let increase Z3 until some other variable becomes 0, and I keep doing this. So now W1 has become 0, now Z1 increases. Now Z3 becomes 0 again, so I can W3 again, and hopefully this terminates when Z0 is equal to 0, and then I have solved the LCP. That's the whole algorithm. That's what it is. The complementary rule until I found a solution. The main story, and there are hundreds of articles written about Lemke algorithms, is how can I make sure that this happens? Because the problem that could happen is that I can have an infinite entrying variable, like an unbounded undirective function in the simplex variable, and this is what is called a secondary array or array termination. And now there are various conditions about M and Q that guarantee that this doesn't happen. Certain non-negativities, for example, and so on and so on. So now this is the algorithm, a bit boring, but now we do it for LCPs as games, and then there's a very interesting twist here, which is the Harsanyi-Zelton tracing procedure that I will get to. So we have here an LCP. We don't have it in the form that we have costs. So what I will do is I will make A and B negative. And so I rewrite A y less than or equal to 1 times U in the other direction. Now the U has changed sign actually. When A and B are strictly negative now, this is actually a system of positive entries. And now I have a system similar to the LCP I have before. This is just a bit trickery with signs. So this system here on the right is the matrix M. A and B are strictly negative, which means that minus A and minus B are actually positive. And here are the payoff variables, are actually the negatives of the payoff variables. This is my system here. And now I have here a MZ greater than or equal to minus Q. So Q is actually have negative components here. So we don't have a solution yet. And so this is the Q that we have here. This is the equivalent to saying Z greater than or equal to 0 is orthogonal to Q plus MZ greater than or equal to 0. So this is a system derived from the game. It's not complicated. We can follow the details, but essentially LCP as a bimatrix, a bimatrix equilibrium problem as a linear complementarity problem. Was there a question? No. Yes. No, they're payoff variables, not multipliers yet. No, sorry. Now comes the linear tracing procedure. And the goal of the whole thing is this can be cast as a special case of Lemke's algorithm. That's the thing we are after. But the nice thing is that we are, let me check, yeah, I did this. Okay, so what is the tracing procedure? This is one of Harsani and Selten's, or Harshani, I don't pronounce him correctly, ideas of solving the equilibrium selection problem. What is the tracing procedure? The idea is that you start with a prior conception of what you think the other players will do. In the case of complete ignorance, maybe a uniform mixed strategy about the pure strategies of the other player, which is of course sensitive to how you describe the game, etc., etc. But anyhow, let's assume we have a prior of what you think the other players will do. Let's call it X bar, Y bar. Okay, now the tracing procedure traces equilibria of a new derived game, of a, in a sense, parameterized game. It's parameterized with a parameter tau, which we call a homotopy parameter, in the following way, that we say we play actually originally against the prior only. This is the start of our, that's why it's a prior. We choose the best response against the prior. Generically, this will be actually a pure strategy on each side. And now we start moving into this best response against the prior. What does moving mean? It means we assign now some positive probability to the actual strategies that are being played. So tau is the probability of the prior. 1 minus tau is the probability of the actual strategy. So the best responses are, say, x hat and y hat. So I now actually play a game where x hat, y hat is a best response to this convex combination, this mixture of my actual strategies and the prior. Again, to repeat, if tau is 1, you don't react to anything other than the prior. If tau is 0, however, you will have solved the game, because now you're applying to yourself only. So the idea is that we follow, we change this tau, and then we change in specific ways the reactions. At certain points, certain things will happen until eventually tau becomes 0. And this actually even selects an equilibrium as a function of the prior. So that's the tracing procedure. It has twists. For example, it might happen that you have to make intermittent increases of the prior probability. It's not monotonic, this parameter, in general. And it's one of the main complications in the complexity of this algorithm. But in general, you can follow this path until you find an equilibrium. Let me illustrate. So you could also say, instead of playing an equilibrium against this convex combination, you have a restricted game where you stipulate that the prior is at least played with minimum probability tau. So in other words, the lower bound for each pure strategy is, and being played, is tau times what it is in the prior. Okay, so that's a way of putting it. So here is a little example for a 2x2 game to illustrate the tracing procedure. And I've used almost the coordination game, 1-1, but to make it a little non-symmetric, I put a 1-2 in the first column, in the first payoff to the column player. So we have these two pure equilibria that we know, and top left, bottom right, and so on. I mean, this is the square that we're looking at. By the way, I mean, you might have noticed that I put lower left and upper right the payoffs. I do this, for instance, in order to illustrate, this is the unique way of identifying where the equilibria, where the payoffs belong to. Schelling put them exactly in these corners, Selten put them in the wrong corners, because you would see the symmetry of the game immediately by reflecting it. When you look at, for instance, the prisoner's dilemma, you have the diagonal that also flips the payoffs at the same time. So that's why lower left and upper right. Anyhow, we also want to have the corners of the square, which is now the mixed strategy space, corresponding to the corners of the payoff table, the 2x2 table. So top left, top right, bottom left, bottom right are the pure strategy corners of this 2x2 game. Okay, now, what have I done here in this diagram? I have indicated the best responses as a function of where you are. You see that if the probability for playing right is exactly a half, the row player is indifferent because his payoff matrix is 1, 0, 0, 1. Okay? As soon as the probability for being right, as soon as you're on the right of the vertical line, B is the best response. On the left of the line, T is the best response. When you go down, because the payoff to left is higher than for bottom, you need to be 2/3 all the way to the bottom to be indifferent. So above the line, left is the best response. Below the line, right is the best response. On the line itself, you're indifferent. You have a mixed equilibrium here. So now what is the tracing procedure indicating? It tells you, no matter, depending what that prior is, where you start, you move in the direction of this pair of top left, top right. I've indicated with the arrows where you're going. So let's assume the prior is here. Well, the best response to the prior is already top left. You went straight for the equilibrium here. Very easy. Okay. Similarly, if you would start in this bottom right rectangle. So the interesting cases are where you're not in an equilibrium best response. So here's what is happening. Suppose we start here. The best response here is to go bottom because we play the row with, say, whatever it is here, 1/3. And we go left because, is that right? No, we go to bottom because the right strategy is played with 2/3. And we go bottom. What am I doing? I said bottom left. Why bottom left? Because we are playing too far to the right, so bottom is the best response, and we are above the 2/3 line, that's why we're going left. So bottom left is where we go, but we cannot go straight all the way because that's not an equilibrium. So what is happening is this little square here indicates the probability that I allow myself the freedom to use my strategies rather than just the prior. When the prior probability is 1, it's just this point, but the less the prior has to be played, the bigger this little square can become. It goes, the corners of the little square go along these dashed lines. And now at bottom left is always the best response pair for a while until you hit this line. This is the interesting part. At this point, we find a second best response, namely top. And now what happens is that top becomes also a best response. And now we increase top as the new best response. And we walk along, this is a degenerate game in this step. So top is becoming, we walk along this thing. Top is now also played, but at this corner here, sorry, what am I doing? At this corner here, left is no longer given positive probability. And so bottom is no longer given positive probability. And hence I'm now free to go away from the indifference line between top and bottom. And then I move here. So this is the trace that is computed from this line. And it will actually select the top left equilibrium from this prior. Okay? Not necessarily everything in that corner does it. For instance, if I go here, we again go to bottom left, but here the right strategy becomes the first one. So I start increasing right and I select this one here. So they're different basis of attractions. They're easy to compute, but they're not the same as, say, from a replicator dynamic or something. But it's a very nice way of so looking at this. And it is not a dynamics. I mean, the dynamics would be here. I mean, it's an algorithmic procedure. It's the tracing procedure. Okay, and what's the upshot of this? Is that it can be implemented with Lemke. So that's what this is about. So I take a prior x bar, y bar. I multiply it with my, because A and B are chosen negatively, with my payoff matrices. And this is now a positive vector because A and B are strictly negative. And I add this, and when I do that, the tau, the probability for the prior is exactly that Z0, which is the extra variable in Lemke's algorithm. And when you do this, you might believe me by seeing how this complementarity pivoting worked. That's exactly Lemke's algorithm. So in other words, I have here now a version of Lemke's algorithm that has a game theoretic interpretation. Okay? So the cool thing is I can use this. And now I have actually a lot more choice of starting points, not just the pure strategies as in Lemke-Hausen, which are certain corners of the simplex, but anywhere in the simplex of the two strategies, I can start and let my algorithm run. And actually, that's what we are doing to find equilibria. In particular, when you look at equilibria in large games, say 100 by 100, and that's not huge, but it's still larger than being able to check all possibilities, which would be vertices of a polytope, which are huge in numbers. They're exponential. In 2 to the 100 is too large. But with thing, we can start random starting points. I choose random x bars and y bars, and I compute, and I find this equilibrium in a few hundred. I mean, the pivoting steps are proportional to the dimension of the game. So you might have heard of people claiming that finding Nash equilibria is hard. When I do this particular algorithm with random starting points, which by the way also is a selection method. If one equilibrium is found all the time, that's a good way of saying this is a very likely equilibrium to be played. Because for many, many starting vectors, that's where this tracing procedure lead. Yes? Yeah, I mean, so what Hassani and Selten propose, they start from the uniform prior, and in the, say, the coordination game, for instance, the 2x2 game, let's say stack hand or something, if the tracing procedure finds the risk dominant equilibrium. So that's one way. When you start from the uniform prior, I generalize this. I take many random priors, and I would say the one that is more likely to be found is also more likely that people find when they start thinking about the game. I mean, it's a selection criterion, but I would suggest it's not a bad one. I mean, it's not, I mean, the tracing procedure has this foundation. If many starting points lead to it, it might be the equilibrium that you should choose. So, and by the way, because we are always moving inside the strategy space, because of this interpretation, I don't even have to worry about rate termination, because the entire interpretation is always that I'm moving inside the pure strategy spaces. I mean, it's the two simplices, so I don't even need to worry about any mathematical condition about why this thing terminates. By the way, I can also emulate the Lemke-Hausen algorithm by choosing a different covering vector, namely the all one vector except for the missing label, which gets a 0. You can prove this is a non-trivial observation. It's not deep, but I mean, you can even emulate Lemke-Hausen with that. And that's how I'm doing actually it. I mean, we have a software for this. So let me say one more thing, because this is our favorite method now for solving large two-player games. How would you generate a random probability vector in say the simplex, the triangle? How would you generate a random point in a triangle? There is a naive way of doing it. You pick 3 random numbers and you normalize them. And that's not a good way of doing that. If you do it, you get the picture on the right, and it's even worse in higher dimensions. If you want uniformity, you need to think a little bit differently. I mean, a trick is to take a bunch of random numbers and take their logarithms and then renormalize. Then that would work. That would generate the thing on the left. But anyhow, that's what we're using to avoid this naively generated distribution. So, and I also want to, it's again a little implementation detail. Remember that I did integer pivoting, where we have numbers, integers. Now, when you compute an expected payoff like a times y bar and x times x bar, if you take a random number, x bar, y bar, you get a very ugly fraction. And that means that when you renormalize that to be an integer, because you just scale the column, you get a very big entry of integers, which slows down your thing. You don't need to do that. Because it's random probabilities, right? Why don't we round them, say, to multiples of 10,000? That means we get only 4-digit integers. And that's actually not again, to generate them, this is like a voting problem when you have, you know, in the US. So here's the other problem. So that's what I'm doing, is I round it to the next integer. Fraction as a multiple of 1 over 10,000. It's like assigning seats in a parliament with 10,000 people. Not a big problem. I mean, you don't need to worry about the Hond or whatever, but you want to make sure that the numbers sum up to 10,000. And you get this distribution, which I do by a variation of, I mean, anyhow, it's just a little interesting side effect that you can also apply the problem of rounding fractions, I mean, random fractions to fractions of a given denominator. Here's a way of illustrating that with actually a very large denominator, 20. I mean, a small one. I mean, everything is a multiple of 5%. Okay, so let me look at just what I mentioned. I mean, I can and I will have, I better cut this short because people want to go to lunch and don't start a new session. you can find all equilibria of a game, which is essentially similar to what I showed yesterday by looking at the vertices of this polytope and try which of them fulfill the complementarity condition. This needs a lot of vertices to check. For instance, if you have a cube in dimension 10, you have 2 to the 10 corners of a cube. That's a very simple polytope. If you have 20, you have 1,000,000 corners. If you have 30, you have 1,000,000,000. If you have 40, you have whatever it is, 1,000 billion. This thing grows exponentially. So if the game is 30 by 30, you have about reached the limit of what you can check. So 100 by 100 is completely out of the question. You cannot find all equilibria, apart from the fact that you don't even know which one to select. So instead, we use this one, Lemke's algorithm, and it is fast in practice. Despite of people moaning that this is not true, it is really fast in practice. And they can also be used to find these likely selected equilibria with the nice game theoretic interpretation of choosing this covering vector. It's not just a trick, it also has an implementation as the tracing procedure. Something quite interesting, the equilibria that you find are having what is called positive index, something I will mention in my next lecture. To give an example, in the coordination game, say the Battle of the Sexes or the 2x2 coordination game, the pure equilibrium of index +1, the mixed equilibrium has index -1. The sum of all these indices is always 1. So there, when you find 2 + 1 equilibria, there must be a -1. And you can also take this algorithm. If you find 2 equilibria from 2 different starting points, you can use the starting points. So say this one goes to top left, this one goes to bottom right. If you now use this starting vector for this equilibrium, you run it backwards, it will find the mixed equilibrium. So what you can do is you can now introduce a backwards-forwards method to start exploring a whole network of alternatingly plus index, minus index equilibria, and thereby generate possibly a network of larger, finding more equilibria. For instance, in the game that Bob Wilson had, where Lemke-Hausen finds only 1 equilibrium, with this Lemke algorithm, it will, very quickly find also the other ones, because you have these random starting points. So this is our choice of algorithm for 2-player games, even when they are large. Okay, so I think I stop here in the interest of time. Thank you for your interest. Yes, please.
I have a brief announcement. Some professors and students have been matched and have received emails about that. The students who have not contacted their matched professors to have lunch with, please do it as soon as possible. Those professors who have already their matches, lunch will be on the 4th floor with your expected Agora ele vai mexer aí, a gente vai. Tem uma equipe técnica.
Som teste. Aí. Ei. Teste 2, teste. Ei, A2, teste, teste 2. Teste 2, teste. Ei, A2, teste, teste 2. Esse aqui mantém, né? Que a gente tinha mantido, né? Remoção de ruído, não. Deixou assim, né? Ou esse aqui nós deixamos? Não. Porque aí tinha a opção de cancelamento. Ok. Ei, 2, teste, teste 2. Ei, ou. Olá, tudo bem? Teste YouTube, teste Zoom, tudo bom? Olá, tudo bem? Teste YouTube, teste Zoom, tudo bom? Hello. Hello, everyone. Você desligou o microfone, tudo lá ou não?
Eu falei. Mas eu não sei como é que tá a configuração.
Jonas, está me ouvindo?
Continua falando.
Jonas?
O menino não está aqui.
Então, né? Aí fica difícil testar. Som, teste, teste. 1, 2, 3, teste. Não tem como. Quer dizer, tem, mas peraí. Não, aqui deixa eu... Já tá quase no 100. Então, isso, mas eu tô falando a 7 centímetros do microfone. Ah, peraí, é agora. Melhorou? Teste, 1, 2, 3. Não, realmente tá vindo muito baixo o retorno. E não é o microfone da sala. Peraí. Ô, Mineiro. Peraí. Ô, Mineiro. Aumenta o som do microfone no back, por favor. Aumenta o som do microfone no back, por favor. Não, no OBS. O que foi? E joga pra mim a sala, por favor. Não joga o da praia lá. Nossa, eu tô falando lá. Não, aqui. Joga a câmera troca a câmera pra câmera que pega ali à frente e joga a câmera pra mim, por favor. Tá, a webcam que tá aqui, eu tô injetando a webcam Mas tá, NDI webcam vídeo 1. Meu, eu não sei se ele tá mandando, né? Ó, eu vou confirmar com você como é que tá a configuração aqui, peraí. Ó. Ó. No vídeo 1 aqui, tá escrito FEA-4 1K de cabine, OBS e PGM.
Quando eu falo no microfone, você escuta no alto-falante aí, né? Do auditório.
Eu estou escutando fazer um eco aí.
Ah, não, mas é por causa do celular. Ó.
Pode ser verdade. Eu não tô ouvindo aqui porque o microfone. Peraí. Ô, Inés, você abriu o som? Inés, você abriu o som?
Do auditório, vê se ele abre.
Você abriu o som aqui? Você abriu o som aqui? Tá, não tô ouvindo? Tá,
Som. 1, 2, som. 1, 2. Eu tô falando no microfone.
eu não tô ouvindo aqui não, Marcelinho.
Ih, caramba.
A única coisa que eu escuto aqui é o som do microfone daqui.
O Edu chegou aí? É porque ele tem que ligar o som do computador. Ah, tá. Primeiro fala para ele ligar o som do computador, que eu acho que nem isso que o mineiro fez.
O OBS é esse som aqui, não esse.
Som. 1, 2, testando. 1, 2. Testando. 1, 2, teste. 1, 2, testando. Saiu na caixa? Saiu na caixa aí, Jonas? Saiu na caixa? Ou ainda não? Eita. Oi. E agora?
Marcelino, e agora? Como é que tá o som?
Nossa, tá muito alto.
Melhorou?
Tá bem alto. Espera aí.
Tá me ouvindo bem agora?
Eu tô te ouvindo bem. Agora eu quero saber se a minha voz tá saindo no auditório.
Não adianta você responder aí que não tá saindo aqui na caixa, Marcelinho.
Caramba. Aí eu não sei se é a saída aí.
Não, deixa eu ver se tem alguma coisa ali no
Som. 1, 2. Som. Aqui, ó. Será que é o... Tá no webcam 1 aqui. No NDI 1. Será que eu deixo no 4? O meu microfone? Deixa eu compartilhar aqui a tela, peraí. Não dá para compartilhar. O Jonas? Agora você me ouve aí ou não? Tá me ouvindo? Som. Alô, som.
Deixa eu ver se tem alguma overlay no fundo. Acho que não.
O Edu tá me ouvindo?
Eu tirei o plano de fundo aqui, viu?
Tá. O Edu tá me ouvindo?
Então, pega o valinho lá em cima e vai almoçar. Você e o Walter.
Oi.
Marcelino, fala aí.
Som, 1, 2, som. Ô, Edu.
Tá? Vamos ver um vídeo do YouTube nesse computador.
Som. Que está no seleção do microfone, está no webcam 1, NDI e webcam áudio. Eu acho que é o outro, deve ser outra entrada aqui.
Tá falando no microfone, né, Marcelino?
Tô falando no microfone.
Você tá falando no microfone, teoricamente. Tá falando no microfone, teoricamente.
Opa.
Agora eu tô te ouvindo.
Som, 1, 2.
Agora eu tô te ouvindo.
Tá me ouvindo?
Ok. Abaixa agora da sala, mineiro.
Som, 1, 2.
Agora eu tô...
Testando.
Calma, 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 calma. Não, mineiro, não o meu aqui, fião. Oi. Tá me ouvindo, Marcelino?
Tô te ouvindo.
Ah, agora sim. Então vai falando, né? Se eu tô falando, você vai falando.
Espera aí. Que tá dando um delay aqui, parece. Eu tô ouvindo antes no telefone e depois no Zoom. Parece.
Marcelino, é lógico que você vai ouvir antes no telefone.
O áudio tá no...
Marcelino, tá me ouvindo?
Caramba, tô te ouvindo.
Meu, então você fala, eu tô te ouvindo, tá funcionando.
Você
não deixa
que
a gente
não...
no vazio aqui, não.
Você que não tá me ouvindo, Edu, eu tô respondendo.
Eu tô te ouvindo perfeitamente. Tô te ouvindo perfeitamente.
Não, algum momento você não tá me ouvindo, porque toda vez que você perguntou, eu respondi.
Não, eu tô te ouvindo perfeitamente, igual agora. Tô falando com você. Você tá me ouvindo? Tá me ouvindo, não tá?
E porque quantas vezes você perguntou, você tá me ouvindo? Eu respondi todas. Isso que eu tô te falando.
Agora eu tô te ouvindo. Agora eu tô te ouvindo perfeitamente.
Já que você tá me ouvindo, o que que você clicou para você me ouvir? É isso que eu quero saber.
Eu não cliquei em nada, eu só mudei aqui que tinha que sair no alto-falante da sala. Só isso.
E antes estava em qual?
Antes estava no cabo virtual.
Que está aqui o selecionado o microfone.
Então, perfeito. Eu estou te ouvindo, você está me ouvindo, está funcionando, certo?
Certo.
O som tá bom aí, de volume, tá tudo ok?
Tá, tudo ok. Mandei pro Jonas aí. Ô Jonas, mostra pro Edu a foto como que tá aqui.
Não, aqui tá normal. Eu estou te
Não,
ouvindo, você está me ouvindo, então
eu
está
sei,
funcionando.
só para definir, ó, que a entrada do microfone aqui está no NDI1.
Ah, eu vou deixar tirar uma foto aqui também para mostrar.
É, só para deixar registrado. Deixa eu ver aqui como que aparece aqui. Ah, a mesma coisa.
Então, beleza, Marcelino. Tá. O que é isso aqui?
Som.
Ouça em um dispositivo adicional. Não precisa estar habilitado isso, né? Precisa? Tá ok. Entendeu? Você está me ouvindo perfeito? Está me ouvindo? Está me ouvindo?
Tô te ouvindo normal.
Então tá bom. Então a gente vai encerrar aqui.
Oh, beautiful. It is a great pleasure to introduce my dear friend and great colleague, Ehud Kalai. What a beautiful, who's got the best slides, first of all. And also, I want to say before I turn whatever powers I have, I want to bless the audio-visual system so that it should work through your entire talk. Ehud, take the floor.
Thank you, Roger. This is not the title of the talk. What I did before that, I made one slide. I didn't know who the audience are. So I wrote one slide before that with all the definition of what is a game, what are the equilibrium concepts. So if you miss that, you can go to my slides and find it in the first slide. But the motivation for the discussion I'm going to have is largely what we think of equilibrium. So I can, so what, not much has been changed drastically. When I was a young person coming on game theory, the common thing was Nash equilibrium. It was a newer concept then. Nash invented it. Von Neumann didn't like it very much. He liked dominant strategy equilibrium. So the common perception was that they will play some Nash equilibrium, and if you want better than that, if you want to please von Neumann, try to find a dominant strategy equilibrium. But von Neumann pointed right away that it's a very attractive concept, but it's not good because most games don't have it. So with this in mind, I think that if you go a little further and you look for more sophisticated concept, you can find other concepts. And one of them I'm going to highlight here, and that is nearly dominant strategy equilibrium. And it models a lot of economic examples. The dominant strategy equilibrium does not, because it's too ambitious. But it is useful for many things. And one of the points in the discussion here that to highlight this fact that it can be used and it's very useful in some applications. So I'm going to talk about the lecture title is Nearly Dominant Strategy Equilibrium, Implementations of Such Concept in Prisoners and Other Dilemmas. So I want to take an old problem that most people are familiar with and show it to you why I want to resort to nearly dominant instead of dominant. And in particular, I'm going to rely on resilience analysis in N-person strategic game, identifies more nuanced concepts beyond the standard Nash and dominant strategy equilibrium. And in particularly, as I said, I want to look at nearly dominant strategy equilibrium. It is a strong equilibrium concept, which is very appealing in a similar way to dominant strategy equilibrium. But it has broader applicability to economic issues than dominant strategy equilibrium. And it's almost as resilient as dominant strategy equilibrium. And it is significant all above the other Nash equilibrium, other than these two. And indeed, examples and experiments that were conducted by people show that people tend to play nearly dominant strategy equilibrium over Nash equilibrium. I'll show you the examples. I don't have an existence theorem. But I'll show you many examples that are very natural. You would like to have it. You don't have dominant strategy, but you'll have this. And then another application, inside of application, I want to take it to implementation theory and show you that if you implement things by nearly dominant strategy equilibrium, similar to Pradeep questions, you will find very useful implementation problems that it implements dominant strategy equilibrium does not, and Nash equilibrium is just too broad. And examples I will talk about are pricing games, auctions, participation games, and prisoners' dilemmas. And the use of resilience analysis goes way back. I'm not going to dwell on it here. Jean-Jacques Rousseau and David Hume in the 1700s already talked about resilience to defections from the social contract. This is political science equilibrium, so to speak. And the question was whether citizens will play by it or not, and resilience against defections from such. 200 years later, Thomas Schelling introduced multi-person non-cooperative game theory as a way to deal with economic externalities. And he wanted to show an example where it's useful. So he looked at an equilibrium and studied the resilience of this equilibrium to show that you get the same phenomenon that I'm discussing here. And 30 years later, Kfir Eliaz and 4 computer scientists looked at the same concept. Eliaz called it fault tolerant, what I'm calling resilience here. And the computer scientists already used the word resilience, and they show that implementation is much more effective when you use resilient, highly resilient equilibrium, which is what I'm going to do here. My son, Adam Kalai, and I worked on the notion in general, and we show a general theorem characterizing all equilibria using the notion of resilience. And it ranks all equilibrium and the dual concept of critical mass of equilibrium, and that all equilibria can be ranked this way. So I'm going to use this ranking. So let me give you a preliminary example so to give you right away an idea of what I mean by that. So let's look at a competitive pricing game. So let's say that I have 20 producers and they can each produce this pen for about a fraction of $1. And each one has to decide whether to sell the pen for $1, $2, $3, and so on. So each one will post a price at which I would post a price at which I is willing to produce and sell the pen to a buyer. And the rule is that the buyer will buy 1 unit from a random seller with the lowest possible cost. Okay, so again, I hope the game is clear. And consider the posted price where all 20 producers say we'll sell it for $1. So that's very familiar economic competition price, but a very nice explanation. So I'm going to give you 2 examples of critical mass, which is very low here, and resilience, which is very high for everybody selling for $1, which I think that making everybody selling for $1 very attractive. You cannot find a dominant strategy to say everybody will sell for $1. So let me first look at equilibrium inducement. How much effort does it make to create this equilibrium? And the point is that if any 2 producer post the price $1, then posting for the price of that $1 is optimal for every producer, all the 20, including the original 2 who initiated it. And since this number 2 is the smallest number of players with this property, I would say that the critical mass of sigma is 2. Does that make sense? 2 people can initiate this equilibrium, and not only that, let's look at the defection resistance. How strong is this equilibrium where everybody sells for $1? How resistant is it to defections? So defection resistance, so imagine that we start with 1, 1, 1, 1 that was induced somehow. And I say, if 18 of the 20 change the price to something else, the price 1 will still be optimal for everybody, including the 18 changers. And because 18 is the smallest number with this property, I would say that the resilience of sigma is 18 players. Does that make sense? 18 players cannot, changes by 18 or fewer players are not going to change the best response property. Okay. And the critical mass, you can see from this example very intuitively, the critical mass and the resilience are complementary dual and the indices, the 2 and the 18 adds up to the 20 players. So equilibrium resistance, which is what I'm thriving for, is high if and only if the critical mass is small and vice versa. Everybody okay? Please feel free to stop me. So let me now put it into formal definitions so we have something to work with. So terminology, I would say that profile theta induces a profile sigma, both profiles, if and only if sigma is best response to theta, or for every player I, sigma I is the best response to theta. So if they play theta, if they imagine that theta will be played, if theta comes to mind, everybody may come up with sigma as a response to that. Oh, and the critical mass of sigma is the minimal number of sigma players that induces sigma. What do I mean by that? The smallest integer L from 1 to n, such that at any profile theta with at least L sigma players, any such profile induces sigma. It's enough that L of the players will play sigma to make everybody wants to play sigma, and I'm looking for the smallest L with this property, and this will be the critical mass of this sigma, so that in the previous example that would be 2. You need 2 players to play the lowest price to make everybody wants to price the lowest price. Anybody okay? And the dual index is the resilience of sigma. Rho in the game tau of sigma is the maximal number of sigma defectors that sigma resist. What do I mean by that? Is the largest integer from 0 to n minus 1, such that at any profile theta with d or fewer defectors induces the play of sigma. So it doesn't matter how many people defected, as long as it's more than this critical value, they would want to play sigma. Everybody okay? And you can check from the definition right away, because for every sigma, the number of sigma loyalists plus the number of sigma defectors equals n. It follows that the resilience plus the critical mass always equals n, so you can use them both. It's convenient in some cases to think of defectors and in some cases to think of players. And there is monotonicity in the tune. If k players can, if 2 players can induce sigma, then 5 players will induce it, or if 5 players are deterred from defection, the 2 players will be deterred from defection. So you have monotonicity, natural monotonicity in both. And kappa, the critical mass, take any value from 1 to n plus 1. N plus 1 is phony because there are no profiles with n plus 1. And the resilience is anywhere from minus 1 to n minus 1. There's no minus 1, so it's true for every profile. Sigma is a Nash for equilibrium if and only if the critical mass is less than or equal to n. And you can see natural when the critical mass equals n, it's exactly Nash equilibrium. That's exactly, if everybody plays it, then everybody wants to play it. Or if the resilience is greater than or equal to 0. Sigma is a dominant strategy equilibrium if any one player plays it, everybody wants to play it, or if any n-1 defect, the remaining player and everybody else doesn't want to defect. So it identifies the natural dominant strategy equilibrium. And we chose it the extreme values n-1 for L or for kappa and -1 for resilience, because all profiles that are not Nash equilibrium will fall into this by definition. Okay. So presenting the same things that what I said in a table form is maybe more natural. So if I have n-person games, so I have n-person games, gamma, the critical mass. Use the mic. Yes. So if I start from the critical mass, because I'm from Israel, if you read it from right to left, it's going to go from 1 to n to n plus 1, which is vacuously anything which is not Nash equilibrium. And if you go from the resilience from left to right, it starts from 0 up to n minus 1, which is the maximal resilience within this range. And these correspond to what we call everything to the left of the heavy line is things that are sigmas that are not Nash equilibrium, and everything to the right of the heavy line, every sigma there is a Nash equilibrium. Is everybody, so that maybe a table form is more visual. So now let me look at the equilibrium concept to show. So let me take the bottom of the previous table, and I have the resilience levels. And if you look at the resilience from, somebody said to use the mic. If you look at the resilience starting from 0 on, these are all Nash equilibria. And this is a solution concept, Nash equilibrium, right? So let me try to generalize this idea. And I say if a Neyman-Nash equilibrium concept, VNN, not VN, not VNM, but VNN. For Neyman-Nash equilibrium concept is a correspondence that takes every game and associates to the game a subset of the profiles that satisfy the equilibrium concept. For example, for every game you take the set of Nash equilibrium, or for every game you take the dominant strategy equilibrium, and that gives you the dominant strategy concept or the Nash equilibrium concept. And you wanted to satisfy 3 axioms that I'll be happy to explain if anybody wants me to. Anonymity, best response monotonicity, and satisfy the sure thing principle copied from decision theory to game theory. And let's define rho to the greater than or equal to q of the game gamma to be all the profiles of resilience greater than or equal to q. Then you can see that Nash fits this definition. These are all the profiles greater than or equal to 0. Dominant strategy equilibrium satisfy this definition. It's all the profiles of resilience greater than or equal to n minus 1. And a general theorem that we reported on in GEB to 2024 is that these are exactly full characterization. An equilibrium E is a non-trivial Neyman-Nash equilibrium concept if and only if it is of the form E equals rho to the greater than or equal to Q. So we already saw that Nash equilibrium are the top line in this diagram. Dominant strategy equilibrium are the bottom of this diagram, but there are all these other intermediary concepts that are missing when you take rho greater than or equal to 0, rho greater than or equal to 1, etc. In particular, I'm going to look at the equilibrium rho greater than or equal to n minus 2, nearly dominant strategy equilibrium, and the ones which rho equals to 0, greater than to 0 but not greater than 1. And I'm going to show you a couple of games where these are very useful as a way to view what is likely to be played or not. Okay. The sure thing principle says if I have a game and I have an equilibrium sigma and I take another game with the same, and I take another game, if I have a game, if I have 2 games with the same strategy profile, the same payoff matrix, and in both games a certain combination of strategies is equilibrium, if I have two games like this and I have the game lambda 1 plus 1 minus lambda the other, this same entry in the payoff table will be exactly a solution concept of the uncertain game. If I'm not sure which of two games is played, but in both of them you're willing to play 3-5, then 3-5 will be something you're willing to play in the unsure game. So let me show you two equilibria that we already discussed some, and then show you the one I want to discuss. So I will talk about fragile Nash equilibrium. These are equilibrium of resilience 0. And in words, it's a Nash equilibrium that does not resist even a single defect. Or if somebody changes their mind, it's going to destroy the best response property of sigma. These are called fragile because one will destroy the best response. And on the strong side, the profile is nearly dominant strategy equilibrium if the resilience is greater than or equal to n-2, which means that the critical mass is 2, requires 2 or less. So the fact that one player playing it means that sigma j is sigma is best response for every other player. Because if one player played, any other player could be the second one that plays it. And by the fact that he plays it, it becomes best response for everybody, including Mr. 2. And since best response doesn't depend on what you do, if I complete the formula, if I complete the profile, and it's a best response for you to play it, it's best response to what everybody else does, not what you did anyhow. So it's enough that one player playing it, that it becomes a best response for every other player. And it's a very strong property, all you need. So in the pricing example, as I discussed before, if one player is willing to sell it for the price of 1, it will be everybody's best response to sell it for the price of 1. Because if one wants to sell it for the price of 1, if 2 sells it for the price of 1, then I have 2 players selling it for the price of 1. And now it's best response for everybody, including the original 2. So one player can induce it in a very strong sense. Now I want a little stronger property, so I would say that we'll discuss strict non-dominant strategy equilibrium, which I will call contagious for short. It's a strategy profile gamma, that for every profile theta, with some player playing gamma I, gamma J is a strict best response for every player, meaning that whatever the other players play, I'm strictly better off playing this. And in the pricing game, you can see that everybody pricing at gamma is a strict, nearly dominant strategy equilibrium. So it means that it has this nice property that enough that one player playing it to make it the strict best response for everybody else. So, and similar to this, if I look at the 10 common value auction, and I take the bid gamma equals tau equals 9999, is contagious. If everybody bids 9 on a value that's worth 10, that everybody is playing his strict best response to somebody else. So it's very attractive equilibrium in auctions. But there is a nice lemma that I'm going to use. Consider any n-person strategic game gamma with a contagious equilibrium tau. By definition, the resilience of tau is greater than or equal to n minus 2. And very importantly, for exact implementation, the resilience of any other profile of strategies is less than or equal to 0. So it's either fragile equilibrium or not Nash. So if I have if I have a strategy like tau, it's very attractive because it's going to be dominant for everybody as soon as one plays it. And any competing profile is not really serious. Is it clear? So So tau is the unique, most resilient profile possible in gamma, and any profile other than tau is either not Nash or fragile. And in particular, if you were doing dominant strategy or nearly dominant strategy implementation, it is you have the players playing a contagious equilibrium. So contagious equilibrium will implement everything that you could implement with dominant strategy equilibrium. So if you look at the tables I wrote before, and if again you look at all the resilience levels, it's a very special structure, because if I have a tau like this, it is the only one that could be in one of these two cells, and any other profile of strategies must be 0 or less. So it's very nice for implementation to have this property. So in words, the pricing games that we discussed before are exact contagious implementation of the lowest price profile, and the highest price is implemented exactly as a contagious equilibrium by highest bid auction in the first price auction. And what I want to do next is show you how to implement confession in end prisoner's dilemma game. I'm going to make the claim that the standard example you see are not valid for some consideration. So I'm going to look at the n-person prisoner's dilemma, and we have a nice example that I will allude to at the end. So I have M, who's a mastermind who might have recruited 20 conspirators. I call them 1 to up to 20 to commit a crime, and the prosecutor has no evidence, but he wishes to impose a jail sentence of at least 5 years on M if the crime was committed, but he wants to let M and the rest go free if the crime was not committed. But there are some constraints, and these are important because usually avoided in standard prisoner's dilemma example. The judge says that if nobody confesses, the prosecutor still has no evidence, and the judge says, I will release everybody with 0 jail sentence and a declaration of innocent for lack of evidence if nobody confesses. And that's very important, because that means that denying is not a dominant strategy, because if everybody denies, I'm strictly better off denying and get a letter of innocent for lack of evidence, right? Which most prisoners' dilemma examples exclude. Moreover, the judge says, I want you to impose more severe punishment on exposed deniers. If I deny in court, but the judge has proved that I did commit it, he will throw the book at me because he can punish me more severely for somebody who refuses to admit the crime in the face of evidence. And that's very important, because that means that confession can be made a contagious equilibrium. And the preference are guilty conspirators prefer less time, but if freed, they have strict preference for being declared innocent. And I can show you, for examples in the state case where conspirators preferred to be declared innocent. So the prosecutor consideration, he has 20 defendants, have them play a pre-RICO style prisoner's dilemma game. Each defendant will be given 2 choices: confess and present convincing evidence of the joint crime, or deny. And those of you who may be confused, notice that I reversed the role of the C and the D. C is not cooperate, C is confess, and D is deny. If they committed the crime, each can play confess or deny. If not, each can only play deny, because they don't have the evidence to show when they confess. And they have common knowledge between them about the crime commitment. And the judge would agree to the following, to any scheme that satisfies his guidelines. Under the LE guideline confession cannot be a dominant strategy. Just the dominant strategy implementation is impossible. And I presented this paper earlier in the summer, and Eric Maskin said this is very important. You have to show this first. And by the judge restrictions, rule this out. And implementation must be based on equilibrium of resilience 18 or less, because it doesn't work with dominant strategy equilibrium. But under the exposed denier guideline, all confess would be a contagious equilibrium, because if whatever they do, if I confess, I possibly get a declaration of innocence, so I'm better off doing that. It would be an equilibrium of resilience 18. So the prosecutor constructs the obvious implementation scheme. He was going to ask everybody to confess or deny. If there is complete denial, he lets everybody go free, and everybody gets an innocent for lack of evidence. If everybody confess, he will throw everybody in jail for 3 years, and there will be a sentence of 10 years. Is not a player, he's just a subject to the confession. The interesting part is if you have mixed case, some confess, but not all confess, he can reward the confessors with 0 year jail time, which gives them a payoff of 0, I assume. And every denier in this mixed case will get 10 years jail in punishment for being an exposed denier, and the payoff will be -10. So these are the rules that the prosecutor suggests, and these rules presumably will satisfy the guidelines of the judge. Everybody okay? So why would the guilty defendants confess? There are 2 possible pure strategy Nash equilibrium, all confess and all deny. It's easy to see that all confess is contagious for the reasons I already mentioned. Thus, the contagious equilibrium lemma, C hat, everybody confessing, is the unique, most resilient profile with 18. And any other, by the lemma I mentioned, any other pure or mixed strategy, sigma different than C hat, is not Nash or fragile. So it's clear what they would confess in game theoretic fair terms. If you look at the reporters who were viewing the trial in the Georgia state, they said it more colorfully. The fragility of all deny, just the fear that one defector will confess, induces all deniers to confess too. So the deniers is not the fragility, everybody denying is fragile. And the low critical mass of C, which is the plus of C, everybody confessing, the confession of any one defendant induces everybody else to confess, no matter what the others do. So it's a very strong equilibrium, attractive equilibrium concept. And if you had more than 20 players, these 2 aspects will be even more exaggerated. And let me elaborate on this here. What the prosecutor did, she made confessing a contagious strategy and every deny be a fragile one. Specifically, if your opponent confesses and you deny, your opponent gets 0 and you get 10 years. But if you confess 2 when your opponent confesses, you get 0 or 3 years, each one better for you than the alternative 10 years when you deny. So it's better to confess if you think that there is one confessor. This leads to a web of mistrust in an attempted agreement to all deny. Specifically, they are in the fear of fear situation. This is in which each defendant fears that the fear of his or her opponents may motivate them to confess too. See, for example, Morris and Sheen, 1998, for Bayesian reasoning about run-on banks. So I don't know if that reminds you of run-on banks, but it's a similar kind of thing, but the explanation doesn't have to be that complicated. It's just, fear of what happens if they don't. And I found out after writing this that there is a name for it in psychology. They talk to this kind of situation as mass paranoia or mass hysteria. And they can go to a great discussion, psychological discussion of what makes it or not. But in game theory, it's a result of three simple von Neumann-Nash axioms that imply that the play of Nash equilibrium and resilience analysis can point to one of the two that are implied by the axioms. And you can actually see the actual Georgia State 19-defendant RICO trial that took place in Georgia State before the election of Donald Trump. And 4 people denied when asked. And there was Scott Hall, Kenneth Chesborough, Jenna Elas, and Sidney Powell. There are 3 pictures of the 3 lawyers among the 4 of them, and they all actually confessed. This is a little more sophisticated than what I'm describing, because she went to it sequentially, and as soon as one confessed, she put them on the web. So she had to get the first confession for fear of later defections. But once she had 2 and she wanted 3 or more to make the case very convincing, eventually it would have been all one suspect. But those of you who followed the news know that the trial was interrupted because she got into her own personal problems I don't want to get into, and she had to be taken off the case. And there is a game theoretic discussion of equilibrium, persuasion to play an equilibrium. And this is a very good example of this that goes by coalitional persuasion. So standard persuasion games involve revealing information to some player to make him react to the equilibrium to play something else. But this is coalitional persuasion. I can persuade everybody to play a strategy equilibrium if I tell him what his or her opponents may play. And the nice thing here is that I only need 2 opponents in the example that I have, because if I convince 2 players to confess, then I convinced everyone. So it's easy strategic persuasion through coalitions. And you can look at cartel, and we can generalize this example and show that cartels are unstable. And you can compare it also to other standard concepts from game theory. So this fragility in the sense that, excuse me, in the sense that I describe here is different than Zelton's imperfection. Everybody denying is fragile in the sense of Kalai and Kalai here, but it is perfect a la Zelton. So to say that equilibrium is fragile in the sense that we discuss is different than saying something is fragile because it doesn't react well to trembles away from the equilibrium. And that's important here to notice that I'm talking about defection from equilibrium in the real sense. And that came up a lot in the morning of when we had a discussion of war and peace, I think, because fear of what other people may do may be within the game just trembles. But fear of what some players may do may be motivated by bigger considerations. So, for example, I have here. So suppose I look at my colleagues at Northwestern study supply chain equilibrium. So if you have a supply chain game between so you have a supply chain between the producers of chips and Ford company who has to install chips in their car. And they bargain over the chips that Ford would like to install in their cars. For considerations of chips alone, they may choose some chips, but the fact that they are afraid that the production of chips may be interrupted by China, who may invade the producer and disallow the production of the chips that Ford wants, they may choose a different type of chips to install in their car, not just necessarily the one that bargaining led to. So considerations outside the game may lead to defections from the game, which are not trembling and infinitesimal defections, but bigger defections. And I'm taking this into account here. And similarly with Aumann's, everybody defecting with certainty is strictly Pareto dominates every other pure strategy profile, thus unimprovable to any group of defectors. It's strong coalitional proof. But coalitional defection ignores ensuring own elementary payoff under hypothetical. So I may decide to play something else because what I play may be very much in danger, because if my opponent plays something else, my penalty may be very big. So I may play some strategy which will give me some insurance benefit in the game, even though if you just do equilibrium considerations, it will not get you there. But we all play suboptimal choices in the game to have an insurance against bad behavior by some other players. So in the RICO and supply chain game, players' consideration of payoffs under unrestricted opponent deviations play an important game. So these are things we usually ignore in standard Nash equilibrium or other kind of domination equilibrium concepts. And I'll be happy to take any questions. Okay, so these are the examples that I talked about. So for example, in the coordination game played by Taiwan and the chip producer and chip users like Ford Company, the game studied by my supply chain friends in the department ignored changes such as production takeover by China or depletion of silicon. These fears may want me to compromise on other equilibrium that would not have been the result of standard strategy. And fear of fears, as I described already, is very famous because it was already captured the imagination of the US voters when F.D. Roosevelt said the only thing that we have to fear is fear itself. There was the cure against depression. And there was again fear of fears, the fear that everybody will get into a depressing state. And the paper we're writing now is more comparison with standard equilibrium concepts, but I will skip it here. So these are what I said I would like to express in the abstract, if there are any questions. Okay. Which game? The equilibrium maximizing your potential. Potential game. That's in the next paper. There are differences. I mean, so you can take the natural equilibrium there, and it's not immune to small resistance argument. No, there's no theorem in general, but there's counterexamples that show that these are different notions. Yes.
Beginning of the talk, that you said that Neyman was demanding the dominant strategy equilibrium, while in Neyman-Morgenstern paper, they actually didn't use dominant strategy, but what we now can call guaranteed utility equilibrium. That was the first example for a guaranteed utility equilibrium. Yes. So I'm just.
So there are many people, and one of them is von Neumann, that I would love to dig out and have them face the argument that you're making. The first person would be Nash, because Nash introduced Nash equilibrium. It stopped at critical mass 1. He didn't go with all the other critical masses. He was a smart man. I'm sure if I showed him the paper, he will understand right away. And maybe he stopped because he didn't want to lose audience. So he defined Nash equilibrium as is. The second person I'd like to dig out and talk to is Shapley, because Shapley liked dominant strategy but did not like Nash equilibrium. And if I show you that these are all steps by a ladder of equilibrium refinements, or more careful, he would have to tell me when did he stop to like Nash and at what level did he like dominant strategy. It's hard. The third person that you are pointing to very importantly is von Neumann. Von Neumann said, dominant strategy equilibrium, in the same source, I think, where you found it. I like dominant strategy equilibrium because it's the best equilibrium. But it doesn't exist, so I'm going to invent my stupid equilibrium that didn't go anywhere. Nobody uses von Neumann Morgenstern equilibrium now. Anyhow, I don't want to insult von Neumann. But he acknowledged that dominant strategy equilibrium is a better concept. But in the same line, right after that, he said, but it doesn't exist. So this gives me a little broader sense of existence with examples. Like nearly dominant strategy, if one player plays it, if one sells it for the lowest price, everybody would want to sell it for the lowest price, right? It's not a Nash equilibrium. If everybody charged 5, I would charge 4. I would not charge 1.
So going for non-Nash equilibria, there is this traveler's dilemma, which is the simultaneous version of the...
that's one of the examples that I'm...
Okay, so that is a dominant strategy. Is one of the things that work with your concept?
Yes.
Okay, very good. Thank you.
Yes. The traveler's dilemma is a key example.
I have a question.
Sure.
I couldn't help but remember of the Gilbert-Satterwhite theorem.
Yes.
That say that a choice function is DSE implementable only if it's dictatorial. So have you wondered if...
That would be a beautiful paper to write if I was younger and more capable, and if I could convince my son to stop doing computer science and come back to game theory, I would encourage him to do that.
I can do that for you.
Yeah. Can we overcome the non-existence of Gilbert-Satterwhite by, instead of asking for dominant strategy or even Nash, go for something lesser?
Okay, thank you.
Thank you. Thank you all.
Som teste, teste, ei, 2, teste. Teste, ei, 2, teste. Som teste, ei, 2, teste, ei. Som teste, ei, 2, teste, ei. Teste 2, ei, 2, teste. Teste 2, ei, 2, teste. Estava nisso aqui mesmo?
Senhora, porque senão não aparecia o cancelamento de eco. Deixa eu ensinar ele.
Som teste, ei, 2, teste. Ei, 2, teste.
Eu frisei lá.
É 8, 5, parece. Teste 2. Me ouves, Jonas?
Sim, escuto.
Tá ok. Perfeitamente?
Sim. Tu tá falando o quê? Uns 7 centímetros no microfone? Não?
Ok. O que você está visualizando é a live já vai começar, correto? Você está falando baixo propositalmente, né?
Mais ou menos, meu microfone aqui é ruim.
Tá ok, então. Obrigado.
Nada.
Deixa eu só habilitar um negócio aqui.
Otherwise, I'll fall asleep.
But
If I
you
sit of the story, say about a vampire.
But I want to take an opportunity to say nice things about Shmuel Zamir before I let him talk. So I think of Shmuel as being the representative of the brilliant school of game theory that has a location in Jerusalem and a location in Paris and a location in Louvain-la-Neuve. And Mertens is in this group, and Neyman is in this group, and Sylvain Sorin is in this group. But I think that Shmuel's the only one who's worked in all three of these places. So he is a man of the world in I think the best sense. And you know what he's famous for, but I'm here to remind you that he's done a lot of things. He'll talk about auctions. He, I think, was part of a team that did the first sort of ethnographic experiment on bargaining 35 years ago. He is a co-author of a book on repeated games that brought to light, brought to the Americas stuff that the folks at Core knew in the 1970s, 80s. He's written the paper that all of us use, but none of us have read, with Mertens, that allows us to use games of imperfect information consistently. And I think that when it comes time to give career service awards, we'll remember Shmuel for being editor of the International Journal of Game Theory. We'll remember him for being a co-author of a massive text on game theory that has something for everyone, for people who don't know game theory, for people who are learning game theory, and for people who think they know game theory. So these things we are all grateful for, but I'm going to close with a story. 7 years ago, I gave a talk in Tel Aviv, and I was very relieved that it was over. And I was wandering along by myself, and I got lost. And it was a day of the Tel Aviv marathon, and the taxis weren't running, and things were confused. But I was fortunate enough to have Shmuel's phone number in my dumb phone. And I was audacious enough to call Shmuel. And I will close this by saying, thank you, Shmuel, for saving my life and letting everybody in the audience listen to his talk.
Well, thank you, Joel, for
his nice words. I want to thank first Marilda and for organizing this nice workshop for the 4th time now, and her team. And let me, since Joel took some of my time here, I will start by my lecture. Okay, this is a joint work with, I don't know, I like to move here. This is a joint work with Todd Kaplan, and it's on, you see the word information there, which was really my main occupation in all my career. And auction is one domain here. So the question we're asking is, in a private value first price auction, can a seller with private information about the valuation of the players use his information? By the way, he will stand abbreviation for he or she from here on. I mean, otherwise it will be long. So as to increase revenue. Okay, let me start, and actually this, let me fix ideas. I'm sure I don't have to say it, but since this will be on the background of the whole talk, we are speaking of first price sealed bid auction. So one indivisible good is put to sale. Buyers submit sealed bid. Buyers submit sealed bid to the seller. The buyer with the highest bid wins, gets the object. Here again, he or she gets the object and pays his bid. The assumption is that the buyer's valuations for the object are independent random variable. Well, this is, as I said, it's known to everybody. So when a buyer bids B, then he will win V minus B if he wins, and the probability of winning is this. Therefore, he will choose B so as to maximize this. And the solution for the case, for instance, of uniform distribution between 0 and 1 is that each buyer will bid half of its value. Okay, this is the line. Let me see if this works. Yeah, this is the line of half V. And the revenue of the seller is 1/3. By the way, I will always make reference to social surplus. Social surplus here, it's all the gain by all players, including sellers and buyers. In this case, this is the expectation of the high value, which is 2/3. So the surplus is 2/3, and the seller makes a profit of 1/2 of the surplus. And now the motivating example that led us really to this question was the following. In a paper by these 4 guys, Landsberger, by the way, Rubinstein is not Ariel Rubinstein, the economist, it's Jacob Rubinstein from the Technion, who helped us with the differential equation that we came across there. Okay, so these 4 guys studied the situation where, assume that in such as the basic auction, after the valuations of the ranking of the valuations become common knowledge. So it's common knowledge that buyer A has higher valuation than buyer B. That's all. Okay, what happens then? What happened there? We found out here is we solved this. And what we found is that there are 2 bidding functions, one for the guy that knows he is high, and one for the one that knows he is low. And now the fact that both of them bid more than one half. Or for all values. Okay. The BL being so higher than half V is quite understandable because the lower guy has no chance if he continues to bid the half V. So he pushes upwards and bids more. But the fact that the high player bids still more than he would pay without knowing that he's high. Okay? Which is, there are two things here. First of all, he knows he's high, so he intuitively could take it easier. But on the other hand, he knows that the low guy, the other guy, is that's what the whole fun about information, you know, what I think that you think and so on. Anyway, this is the result. This is the fact. I mean, even without the explanation. So we said, if this is the situation, then why not, if the seller happens to know this, the ranking, it could increase its profit by just making it public. Okay, so that's the beginning, really really the motivation for the whole work here. Is there a water here? Oh, sorry. So in general, I mean, why do we want to study this question? Well, because a seller really indeed may have some private information. It can come, for instance, in an auction house. It can be from previous information, previous auctions that with the same participants. Oh. And then, I mean, the seller may have know more about the object being sold than the buyers. So the attribute he may know that these attributes affect the value of the buyer differently. Okay? If information proves to be valuable, it may be worthwhile for the seller to try to acquire it. Okay, so that's the question we want to study. The framework to study this, there are two possible frameworks to study this. One is mechanism design. Given the information, the seller chooses the optimal selling mechanism to maximize his revenue. The other framework can be within a specific auction design. Okay? We're not allowed to change the auction design. Why we don't want to change it and think of mechanism design? It may be impossible or illegal or too costly that the selling mechanism to change the selling mechanism according to the available information. So we study this problem. This is just justification. We study the problem within the framework of first price auction. So the setup is, in this setup, as soon as the seller has private information, he can communicate with the buyers. We must consider him as a player. I mean, unlike in the usual model, who is behind, the seller is behind and inactive. Here, he is a player. The features of the seller as a player is characterized by these 3 points: the available information he has, the available signal that he uses, the language, and the commitment power. Commitment power can be we consider 3 levels of commitment power. One is no commitment at all. Okay? The other is what we call it has various names in the literature. We called it a partial truthful commitment, This means actually you have to tell the truth. Whatever you say must be correct. The signals are verifiable. That's the other name which is around in this context. And the full commitment, sorry, the truthful need not be here, but full commitment is actually committing to a signaling strategy. So you write down a signaling strategy and let a machine or some other agent do it without, you are not able to interfere with it later, okay? So let's take an example of no commitment. The example of no commitment, take a motivating example. So we have the available information for the seller, say he only knows the ranking of the values. The available information is therefore two signals. One is to say, to write down V1 bigger than V2 or V2 bigger than V1, okay? The seller has no commitment power. The result is that the revenue is 1/3. The seller's information is useless. He or she, he cannot, if he has no commitment power, he cannot make any gain from this. To see this, just to, let me, if I can roll quickly backwards. Let's go to the picture there. Yeah, if you see that, I mean, of course, the seller would like to announce, to reverse to lie here, because he wants the high buyer to bid according to the upper bidding line, okay? But this is not credible, and he cannot do it without commitment, okay? He cannot do it without commitment. Actually, the result that I'm talking about is true for any available signals or any private or public signals. Could not help here. If you don't have any commitment power, you cannot get any advantage from the fact that you know the ranking, okay? Let's go to this with, let's give him some, let's say, partial truthful commitment with the same example, okay? Now, available information is as before, the ranking. Now we give him one more possibility, not to say anything. I mean, just the signal fee is no announcement, so either he says V1 bigger than V2 or V2 bigger than V1, or say nothing. Now, notice that when I'm writing now equilibrium, I'm writing this what each of the players do, including the seller, okay? So the seller has partial truthful commitment. Now, the equilibrium, the seller always announced the true ranking. Okay? The buyers bid according to figure 1. I will not roll it back now, but you remember it. According to figure 1, when the ranking is announced. Bid half of your value when nothing is said, when there is no announcement. Okay? This gives the revenue of 0.3696, which is bigger than 1/3. So already there is some, yes?
What happens if the seller knows what to do, but it's only allowed?
This is the next slide. Not really the next, but it will come soon. Yeah, it will be coming. Okay, so we are still in this picture, but so we already have some situation where the seller can have some profit from this fact while telling the truth. I mean, not the whole truth, but the truth. In this case, the whole truth even. Okay, so let's now take, you see what Sergio suggested, that that the seller knows V1 and V2, knows really the valuation. Okay? The signals, he can say nothing. He can announce the ranking. And he can announce, we give him only 3 possibilities. He can announce V1, V2. Okay? Is that clear? I mean, the seller knows V1 and V2. And then he can either keep quiet or say, this, you are higher than this, or announce fully the information. Remember, we are an impartial truthful, so he has to say the truth. He has to say the real V1 and V2. Okay? Here is the equilibrium. I will have to quickly just show you how it, now here is the equilibrium. What is the equilibrium? The signaling strategy, just say, announce the ranking if VL is, I hope that the notation is clear. I mean, VL is the low, and if the low value is less or equal to the half of the higher value. In that case, you just say the ranking, okay? If VL is bigger than 1/2 of VH, announce the values. Yes? Excuse me?
The beliefs, the bidders. Announce
Yeah, yeah.
What do I think about the other valuation?
What you can say? I mean, if he is hard, that brings us to the other paper that I mentioned. I mean, what are the beliefs? I mean, we are assuming, first of all, that the signal is truthful, okay? That's the truth. Then you are, as usual in these cases, you are Bayesian. I mean, if I know that, for instance, if I know that I'm higher and I know my value is 0.7, then I know in this situation of uniform distribution that your value is distributed uniformly between 0 and 0.7, okay? The beliefs are derived from the assumption about being Bayesian and, okay? So here is the strategy. And I specified the signaling strategy, and it's not completed here, but you'll see that the buyers, the low value buyer bids his value, and the higher value bids if he knows the value of the other one, V2, that's in this region. Okay, that's, let me see. It's here. In this region, he bids the V2. And in this region, he bids half of his value, which is the highest possible for the other value. So in any case, he wins the auction is efficient, okay? And the revenue equals to 5/12, which is this number, which is 5/8 of the social surplus, 2/3, 5/8. We started with 1/2, we were going up slowly, okay? 5/8 of the sequence, okay. Now, let us enlarge the set of messages. Before we allowed him only 3 messages, now we I'll write it here. Okay. We announce the true ranking and the corresponding I for which VL belongs to. So let me show this picture. It will be easier than reading all the notation. Look at this. And this axis is VL. And we partition, and this is VH. Okay? And we partition this with 1/2 here, then half the way here, which is 3/4, and so on and so on. Okay? And the language, the messages are player, the seller announces the ranking, first of all. So each one knows whether it's high or low. And then it says where VL is located, in which region, whether it's less than half, then the high value, or 3/4, or so on and so on. Okay? Is that clear? And what happens here, again, I didn't specify I will now, the strategy of the buyers. The low value will always bid his value, her value. The high value bids the highest possible value of its opponent. Is that clear? So if the high value, if the announcement was that VL is here, then the high value would bid this much, which is the highest value possible for the other player, and he wins for sure the competition. Is that clear? Okay. Now, so we did that, and the result is, wait a second, first of all, that's the computation. I mean, if you believe me, this is the computation, and the revenue is now 4/9, which is bigger than 5/12, okay, which was the previous one, which is 2/3 already of the social surplus, okay?
Are you saying that this is the optimal partition? You can choose any partition?
Excellent. You're always clever than me. That's the next slide. Okay? That's the next slide. Okay? Proposition among all signal strategies of the seller defined by sequence. Okay? Where the seller announces the interval in which VL is. Okay? Then the highest revenue is obtained when this is the partition. Okay? So this branch is closed. Okay? We know that the better you can do. But now we try to push further. I mean, can you do more? I mean, why interval? Yes. What? Any problem, Sergio? No, the sequence is the sequence partition of 0, 1. Yeah, defined. These are intervals. Announces alpha. Not necessarily dyadic, you know. I mean. Yeah. Okay. Now, can the seller do better than that by using a set of more general signals? It can. Higher revenue can be generated by signals of the form of the same idea. I mean, to give an interval in which VL is, but not necessarily a consequence of sequence of intervals, successive intervals. We'll see the example in a minute. Or here it is. Again, you can read it. I mean, this is a situation where it's defined by 3 numbers, but I think the easiest would be just to see it. See it here. We partitioned, you see, again, this is VL here. 1, actually, this is 1 means that's V high is here. Okay, so first, we again partition 0, 1, by the way, as before. But the signals are not successive intervals. So look at the red thing here. This is 1 signal. And look at the blue. That's a second signal. And the third signal is here. Okay? From here to 1. So here we have three signals. One, that this is what? Exactly, exactly. You're right. I mean, we were not very consistent in the pictures. So those alphas are this means 0.2 means that VL is 0.2 times VH. Okay? And so on. So you see the picture, and it's easier to describe it in Word than to read these notations. If you announce in which of these two, whether it's here on the red, or it's on the blue, or it's outside here. These are the three signals, okay? Signal 1, red signal, blue signal, and purple signal, the last one. The last one will always be this, okay? And again, announces here, M1 is announced. That's first signal. This is second signal. And third signal is V1, V2. I mean, just saying what are the values, okay? This guarantees, okay, these are it doesn't matter. I mean, these, I'm explaining here what conditions are to be satisfied that will make it the equilibrium as follows. So we know the most difficult part of the essential is the signaling part. So the signaling part is here. The buyer that has a lower value bids his value. The higher value always bid the highest possible value of the other. So if he hears M2, the red signal, he bids here. If he hears the blue signal, it's here. If he knows V1, V2, he bids the value of the other guy, okay? And again, this guarantees that defines actually the bidding here, and there the inequality that has to be satisfied. And for this, for instance, that's what we have, okay? We have these numbers. This is just an example. This is just an example, and this generates already a revenue which is higher than two-thirds of VH. Okay? Okay? Higher than two-thirds, which was the best we could do with the continuous thing. Okay? So now we come to, I define, and with this idea, with this in mind, I mean, this we could forget. This was just to prove that we can reach more than this partition. Now, I want to define a family of strategies, signaling strategies, which I call MN. Well, this is a partition of the interval 0, 1 again to M times N intervals. So each message will consist of N intervals. N intervals not necessarily touching each other, okay? So we have M times N intervals. Again, this is a partition of 0, 1. And the idea is that the message is in which the message will tell you that VL is in one of these intervals of this message. Okay? The best, yeah, okay. And that's what, I mean, that's what is written here, just to, I hope. Okay, proposition for any finite M and N, there exists an equilibrium signaling strategy, sigma N. Okay? Equilibrium strategy now looks like this. Here is the case for M m equals 2. Not necessarily the one that I gave before as an example, but this is m 2 by 2. What is 2 by 2? 2 signals, each of them composed of 2 intervals. Okay? So, and the condition for the equilibrium is that the value, the high value bits, the highest possible value of the other. So if this is announced, the blue one, the high bit bids here. If the red one is announced, the high bit bids here. Okay? If this is announced that it is beyond that, then V1, V2 bids V2. Okay? This gives already 0.6909, which is better, but we can go further. Here is the one for 4. 4 times 4. Okay? 4 times 4, well, it's hard to see, but believe me, I mean, that's what our computer produced. Okay? So all these intervals, some of them you hardly see, are covering this part, which is a partition, and 1, 2, 3, 4. So the message will be either red or blue or whatever color and so on, or V1, V2. And the equilibrium is bid. If you if you hear about red, then bid here. I'm speaking now to the high buyer, because the low buyer bids his value. Okay? And this is an equilibrium. And now when this is translated, okay, just before I say that, let's go to 23 by 23, okay? And look at the revenue, 0.7496, okay? This is important. I mean, you'll see in a minute why it's important. It's close to 3/4 here, okay? It's close to 3/4. Now, when I said before, let me go here. This proposition is non-triviality because it says that we can satisfy for any m and n, we can build such a structure with the conditions of the equilibrium, that the best reply for the high is to bid the highest possible in the message, and so on. And here, I mean, I say non-triviality, and I want to thank the guy sitting here, Sergio, for helping us with this. And the result is that we have this specific, I mean, you could say that I can think of other strategies, but this is one strategy that gave us something that we wanted to. So we got, by increasing m and n, actually we took them to be equal, which is again just a question of, to make it easier, we are getting close to 3/4. So just to review what we are doing here. The surplus, it was 2/3, as we know. The classical model, with no information there, the seller gets half of the total surplus. By announcing half and then the value, we got 5/8 of the surplus. By announcing this partition, we got 2/3 of and by announcing, by using this family of strategy, signaling strategy, we get close to 3/4. First question. I don't think I will have any time for proofs, but you see, I could push a button and then you should. Under partial truthful commitment, there is no partition equilibrium. We cannot, where the revenue is exactly 3/4. But we can get close to it. For any, okay. So we can get close to it in this sense, that for any we can generate a family of strategies like this, that for any epsilon, you get the surplus as close as you want to 1/2, which is the 3/4 of the surplus. Okay? Can the seller do even better? The answer is no. The answer is no. And this is nice. I mean, it was easy, but nice surprise. In our example, there's valuation with the valuation IID in 01. The seller, informed by the realized valuation, cannot extract more than 3/4 of the total surplus. Okay? That is 3/4 of the expectation of VH. With any level of commitment, okay? With any level of commitment. And the proof, I will give the proof here because it's simple. We call the min-max theorem. We'll see in a minute why we can use it. Here there's a typo. Here is the proof. I just realized the typo. I didn't have the time and the means to correct it, but anyway. Buyer with value VI, by bidding half of his value, can guarantee this without the half here, okay? Because he wins VI minus 1/2 VI times the probability of winning, which is half of VI, okay? Which is 1/4 of VI squared, okay? Assuming that the other bidder does not bid more than its value, okay? Therefore, each buyer can guarantee just by bidding half of his value, this integral, 1/4 of the integral of this, which is 1/8 of EH. It is 1/12. So the two of them can guarantee 1/8 each. So the two buyers can guarantee 1/4 of E of VH, which means that they cannot leave more than 3/4 E of VH for the seller. Okay? Look, which is the nice thing about it, that the seller becomes a strategic player, then the max-min concept was naturally called for. Since when the auction is efficient, and this I mentioned that the efficiency all the way, this is a constant sum game between the seller and the high valuation buyer. And therefore, we can use the min-max theorem. Okay? The conjecture that 3/4, you can say, can be approximated by this family of equilibria, it can and cannot be obtained fully by partial truthful commitment. The seller, we conjecture that under full commitment, can be reached. So what we have here, full commitment does not yield the seller significantly higher revenue than partial truthful commitment. Apparently the same asymptotically, at least in this case. Okay. Is it generally true? I mean, you are puzzled by these things and you ask yourself various questions. Is it generally true that full commitment power does not yield the seller higher revenue than partial truthful commitment? I will say more about it later. And the answer is no. I mean, generally not. And here again, because lack of time, I will just here as an example where it's not. Again, I will not push the button of the proof. Consider two buyers A and B, where buyer A has a valuation of 1, while buyer B can have valuation of either 1/4 or 3/4, okay, with equal probabilities. The seller knows the buyer's B valuation. That's the information, okay? So, and he can announce either 1/4 or 3/4 or nothing. Remember, this is partial truthful commitment. Yes, okay, he can do this. Now, with partial truthful commitment, he can achieve only 1/2, okay? Because, again, that's the proof goes through this. Under partial truthful commitment, the seller will fully reveal the values. In other words, he says he will make it known what is the value, and therefore, the high value, which is in this case a fixed player that has value 1, will bid the true things, and the expected revenue is 1/2. With full commitment, he can get 5/8, which is higher than 1/2, the revenue partial truthful commitment. I'll just again, I will not go into the proof, but I'll just give you an idea why this can happen. Because in full commitment, the seller can commit to a mixed strategy. He can say, if this happens with this information, I will do this with probability 1/2 and this with probability 3/2. But this is not, this cannot happen with partial truthful commitment, because in this case, he will not really, when the lottery is in the wrong side for him, he would tend to do it. But anyway, this is okay, so yeah. So with full commitment, the seller obtains, this is just for the example. I mean, what I'm saying here, this is just 5/8 here is the highest possible. The highest possible revenue, again, we use we use the min-max theorem here. So let's look at our example with truthful commitment. The effect of the full commitment power is when the seller uses mixed signaling strategy. That's what we said. Since in partial truthful commitment equilibrium, a seller using a mixed signaling strategy must be indifferent between all pure strategies. Okay? In partial truthful. And in full commitment, this can be violated. Okay. Any equilibrium in full commitment setting in which the seller uses signaling strategies, pure signaling strategy, is also an equilibrium in the partial truthful commitment. Okay? Yes? The counter example here with the A and B there, that 1 3/4. Well, I didn't check this, but a little bit of noise wouldn't help here. I mean, you need this distance between the two values is important, and you cannot do it with small noise. This will not do it. This will not do it. But this is just an example. It's not. Okay, thank you. Okay, so Let me see. Okay, now I'll skip things since my chairman is partial truthful commitment. Partial truthful commitment means that telling the truth, but not necessarily the whole truth. That's it. Whatever you say should be true, but you need not say everything. So strategies use of information has been around. I mean, strategic use of information has been around in game theory since the work of Aumann and Macho-Stadler 50 years ago. I'm sorry to reveal my age, but it is about the time that I was involved in it because that's when I was introduced to this subject, and all the work that I did, actually, not only me, but that was done on this, was strategic use of information in games. But here we are, for the first time, applicable in economic context. The strategic use of information is here we present the strategic use of information in auctions, and firms worker presenting. You can see this. I mean, the workers has an unknown outside offer, and for instance, in hiring situation, and is free to announce in negotiating with the firm before the offer is made. He cannot lie, but he can be vague. You can say, maybe I have an offer which is higher. More generally, a bargaining situation where each player disclose truthfully, but strategically parts of the private information. And to some of you, I mean, a professor writing a letter of recommendation to a student, we know that that's very, you need not, usually you don't lie, but you don't say the whole truth. I mean, that's part of it. Okay. So now, since, there's a relevant work of Hart, Kramer, and so on, evidence in games, truth, and commitment. So again, it goes in the same direction that telling the truth, you can reach as much as almost in situations, almost as much as you can achieve by commitment. Now, since my chairman is pushing me, I had a whole section about comparison to classic results, but I skipped most of them. I will go to the one of Crawford and Sobel. They had a paper in 1982, the strategic information transmission. And I'm not going to say any bad word about this, but what? You don't have enough time. No, I will quickly say it. So this, they have a sender and receiver game in which the sender knows the state of nature, which is a number between 0 and 1, and he sends a message, M of S, to the receiver. The receiver chooses a number Y, which is a function of the message received, and the receiver gets minus Y minus S squared, and the sender gets a payoff Y minus S minus B for some positive B. In words, the receiver prefers an action that the action Y close as possible to S, which he doesn't know. The sender knows it. The sender prefers an action as close as possible to S plus B. Okay? And the equilibrium, of without commitment is that each equilibrium is defined by a partition of the interval 0, 1, okay? A real interval, not a single point, a proper interval. At the state S of nature, then the message sent is pi of S. So It says this interval contains S. Okay? And the equilibrium descender reveals partially his information, not really S, but the interval containing S. According to our analysis, so this they interpret as strategic use of information. Coming two lines here. And according to our analysis, with partial truthful commitment power, the sender, there is a full revelation in equilibrium. MS, the sender sends S, the real S. The receiver acts S again, the same message. This gives higher payoff to both players than any of the Crawford-Sobel equilibria. Okay? They had less because they had without commitment. They didn't say it fully. So our point is, and with this I will finish, that the partial revelation in the Crawford-Sobel is not due to lack it's due to lack of commitment power and not to strategic reasons. Okay, they do that because the sender has no commitment power. He cannot be sure that he will be believed. If you would be sure that he's believed, he would say yes. And therefore, the only point here is that this is the strategic lack of commitment power rather than strategic reasons. Thank you. Any question, any remark? If I have time, yes.
If you started with, and you knew that the bidders were, say, independent uniform 0 1.
Yeah.
And you ran a second price auction and got bids, and then you said with small probability, whoops, never mind, that's how the seller could get that information. And as long as that prior probability is small enough, all of your analysis might go through. But of course, as to make that probability bigger, they're going to cheat on the other. The question is, the optimal auction would have been set reservation prices of a half. And then you could have a second price auction with that if you like, or whatever, first price auction, the reservation price of that, we know that. So how does this commit? It must be with commitment that we're not doing as well as the commitment, the optimal auction with reservation price, or you're changing the incentives, they would start cheating in the other.
You are speaking of the Crawford-Sobel example?
Because you're keeping the mechanism fixed. If you're allowed to change the mechanism, you can just say V2. You get.
No, I'm keeping the mechanism unchanged.
I'm adding, you didn't start knowing the information about their bids. Seller doesn't know their true values.
Okay.
Yes, but when they stuck with the mechanism, you cannot change the mechanism. You cannot change the mechanism.
Yeah, I'm not changing the mechanism. I said from the very beginning. I mean, I'm sticking to first price private value auctions.
That's fine. It's private value. I know it's private value auction. They come with private values. You run the first auction, second, however you like, and you look at the bids. As if imagine with probability epsilon, we're going to do what you just did with 1 minus epsilon. We're going to just run an auction according to first price auction, if that's what you want. I don't care. He looks at the bids from that auction with probability epsilon. He says, I'm going to redo it, and I'm going to give you information from Zach, and then follow the Zamir lecture. Now, is that epsilon small enough? It doesn't change the incentives very much. We hope they'll still bid honestly. And whatever we knew about it, like I say, if that first round was the second price auction, it's really easy. They just told them their values. But once we make epsilon, but then you don't get much value from what we just learned from the Zamir auction because we're only using the probability epsilon. As you make it larger, now I'm asking, have you studied that incentives, how it changes the incentives in the first price auction? Because I think it's all covered.
Haven't you been studying?
Of course I have. 1981. So it has to be there's some loss there. Yeah. Unless, that's what the hard part is I've been trying to figure out what exactly is the fraction of revenue as a fraction of the first price auction bidder's high value, and I couldn't get it. So I think either the first part, the alcohol auction with reservation price is actually better than this ex ante, or it has to be that you're corrupting their incentive so that the running the first round doesn't really give him the information that he was hoping to get from the seller was hoping to get from it in order to manipulate the second round, and probably it's now a large exit. Anyway, that was
my guess.
That was the next slide. You just, but you didn't do it. Okay.
But
I think there's another group who started talking 3 minutes ago. So, we'll thank Shmuel again.
Sorry, somebody asked that.
I think he's here all.
to account equal interests of everybody. Okay, the two biggest sub-cases of this model is continuous and discrete case. Continuous case typically assumes that the set of resources is a convex compact in a finite dimensional space, typically actually an interval 0, 1. And discrete case is the one about which I'm going to talk today, is the case where actually the set of resources is finite. It's finite. It's a set A, which consists of finite number of objects, and each object is indivisible and has to go in its entirety to one person. Okay. Continuous case was mostly dealt with by mathematicians in 20th century, and Rave probably will tell you something about that. While discrete case was mostly looked at by computer scientists, and this is really a 21st century literature. Okay. And we will be sitting inside the discrete case. Okay, so that's the story. Okay, so that's the initial story. Okay, so discrete fair division. So classical model, I call it classical, but again, you know, it's really 21st century story. Okay, so over the last 20 to 25 years, there were zillions of papers, 90% of which were produced by computer scientists, which discussed that model. And the model is finite number of agents have to divide finite number of indivisible objects. There are no monies, there are no lotteries, there is no free disposal. So an allocation is a partition of set A of object into n baskets. Each agent gets a basket. Okay. We assume here, again, for the purposes of this talk, but it's a most assumption which allowed people to go reasonably far. So we assume people have different valuations of single objects. So I'm Mrs. I take this, I have this valuation function Vi, which where I assign a valuation to each single object in set of objects A. Notice that my valuation could be positive or negative. Okay, I could hate object, but still everything has to go. Okay, and they have additive valuations over the set. If I receive a basket, my valuation of basket is sum of my valuations of objects in the basket. Nothing special. Okay, so we assume that valuations. There are no incentives in this talk, so we assume that valuations are known. Okay, they are publicly known. They are common knowledge. They are verifiable. No issues. Okay. Now the question is, can we find in this setting allocations which are efficient and fair? Now, efficiency, there is finite number of allocations. Efficiency is a standard Pareto efficiency. There is no issue here. What does fairness mean? This is a bit more tricky because two traditional notions of fairness about which I mostly will be talking today, well, only will talking today, even though there are other options, is envy freeness and proportionality, which is also sometimes called fair share. Envy freeness tells that once partition is proposed, I feel that my basket is the best. I don't envy you. I don't want to exchange my basket for your basket. Right? And proportionality means is that if there are 5 of us, each of us believes that they got at least 20% of the total, right? If there are n of us, each believes that they got at least 1/n of the total in my own valuation. Okay. Now, the problem, those are very well agreed upon notions of fairness in the fair division literature. The problem with discrete model is that they are not really achievable. The classical counterexample here is so-called one diamond and many rocks examples. So if there is one diamond and many rocks on the table, if you don't receive a diamond, you envy the guy who receives the diamond, and you also don't feel that you got your fair share, right? So there is a problem, and it's clear that this problem was resurrected again and again due to indivisibilities. So the solution which was proposed is, okay, we cannot do envy freeness or proportionality in full. We do approximate envy freeness or approximate proportionality. And the approximate means up to one object. I might envy you, but my envy is small. Namely, my envy disappears if I
if I would be allowed to do something about one object. And notice that this is a mental exercise, right? So you propose a partition, and this partition, some people envy other people, but this is a small envy. And small envy interpreted like that. So I look at your basket. I envy you, but my envy is small because if I would be allowed, let's say, to forget about one object in your basket, or make a copy of one object in your basket and add it to my basket, or in case where we all hate our objects, delete one bad object from my basket, right? Do something about one object. Once I do something about one object, envy disappears. In that sense, envy is small. It's up to one object envy. Now, there are several definitions which were played with, and I'm not going to discuss them, okay? But they are all in this same spirit, okay? I will talk about my definition, which is yet different, and that will be later. Okay, so we have those notions of approximate envy freeness and approximate proportionality. First question, are they compatible with with full efficiency? Is it true that in this model we always confine an allocation which is fully efficient and envy-free, or at least proportional up to 1? Well, people looked at that, and actually it's known, it's very important that in that classical model, actually cases of goods when all variations are positive, and of bads, or chores, when all variations are negative, are very different cases. Okay? They are very different cases. They present different technical difficulties. The results are different, so there are issues. Case of goods is easier. So as you see, there is a positive answer to the question I just told you. So for case of goods, well, all variations are positive. There always exists Pareto efficient and envy-free up to one object allocation. And this is the result from 2019. Okay. Now for chores, it was an open problem. Now there is a working paper, very recent, which actually claims to prove that it's also true for chores. I did not do the proof, so I cannot guarantee you that it's true. But some other people whom I trust read the proof and say it's correct. Okay. So, but that kind of gives you some feeling that it's not trivial questions, and there were many people. They told you know there are literally thousands papers. I mean, they are more geared toward computational questions, but questions of this type are also discussed widely, mostly in computer science community. So, so questions, even these straightforward questions, are not easy. Okay, so. That's some kind of a glimpse on a general model. So what I am doing? Well, this is a very simple model, so I want to simplify it a bit more. Right? I want to add additional restrictions. So what do? I consider a situation inside that same model when we add additional constraints. An additional constraint is that every agent has a quota or entitlement, which is the number of objects this agent should receive. And this is the number which is, it's a positive integer which is written on your front. And it has nothing to do with your entitlement, with your contribution, with your rights. It's just some completely exogenous to the story number with which you were born. Okay? And now the principal has those n agents. So there are n agents. Each agent has the valuation function. And each agent has a quota, namely the number of objects they have to receive. And we assume that sum of the quotas is equal to the number of objects in order not to bother with predisposal issue, right? Or, lack of. So there are 3 agents. One is entitled to 3 objects. One is entitled to 5. One is entitled to 7. And there are 15 objects total. Okay. I can give you many examples in which this is a reasonable setting. One which is a bit artificial, but it's a good benchmark illustration and should be dear to everybody in the audience. It's a distribution of teaching load in the department. So I'm department chair, you guys, you are agents. So I have a set of classes to distribute, but each of you has different contract with university, which tells how many classes you have to teach. And some of you have to teach 8, and some of you have to teach 2, right? And that's your quota. And we assume that some of your obligations, or contractual obligations, is equal to the number of courses which we need to teach. Okay. And as a department chair, I was department chair for 20 years. I know very well your preferences. You cannot hide them from me, so I know how you evaluate classes. Okay, so now I just want to be nice to all of you. And your evaluation of classes could be negative or positive. You could love to teach some classes and hate to teach some other classes. Actually, in this model, contrary to classical model, and I will not explain why, but I think you probably have a sense, when evaluations are positive or negative, it does not matter because nothing in the model or in concepts which I will discuss in proposed solution changes if we do affine transformations of utility. So really it does not matter, the sign of evaluations does not matter, and that's nice because now really it's not two different problems, it's one problem. Okay, oops, rejetar, I suppose. I don't know what I reject, but I want to reject it. Okay. So first thing is now we have to return to discussion of what fairness is, right? And let's talk about what, for example, about envy freeness. What does it mean, envy freeness? I have to teach 3 courses. You have to teach 5, right? So I compare my basket of 3 with your basket of 5. When do I envy you? And when I don't envy you. Okay? So we played with different definitions. We believe that the best definitions here, and this is the one which actually allows us to get nice story, is comparison on average. If classes which I get to teach on average are more interesting for me than classes which you get to teach on average, then I don't envy you. Then I feel that the department chair was fair in terms of the average quality of classes. Did not give me bad classes and you good classes. Okay. So now what I will do, remember that you still evaluate your basket based on the sum of your evaluations of objects, but since all your baskets have the same number of objects, because all your baskets have to be on the same size, I just consider the average value of the items in your basket, and I call it your utility. So if you are, and since all your baskets have the same size, it's the same, right? Because we just divide by quota. So I call utility, letter U of a basket, an average value, average variation of of items in the basket for a given person. Now, I don't envy you if my utility from my basket is at least as large as my utility from your basket, right? And I feel that I got my fair share, I'm proportional if my utility from my basket is at least as large as my utility, the average of the total pie. Okay, so those are simple, so those are different definitions, but they are natural in this setting. Good. The same problem, Van Diamond, many rock, many other examples. We cannot guarantee full envy freeness or full proportionality. We need to do approximation. So what we propose as an approximation is again up to little reshuffling. So that's it's small envy or small disproportionality which disappears after I do something with one object. We call it fairness up to one upgrade. And for example, in terms of envy freeness, it means the following. So I might envy you, but my envy is small in the following sense. If I would be allowed to upgrade my basket by using your basket as a reference, my envy would stop. So I don't touch your basket, I use it as a reference. I look at my basket, I throw away the worst item there, which I really dislike, and instead I add there the best of your basket. So I upgrade my bad item to the level of the best item in your basket. But I don't touch your basket, right? So your basket is a reference. It's how much I am allowed to upgrade. If after this upgrade, my envy would disappear, then my envy is small. I don't envy you up to one upgrade. This definition is actually stronger than any other definition which is used in preceding literature, which means that if we get a positive result which guarantees us allocation which is, let's say, envy-free or proportional up to one upgrade, then it also would be envy-free or proportional up to one object in all other varieties which exist in the literature. So this is really the strongest one, and in a way it's probably the strongest possible, but that's, again, I don't have time to discuss that. Okay, so so that's the story. Okay, so we have this setting, and the question is, can those properties which be guaranteed together with full efficiency? Okay. And we can say something good about it. Okay, let's see, why is it this? Okay, now this thing doesn't work for me. Great. You know, I might have done something wrong, but I also tried to do it on the, yeah. Here? Ah, you think, yeah, thanks. Perfect. Oh yeah, this technology, okay. Yeah, I'm here. Okay, so first statement. There always exist allocations which are fully parity efficient and proportional up to one upgrade. Okay, and you know, I put here the sketch of the proof or like main idea, but I'm not going to go into it. It's suffice to say that it's at least the way we could do it, it's not trivial, and it consists of first constructing a fractional allocation and then slowly in several steps to make it integer by making more and more entries integer until you get really discrete allocation, just keeping both Pareto optimality and proportionality or proportionality up to one upgrade held. Okay, and in a way it's a constructive proof because it tells you what to do, but it's not really a nice algorithm. Okay, but at least, okay, so that's statement number one. So here we are good. Now, we are not at all good with NV freeness. We don't know much about NV freeness. We have much weaker result about NV freeness. Don't even look at that. I will just tell you. So about NV freeness, there always exist allocations which are fully parity efficient and NV free up to, roughly speaking, 2n minus 2 objects, where n is the number of people. So effectively, the following is true. You can always find an allocation which is fully parity efficient, and you can be envious, but your envy would always disappear if you would be allowed to look at the basket of the guy whom you envy and look at your own basket, and then you upgrade n-1 items in your basket and you downgrade n-1 items in his basket. Right? So if there are few people and each of them is entitled to millions of objects, that probably sounds like not a very bad result. Unfortunately, we could not do more than that, and I honestly might tell you that the only proof we found, it's long and difficult and involves a lot of analysis and algebra machinery. Okay. And I don't know, we hope to get something better, but for the moment we are stuck, so we got this. Okay? So that's what we know. Now, in remaining about 10 minutes I have, I will tell you second part of the story. And second part of the story is the story where I change informational requirements. Okay, in the following way. So we have the same story, right? So you guys, you are instructors in the department. You know your quotas, the number of courses you have to teach. You know the list of courses. Your preferences are public information. Everything is known. I'm department chair. I was department chair for 20 years. I know you. Now, do I really know your cardinal valuation of courses? Probably not. But what I do know is how you rank courses. I can tell that you probably prefer to teach game theory to teaching econometrics, and you're probably indifferent between teaching econometric 1 and econometric 2. But I don't know anything beyond that. So now we have a situation when the principal or the mechanism designer only knows ordinal ranking of agents over the set of objects, over individual objects. Notice, and that's important because it actually makes situation much more difficult and hence much more interesting mathematically to solve. Your preferences don't need to be strict. You might be indifferent, and indifferences might be subjective. I'm indifferent between two courses, and you actually rank them as different. Okay, so this is the situation, and again, so the question is, can we find something which is fair and efficient? Now here, efficiency is a more tricky thing because I, as a designer, I don't know, I don't have full information. So I cannot guarantee efficiency, right? Very classical, very trivial example is assume there are two people, each with quota 2 and 4 classes. And we have the same ranking. A is better than B, better than C, and better than D. If I'm department chair and I want to be nice to both of you, the only way is to give one of you A and D and the other B and C, right? But that could be inefficient because you actually would, it could be that you prefer to flip your allocations, right? So there is paradigm improvement, but I have no way to know it, given my information, right? So now, what can I guarantee as a principle with limited information? What can I guarantee? Well, I can guarantee something much weaker. Namely, let's consider the notion of ordinal domination. So it's a very simple case. So assume there are two baskets, S and T, of the same size Q, which is my quota. And both, so we consider it from my point of view, I'm agent I. And both baskets S and T, I rank from best to worst object. Then, if in basket S, first object in S is better for me than first object in T, second object in S is better than second object in T, etc., well, better or equal, then it's clear that I prefer S to T. If those inequalities can go both ways, then I could prefer S and could prefer T depending on my cardinal utility, right? So it's not known what's going on. So I call the situation when I really prefer SK to TK for all case. In this case, we know that S is preferred to T, and I say that S dominates T for agent I. Now, if there are two allocations, we say that first allocation dominates second, if first allocation dominates second for every agent, right? Now, if I'm principal, if I'm department chair, I would never want to give you guys dominated allocations because I know that there exists another one which for sure would be better for all of you, right? So dominated allocations we should kill. So now I say that an allocation is ordinally efficient if it is not dominated in that sense. And this is the best which I, as a principal with limited information, can guarantee in terms of efficiency. Okay? It's of course a very coarse thing, right? But still, it's something. Okay. So now, a first question to ask is: can we actually describe the set of all efficient allocations in this definition? How do you know whether allocation is ordinally efficient or not? Well, it's actually there is actually a very nice description which helps me a lot, and it's the following. So let's step back a bit from the story and consider the following way to allocate objects. So for each agent who is entitled to Q object, I chop off this agent into Q subagent, and each of those little subagents has exactly the same preference, but only needs one object. Now I have M subagent. The number of subagent is equal to number of objects. I put them in the queue, and I allow them to pick up their object. Each of them needs only one in turn, right? So when it's your turn, you come and you grab the best object. Notice that it's a wonderful definition when preferences are strict, but not so wonderful if preferences are not strict, right? There is a way to nicely refine it, and the way to nicely refine it is the following. When it's your turn, you are not guaranteed an object, you are guaranteed an indifference class. So we start from the set of all possible allocation, then the first guy comes in and deletes all allocations which don't give him one of his top objects, one of his top indifference class. Now the second person comes in and she deletes all, she leaves on the table only those allocations which give her something which is the best possible, and she deletes everything else. And then they continue like that. And after all of them went through this, it might be that we have several allocations left on the table, but everybody is indifferent between all of them. So utility-wise, the result is unique. Okay? So, and that's the definition of allocation resulting from this queue. And different queues, of course, generate different allocation. And we call allocations which result from queues, we call them queuing rules. Okay? And returning to ordinal efficiency, fact is an allocation is ordinally efficient if and only if there exists some queue from which this allocation results. And actually, the backward arrow, if allocation comes from the queue, then it is ordinally efficient. It's not very difficult. The forward arrow to check if allocation is ordinally efficient, then we can find the queue which generates it, is a pain. And again, it's not really pain if preferences are strict, but it's a pain if preferences allow for indifference. Okay. So now we know. So think about me. I am department chair. I know preferences. It's one shot problem, right? It's one preference profile problem. I know your preferences. I want to be nice to you. First of all, I want to guarantee ordinal efficiency, and then I can want to guarantee fairness. If I want to guarantee ordinal efficiency, I am forced to use a queue. So now what I need to do, I need to find a fair queue. The queue which will be most fair. Okay, wonderful. So what is a fair queue? I will just propose you a queue. Okay, and the queue is the following. So we constructed one subagent after another. So if there are already several people in the queue, in next position, I choose who gets the next position, right? So I look at this guy. I try to say, okay, so this is my empty position, number H. Okay, so position number H. I will try to put a subagent in that position from each agent. And for each agent, I calculate, if I put his subagent in this position, how many total subagent he would have at this beginning of the queue relative to his quota. So number of subagents divided by Q. And I will choose the guy for whom this number would be the smallest, the most disadvantaged guy. Right? The guy who so far had the least number of subagents in the queue relative to his quota. And I will continue like that. And actually, you kind of can see that most of the time there will be unique agent. Generically, there will be unique way to construct the queue. In many cases, but more degenerate, there will be several. So, okay, so the statement. This queue guarantees always, no matter the preferences, it always guarantees NV freeness up to 1 upgrade. It also guarantees proportionality up to 1 upgrade. Second statement, if you actually need to choose one queue forever, which you will write in constitution and use for any changing preferences of people, this is the only queue which guarantees NV freeness and proportionality up to 1 object. Nothing else guarantees it. So essentially there is a unique way to guarantee ordinal efficiency and strong fairness. Now probably somebody will tell me what this queue is, because actually it's a very well-known queue. And I invented that queue and I thought, it's a wonderful queue. And then I realized that I am actually inventing the bicycle because the queue is known. No, it doesn't ring the bell. Apportionment methods, Jefferson method. This is the queue. This is the Jefferson method queue. Okay, and I can talk about it because I have like 3 minutes, so I probably should not go into this. Well, I probably because I'm already at the end. Okay, apportionment method. It's the method to in U.S. Parliament, each state gets number of candidates which should be proportional to the size of the state population, right? But we cannot have it fully proportional because of problem is integer, so we have to have it roughly proportional, right? And there is a literature which discusses methods to allocate, to divide the parliament seats between states in proportion to their sizes. And methods which correspond to those queuing stories are so-called House monotonic methods, where whenever the size of the parliament increases by 1 seat, no state loses a representative. And the method which actually corresponds to this construction, it's a very famous and relatively old Jefferson method. Okay, and I think I will not talk about the rest. I will stop here. So, I told you a bit about cardinal case, a bit about ordinal case. Then we also have something about continuous case, but it's even more painful than questions? Of you? Yeah,
I'm fine.
yeah. Okay. Well, I was trying to delete it, but fine.
We can do it afterwards. I think I'm all set. So we are almost on time. Let me check. So thanks for joining me here, and thanks for talking about something which is actually close to my mini course for several reasons. First of all, I don't have to give so much introduction, and secondly, it also involves something interesting from our David Gale, which you might not know. So this is one of the reasons I chose this topic. It is also a problem that was open for 25 years. It might not be the most important problem, but I thought I would never solve it, or nobody would ever solve it, but in the end we did. So this is joint work with two people from Frankfurt, Konstantin Ickstadt and Thorsten Theobald. So this is a question. I mean, how many mixed equilibria can a game have? Say a two-player game, a bi-matrix game. Why is this interesting? For example, we want to know how long it might take to find, for instance, all equilibria. And it also gives us an insight into the structure of Nash equilibria. Now, we have to restrict the type of games we're looking at, because here's a trivial example, which is a degenerate game, where there are two best responses, left and right. And it already has an infinite number of equilibria, because the column player might do either left or right or any convex combination. And then it's an infinite set. So what we want to actually look at is the number of equilibria in a non-degenerate or generic game. There is a definition, which I actually mentioned in my mini course, which is kind of intuitive. Generic means, except for some special cases that have relationships between the payoffs that we wouldn't normally expect. So here's an example of a game that has a lot of equilibria, the coordination game, where we have the identity matrix for both players. Let's look at the bottom case, for example. A 4x4 game, both have the identity matrix. They want to meet. Only if they meet, they get a positive payoff 1. And this game has all the pure equilibria on the diagonal, but also any subset of equilibria that you play with uniform probability. For example, the first and third column, if you play them with uniform probability, also the first and third row are the best responses. And so that defines a mixed Nash equilibrium. And because there are 2 to the n minus 1 in an n by n game, non-empty such sets, we get 2 to the n minus 1 equilibria, mixed equilibria. And the conjecture by Quintin Shubik from at least 1994 was that this is actually the upper bound for these equilibria. It's easy to see for 3x3 games, 2x2 as well, obviously. It has been proved to be true for 4x4 games by, you see in the 90s, Keiding and McLennan and Park. The case n equals 5 is the one that I'm talking about today, among other things, which was open and has been open until very recently. And I disproved it for n equals greater than or equal to 6, where I constructed games which has about 2.4 to the n many equilibria, which is significantly larger than 2 to the n, for example, for a 10 by 10 game, almost twice as many, and obviously exponentially larger. Now, the construction that I did created only 31 equilibria for a 5 by 5 game, and therefore it did not beat, this Quinn-Shubik bound. And so here are the actual numbers of my equilibria. The first example was a 75 equilibria game when you have 6 strategies on each side. And I will explain how I constructed this, because this is a starting point. Now, an easy way to construct more games from an existing game, say we're looking at square games at the moment only. In fact, our work is actually generalizing to non-square games. But suppose you have if you have any game which has a bunch of equilibria, you can add an extra row and column with just a unit payoff in the columns and 0 otherwise, and you double the number of equilibria, because any previous equilibrium stays in equilibrium. Any one where you use the extra column and row with some suitable probability is an equilibrium, and you get the corner pure equilibrium on top. So this is in fact how you can grow when you start with the 1x1 matrix, the coordination game. Now, in particular, you can also construct a 7x7 game from a 6x6 game, with 151 equilibria. And in fact, that's the best thing I know how to do it. Now, let's just look at a simple case. We have 2 rows and any number of columns and columns. And what you do is you try to construct an upper envelope of payoffs. This is an example, 5, 0, 4, 3, 3, 4, 0, 5, which are the possible best responses of the column player. And they're done in such a way that you get this nice many intersections. All the intersection points and the endpoints are possible equilibria, the pure equilibrium in the top left, or where you are indifferent, where the column player is indifferent between A and B, or B and C and D, and D alone. And so you can fill this up with suitable alternating payoffs for the row player, so that any consecutive columns can be played in such a way as to make the row player indifferent. And then you get, in fact, n equilibria, all the endpoints here, which are actually n plus 1 if you have an even number, like here. So 5 equilibria if you have 4 columns, 3 equilibria if you have 2 columns, as we know, but only n when n is odd. And you see one of the interesting parts of this equilibria is that you use actually the same support on the left in all these equilibria, except for the pure ones. And this is something that you clearly need to do if you want to exceed the Queen-Shubik bound, because there in the coordination game, you use each support only once. So if you want to go beyond 2 to the n minus 1, you have to use the support more than once. And that's actually exactly what we'll do in a systematic fashion. Now, I tell you now about counterexamples to the Queen-Shubik conjecture. And they are, as you might guess, related to polytopes, because I told you earlier that bimatrix games are essentially polytope problems. So what do? We look at the following polyhedra first. We have this bimatrix game AB, and we introduce an upper bound on the expected payoffs, say A times Y bar is, at most U in each row. So for instance, if 0, 6, 2, 5, 3, 3 are the 3 rows, you get these rows 2, 3, 2, 1. You now label them when they are best responses, when these inequalities are tight, which are the best responses for the responder, in this case, the row player. And you use 4 and 5, the labels for the existing player who mixes whenever they are unplayed. And then you get, an equilibrium condition that says any pair of points of X bar and Y bar in these polytopes that together have all labels are actually the Nash equilibria. This can be translated to polytopes, which are bounded objects. This one is unbounded because U and V go all the way up to infinity. Here, if A and B are positive, you can divide by U and V and normalize the payoffs to 1. You sacrifice, by the way, the capital X and the capital Y are the mixed strategy simplices. I didn't say that yet. I don't need to, in fact. But here they are unconstrained non-negative variables that have to be rescaled in order to become probability vectors. The rescaling factors is then the payoff. So you look at these polytope pairs and look for complementarity. What is that? In the next slide, complementarity means the following. Look at the inequalities here. I've written them here for the first player first, X non-negative. So we have M inequalities for player 1, non-negative variables. And I've similarly written them first for the second polytope, which are now the best response conditions, meaning whenever AY in row I is tight, meaning it's equal to 1, then this row I is the best response. And the condition says that for each of these two sets of inequalities, either in the first or in the second set, one of the two inequalities has to be tight. Either xi is 0, the strategy is not played, or it's equal to 1 down here, meaning it's the best response. It would not be allowed to have an unplayed best response. Sorry, it will not be allowed to have a positive probability for a pure strategy that is not a best response. And here's the same set of columns, the n columns, of inequalities for the column player. Here best responses against X, here non-negativity or 0 for the column player herself. And the way we identify this is our so-called labels that identify the binding inequalities, which are then expressed by this orthogonality or complementarity condition. So that's what we're looking at. And in a degenerate game, there will be no more, this will be so-called simple polytopes, meaning that in any, there's no more than dimension many facets meeting in a corner. An Egyptian pyramid is not simple because it has the four sides of the pyramid meet at the top. If you perturb it a little bit, you would get a little edge at the top where only 3 things meet. So you want a non-degeneracy. And then what happens is that only vertices of these polytopes corners, that is, extremal points, can be equilibrium strategies. We do also have an artificial equilibrium here, which doesn't count, which is the all-zero vector. Now, as I said, in a non-degenerate game, every Nash equilibrium is a vertex pair of P and Q, so both X and Y are vertices, corners. So the number of vertices of such a polytope is an upper bound on the number of equilibria, because they're actually unique. Once you have one vertex, the other one is unique if it exists. So you cannot have more equilibria than vertices. So that leads to the vertex bound, which means that was just what I said. The number of vertices of such a polytope P and Q minus 1 for the artificial equilibrium is an upper bound on the number of Nash equilibria. Now this number is much lower than when you just look at the supports. There is a theorem, it's called the upper bound theorem for polytopes, which by the way was open for about 25, 30 years, which has an asymptotic form when you look at, say, you fix the dimension m, you increase the number of columns, and say n, and then the number is actually n to the rounded down half of the dimension. I mean, half of the dimension is an upper bound up to a constant factor for the number of vertices, and that is much lower than the number of supports, which is actually number n to the m. One could talk about this, but I mean, this is a better bound. So again, the polytopes are a good way of bounding these things. And now I want to talk a little bit about the construction of such polytopes that generate a lot of vertices, which is actually a cute thing, and that leads to what David Gale actually did. So it's an interesting concept that you wouldn't think exists. It's called neighborliness. And what we're doing now is actually redefining for a while polytopes not as bounded intersections of half spaces defined by inequalities, but as convex hulls of points, which is a different way of describing them, and I'll come shortly to the difference. So let's look at a bunch of points. Now, if you have 4 points in 3 space, you generate a simplex, a tetrahedron. If you now add another point, a 5th point, you will see that there will be 2 points, like in this picture here. You have here, say, a triangle and then 2 points that do not see each other. They are not connected on the outside of the polytope. You see them, they're going inside through. It's actually an easy consequence when you write the inequalities for 5 points in space, that there must be such a thing. This is also called Rador configuration. So if you have more than 4 points in 3 space, you get points on the vertices of the polytope that are not on the outside. However, in dimension 4, you can get such things. You can create points, and I will show you how, in 4 space, such that any 2 points are on the outside of the resulting polytope, which is already telling you something about dimension 4 being different from dimension 3. And this can be generalized. Actually, in dimension D, there are these neighborly polytopes with, say, a capital N vertices, such that up to half the dimension, all of them, suppose you're in dimension 6, any 3 points define a triangle, which is actually a face of the polytope in dimension 6. So a face is something on the outside. I mean, and it turns out that because they have now the maximum number of faces in up to half the dimension, as many as possible, because any point configuration in these low dimensions is already a face, it turns out that this extends to the higher dimensional faces, which is actually the core of the upper bound theorem. It has to do with, it's a nice theorem. Now here's how to construct them. We can look at the cyclic polytopes, what they're called. We look at the moment curve, which is a parameter, t, in the real numbers, which you take to the power t squared up to the t to the dimension d, and you create a column vector there. And so you look at this curve. So for example, in dimension 3, dimension 1 is a line, dimension 2 is the parabola, and in dimension 3, it's the cubic function here. And you take, say, n points here, say 6 points here, and you take their convex hull. Now, you take the convex hull, and now you have these points. And now the question is, it happens to be that any d, so in this case 3, any 3 of these points define a hyperplane. You cannot have more of them. The other points are not on that hyperplane, because otherwise you get a polynomial with more than, of degree d with more than d zeros. So all the other points are not on this hyperplane. And the question is, when does this hyperplane define a facet of the polytope? What does it mean? It means it defines an inequality such that everything, all the other points are on the other side. So I've done them here in pink. I have taken here 3 points in blue. And the 3 points here, they define a facet because all the pink points that I didn't use of these 6 points are on the other side. And now the very cool thing about this thing is that you can tell whether this is a facet or not from the sheer order in which these points that I've chosen, these blue points on the curve. They appear in this order on the curve, T1 up to, it's all the order. It doesn't even depend where the points are. And I have encoded it in a bit string, a very computer sciencey thing. By the following, I say I put a 1 there. I take a bit string of length n. And whenever I use the point here in blue, I put a 1 there. And if I don't use the point, I put a 0. So this pattern 1, 0, 0, 1, 1, 0 encodes a certain subset, an n subset, I mean d-dimensional subset, the element subset of my bits, of my points. And this thing has the feature that I can tell from this bit pattern whether it's a facet or not. And the facet, and it's called the Gale evenness condition. What does it say? It says you take it any such bit string which encodes a subset of the points on the moment curve, and if the ones in the inside have to come in pairs. In other words, when I have a 0 followed by a bunch of 1s followed by a 0, that has to have an even number of 1s. And why is that? That's, I mean, very cute. Let's take such a subset and say, suppose they appear in pairs. What I forbid is 0, 1, 0 or 0, 1, 1, 0 and so on. Why? Because the zeros encode the strings that are not on the hyperplane. I'm now looking at the hyperplane. I mean, in high dimension, I look at it from the side. And what would happen if I had an odd number is I have a point not on the hyperplane. And then the curve crosses. This is another feature of the moment curve. It has not too many turns. Crosses the hyperplane. And then I have another point. It's on the other side because I've crossed it an odd number of times. So that's clearly something that cuts through my polytope. But if they're all appearing in pairs, in even numbers, they're all on one side, like in the picture above. So in other words, the substrings of all ones characterize my polytope. I know exactly what are the facets of this polytope in dimension D. So it's a totally, I know the entire combinatorial structure. And now I can also count these things. So essentially, I need to only look at these bit strings. It's all combinatorial. So for example, if I'm in dimension 4 and have a 4 by 4 game, then I mean, I get a polytope which is composed of pairs of 1s and a bunch of 0s. There are 15 possibilities. Clearly, any such thing is a Gale evenness string, one where the bit strings appear in even, the 1s appear in even number of times, or I can put an odd number of 1s on each side, and then I have something in the middle where I have only one packet of 1s and 4 zeros, so there's another 5 possibilities. So we get 20 Gale evenness strings, and these are the facets of this polytope, and there's actually more than the cube. A 4-dimensional cube has only 16 corners. So this is in fact a polytope that has the maximum number of the things that I'm looking at. And so I can count, and you can also see that this is actually of order half the dimension. In particular, in dimension 5, I put in 2 pairs of 1s, 5 zeros, and then I have to put an on, because an odd number and 1 on either end. That's 7, choose 2 possibilities, times 2, 42 possibilities. Life, the universe, and everything. If you know Douglas Adams, 42 is the ultimate answer. So this is the number of possible vertices of a 5-dimensional polytope, which is the current known upper bound for the number of equilibria, -1 for 42. Isn't that a beautiful answer? But it's not the answer. So for the games. So by the way, we get an upper bound from the for square games of about 2.6 to the n. So with 2.4 to the n, we are close, but not there. The upper bound is 2.6 to the n, and in particular for dimension 5, it's 42. By the way, I like to include the artificial equilibrium in these computations because, I mean, it's just nicer to look at an even number, not discounting it all the time. But the Nash equilibrium is 1 less, 41. So now here's one trick that I have ignored for now, is I have to convert this polytope, which is a convex hull of points, to inequalities. There is a duality or polarity between them by reinterpreting. Yes? An upper bound, the number of 5, the polytopes that I get for a 5 by 5 game is 42. No, there isn't. That I will prove that there isn't. But I mean, it's the upper bound that I get from the vertex bound. That's what I'm saying. Correct. No. Any polytope has no more than 42 vertices. This is a particular case that I can easily count, which I know meets the upper bound for the vertex bound. Does that make sense? So the Gale evenness, the polytopes generated from the moment curve, give maximum number of vertices of a polytope. That's my theorem. It's not my theorem, it's known. But I mean, so I'm only saying that the upper from the vertex bound, you're guaranteed to get no more than 41 equilibria, but the actual bound is actually lower. I will prove it's 31, which is the main story. But well, anyhow, I do have to convert these things into, I just have to reinterpret them in order to make them inequalities, because the convex hull of points has a lot of facets. I need to dualize it by reinterpreting them as normal vectors of inequalities by putting the 0 in the interior, and I get this polar polytope. And then in other words, instead of looking at convex hulls of points, I need to look at inequalities defined by normal vectors. And then what used to be a vertex becomes a facet, and what used to be a facet becomes a vertex. That's a duality for polytopes. Sorry, I have to go on. So I use this, and now it turns out that when you have my polytopes for games, you have these bit patterns which express the equilibrium condition. So here are two polytopes in a different representation. I mean, you encode every vertex by a bit pattern where the facets it lies on. For instance, here 1, 1, 0, 0, 0 is the artificial equilibrium because these facets are 1, 2, 3. It complements the 0, 0, 1 vector. And all I have to look at is two bit patterns that together get all ones with an OR, if you wish. So the nice thing is about the Gale evenness pattern is that I can look at the bit patterns and then try to generate equilibria which fulfill the complementarity condition. Now, if I do this for the cyclic polytopes, which have the maximum number of vertices, I, for instance, get here a bit pattern 0, 1, 1, 0, 0, 1, 1, 0, 2, 3, 6, 4, which is complementary to 1, 4, 5, 8. So this would be an equilibrium if I have these two polytopes. It turns out that then not only the ones, but also the zeros have to come in pairs, and I would only get 12 equilibria. And one of the tricks, and that's the tricks that I used, is that I can permute the labels. And the trick is to permute the labels of the second polytope by just swapping them. Like instead of 1, 2, 3, 4, 5, 6, 7, 8, I have 2, 1, 4, 3, 6, 5, 8, 7. And this has the effect, so I know I'm fast, but the effect that the bit patterns 0, 0 and 1, 1 are unaffected by this. They still stay equilibria, but I also have another substring of the form 0, 1, 1, 0, which when I complement it, I get 1, 0, 0, 1. But when I permute these things, this inverse, I get 0, 1, 1, 0 again. So I get a Gale evenness string again on the right. You see, I get now all the substrings that I can form from 0, 0, 1, 1 and 0, 1, 1, 0 as possible equilibria. And they turn out to be more than 2 to the n when, again, it's a little large at when n is equal to 6 to get the 75 equilibria. And it's an open question, but I'm still working on it, whether this is the best possible permutation to get the maximum number of matching vertices. Now, so here is the story of this. I mean, and you can count them, and then you get these 76 equilibria with these strings with the 0, 0, 1, 1 and 0, 1, 1, 0 patterns. Now, this was the game that I could publish after this work. The numbers are quite big. I was asked, I gave a talk I think in Caltech in economics, and what was the question from the economists? Can you imagine? What's the economic interpretation of this game? And I said, sorry, it has 75 equilibria. Okay. I have then found a slightly simpler using the trigonometric moment curve, cosine, sine. I mean, so then I had a smaller game, but anyhow, the economic interpretation is simply that you have to reuse a support more than once in order to get this result, which is almost a trivial observation. But anyhow, maybe you find an economic interpretation of this game. So, and they have also been used by my then PhD student Rahul Savani and me with a different permutation to generate exponentially long Lemke-Hausen paths for any drop label. So the cyclic polytopes, and the cool thing is you only need these bit patterns. You don't need the You don't need the actual payoffs. So now the bound, we had the vertex bound, we get a second bound, which is called the stable set bound, and it's obtained from the following. Let me illustrate the so-called index, which is the following. These paths, they not only connect any to equilibria, but they also have a direction. When you look at this diagram, you have 2 on the right, on the left, 3 on the left, along the path, so you can tell where you're going. And this is the D in the PPAD story, if you have heard about it. And that means that the orientation, there's a unique orientation around the index, around the equilibrium, which go clockwise or counterclockwise. And the endpoints of Ramke-Hausen paths have opposite index. This was a definition due to Shapley. In my mini course, I will give a simplified proof of Shapley's proof. And now the interesting story is that if you have any 2 adjacent vertices, I have to go a little bit faster here, on my polytope, they have to have opposite index because they can be reached by a very short Ramke-Hausen path. So in other words, the equilibria of the game, you have to be able to partition it when you look at the graph of this polytope, meaning the edges and vertices, as we call them in graphs. Any 2 adjacent ones have to have opposite index. So in particular, in a triangle, you can only have 2 equilibria because otherwise, or in a pentagon, here's another example. I mean, they have to have alternate index, but you cannot put, you have to waste one of the points. Yeah, because you cannot assign an index to that one and adjacent ones have. So you get now a bound that says you have to be able to partition the graph of the polytope into disjoint sets that they are themselves stable in the sense that they don't connect to each other or independent. Okay, so you have to be able to partition your vertex set into 2 independent sets of maximum equal size. And that gives you an extra bound. And because I'm running short, I mean, the whole story is that we were able to use this bound in order to bound the number of equilibria. Now, what is very interesting about these neighborly polytopes, people when they discovered them, actually Theodori had discovered them in the early 1900s. Gale discovered them in the 60s. And they thought these were the only neighborly polytopes. And nothing could be further to the truth. Oh, I should say one more thing. Because I'm short, I realize I should have talked less. But I want to do one more cute thing about 3x(n) games. It turns out that you can create games where every vertex is used. So for instance, the cube, we know, we get eight things, but I can subdivide the cube by 2 extra lines, and then I get a hexagon. And what I have done here is I have colored the faces of this. It's a cube with some things. I have used them with 3 colors. It's a 3-color theorem. What does it mean? You might have heard of the 4-color theorem, which means that any planar map is 4-colorable. And there is a special map which is 3-colorable, which is one where every country has an even number of neighbors. Because you just say this, I mean, we can do this here. You start with one country, give it a color. So the rule is that no adjacent countries are allowed to have the same color. And then you just alternatingly them in the other colors. And you can, because of the evenness, you get 3 colors very easily. So you get 3 colors. And at the time when people observed this 3-color theorem, they said, okay, if you have an odd number of neighbors, you just need an extra color. That's the proof of the 4-color theorem. And for 20 years, people thought this was the proof, but it was wrong. It's only a proof of the 5-color theorem. And then it became a huge open problem for 100 years. So this is the simple version of the 3-color theorem. What do I want to say about this? You can actually generate polytopes where every single vertex is used, except when the game is of size 3x4. Here is an example. For instance, a 3x6, which is not so easy. And then you get here's a game on the right, which are the numbers, where every single vertex is used and becomes an equilibrium. So it's a game with 13 Nash equilibria. And the numbers are actually, you have the colors here are actually the unit vectors that you generate on the left-hand side, where you have much higher dimensional polytope in dimension 6 by just using the unit vectors here, which is like the cube, but more general. So that was the cute thing. I have only 5 minutes, so That's why I'm rushing so much, but this is a really cute story about 3 by n game, which you get the maximum number, the vertex bound, except when you have 4 columns where you get only 7 equilibria, because there are too many triangles around in these games. So you can get this. Now, let me skip the 4 by 4 case. Let me do the 5 by 5 case, which is the main result. And there we look at there exists lists of polytopes, combinatorial types of polytopes. They do not exist for 5 polytopes, dimension 5 with 10 facets. We don't know how many there are, but they are neighborly ones, the one that have the magic number from Life, the Universe, and Everything, from the Hitchhiker's Guide to the Galaxy, the 42. You have actually 3 of them in dimension 4, but in dimension 5, you have a whopping number of 156,000. So rather than being unique, I mean, like in the Gale evenness, there are a huge number of them, but at least there is a list. So we look at the one that have 42 vertices, we can check them, and we can find enough disjoint triangles or tetrahedra to get that down to 32. And that means these games don't have more than 31 equilibria. But now what do you do when you have fewer vertices? And I thought, okay, that's just an easy case, but it's not true, because once you have fewer vertices, so what happens is you have to have 2 facets that are disjoint, because of the neighborliness is no longer true. But then you can have also vertices that are not sitting on these facets, and that becomes a complicated story. And we were stuck for 10 years. And now I can only sketch, but I mean, we looked at then case distinctions for these faces of the polytope, where we have lists, and with enough ingenuity, if I may say so, it's two details here, we can then check the stable set bound and so on. And it turns out, so the answer is 32. Let's put it this, 31. So a 5 by 5 game, a non-degenerate 5 by 5 game, can have at most 31 Nash equilibria, as Quint and Dubey conjectured, but they had nothing to do with polytopes, what they conjectured. Their polytope is the cube. When you have the identity matrix, you just look at the cube. We look at a lot more complicated objects, which have 40, 42, whatever vertices, not just 32. And that's it. One of the faces that we looked at is the semi-cube. When you look at it, so this could be extended to a 4-dimensional cube, the projection of a 4-dimensional, it's also called a tesseract. But if you do it like this, here, you get a triangle here, and you get actually other triangles here, there, and there. And these 3 points cannot be equilibria, because they would violate the parity condition. You remember that if you have a triangle, one of them cannot be used. If you have a simplex, a tetrahedron, you can only use 2 of them because they're all adjacent. The 2 of them have opposite index. Any new one would have to violate the index condition. So that doesn't work. So this has at most 14 equilibria, and then with enough analysis and computer analysis and some case distinctions, you can prove this fact. Sorry. But this is the summary. M by n games are pairs of polytopes. They are simple polytopes, they're non-degenerate. And now we use the stable set bound that says if you have adjacent points on a polytope, they have different index. So whenever they have to belong to 2 disjoint sets of positive and negatively indexed equilibria. So that introduces a new bound on the possible number of equilibria that you can have, which you can investigate with computation. We did essentially along computations here. And with this computer analysis, we looked at the lists of polytopes that is known in dimension 4 and 5 in enough of a way that we can prove that 5 by 5 games can have at most 31 equilibria. Thank you. So it's not a very satisfactory, proof, but computers help now. I think we should go online now for our next speaker in some way. So you do.
Hello. Hello. Hello, can you
Hi.
hear me? Hey.
Hi, do you hear me?
Yeah, we can. We are ready. Hello.
Hi.
Are you listening us?
I am, yeah. Do you hear me?
Yeah, we can. You
Good.
may start, sorry, about the little delay we had.
Do not worry. I share my presentation?
Yes, please.
Maybe.
You just closed your presentation.
Yeah, I'm trying to put it bigger. But it does not allow me to. Now, yes. Now, like that is bigger.
Yeah.
But it does not go. Sorry. Okay. I hope this my sorry, I don't know why okay. So I will present a joint paper with David Pérez Castillo that is around there in Sao Paulo, and Miquel Álvarez Mozos from Barcelona, and also kind of the kind of game we are interested in, and we think that there are some other interesting things to do around. So I hope I convince you about that. A central question in cooperative game theory is how we will share the gains from cooperation. And this has interested many researchers who have proposed different ways of sharing the surplus created from a cooperative point of view. And also they have tried to propose games or environments that are interesting for, in particular, for economics. One of the most appealing sharing rules, the most appealing sharing rule, I think, is the Shapley value, who was proposed by Shapley for characteristic function form games in which we have a set of players, we have a function that determines what is the worth of the contribution of the players to a particular coalition, and you can define the value of this, the worth of these coalitions only by determining the members of the coalition. You don't need to know anything about how the other players are organized. And Shapley has characterized this sharing rule on the very desirable properties. What we try to do here, after a short presentation, is to propose to you a class of games, a family of games, and mimicking the way in which Shapley has proceeded, extend the Shapley or adapt the Shapley ideas to this class of games. So, a previous stage that is related to the way we see our model is characteristic function games are very interesting and very nice, but they do not represent very well situations in which we are in general interested in economics. Trade agreements or mergers depend not only on the people who participate in the agreement or on the merger, but also how the other people are organized. To this class of games that describe is much more larger and describe much interesting situation from the point of view of economics are the partition function form games. In this class of games, as you see an example, many of you know that, but just in case you work on different topics, in this partition function form games, the value of a player, in the table you have an example with 3 players. The 2 first rows of the table are how much one gets when 2 and 3 are separated and how much one gets when 2 and 3 are together. In this class of game, the partition function form games, you cannot say what is the worth of a coalition without specifying also what is the partition, the whole partition of the players, how the other players are organized. This class of games is much more larger, and not surprisingly, there are many solutions. There are several attempts to propose extensions of the Shapley value by extending the original axioms of Shapley to this situation where there are externalities. And this is again an example. If you see to the left, in the partition when 1, 2, and 3 are isolated, 1 gets 1 and the other 2 players 0. When 1 is alone and 2 and 3 are together, all the coalitions get 0. When 2 is alone and 1 and 3 are together, all of them get 0. The same when 3 is alone and 2 and 1 are together, and the rank coalition gets 1. Okay. So for this very simple game, you have also several proposals. There is a proposal, the earliest in the literature by very far. The other people we have moved much later, is by Myerson. There is some that is called externality free or extended Shapley value, that the idea is that they consider they are axiomatic. So what I'm saying is a naive version of what they do, but they consider either that the external players, they only count when the external players are together or isolated. There is a proposal by David Perez, David Weinstein, and myself, that is the second one that you see, Macho, Perez, Weinstein. And there is a class of solutions of sharing rules that we call the average. That is a way of computing the Shapley value by computing the Shapley value of a gaming characteristic form that we constructed by doing averages about how much a player can get, putting weights to the different partitions of the odds. Okay, but it's a very large. I mean, there are many proposals, and then many others are done or can be proposed. What we are interested in here, the motivation for this paper was to consider situations that have also externalities, but have a particular structure. Many of the choices we do today, in Spain, we are suffering that now. The environmental change and is very important. On other situation, the extraction of non-renewable resources, the disposal of nuclear waste, the construction of non-live infrastructures. There are many situations in which there is a set of players that are taking decisions today and will determine the conditions or how the players that will come in the future will be able to generate wealth. So we propose to consider this new class of games that are games with externalities, because the way some players are organized affects others, but they are games with these intertemporal externalities. So our idea is these games have this very simple structure. We will have, this can also apply to players that live in different countries or in different places in such a way that one affects the other and is not reciprocal, and that you cannot move from one set of players to the other. But I will consider all the time present and future, and hence the intertemporal dimension. So imagine there are two people living in the present and two people living in the future. 1 and 2 live today, 3 and 4 live tomorrow. There is no overlap in between the time these two generations live. Players in the present form coalitions and create worth. People in the future also, 3 and 4 can be isolated or together, but how much they can generate depend on what is the inheritance that the people in the past have left to them. Depends on whether 1 and 2 were together or not, for example. Okay? So that's the idea of what we do. So this family of games is defined as follows. We have two disjoint set of players, N1 and N2. N1, I will refer to them all the time as the people, as the present people. N2 is the people that live in the future. And these two set of players are disjoint. There are these two periods. People in N1 interact in period 1. They after disappear. People in N2 interact at t equal 2. And the organization of the players in N1 affect the worth of the coalitions in N2. And we also consider, to be close to the basic literature, that the game is with transferable utility. What in our family of games in particular means that we can transfer money from the present to the future, or the other way around, at zero interest rate or zero cost. Okay. So we denote S1 the coalitions of players in the present, and they are non-empty. They are non-empty subsets of the set of players. When a coalition of players today form, the players have jointly as surplus that is V1 of S1. So V1 is the surplus function. And in here, there are no externality. In the present, in these basic models, in the present, the coalitions of the other players that are living today do not affect the worth of a coalition. There are only externalities in between periods. Coalitions of the people in the second period in the future are denoted by S2, and they are non-empty sets of the set of N2 players. And how much, what is the worth of a coalition of the people tomorrow, depends also on the past of organization of the players in the present in N1, that means on the partition of the players in N1. Okay? So the value, the worth V2 of our coalition S2 of players depends on the partition that was formed by all the players in the past in N1. We also assume that the value of the empty coalition in the present or in the future, the worth of the coalition in the present or in the future is zero. So what we have is this game that is a set of players divided in between people living in the present and people living in the future, N1 and N2, and a worth function. V1 affects to the how much the people in the present generate. V2 affects how much the people in the future, in the coalitions in the future generate, depending on what was the behavior of the people in the past. So value, as always, is a mapping from the set of players to the real numbers that will tell us for each of the players in the present and in the future how much each of them gets, with the characteristic that they share the total surplus generated in total in the economy, both in the present and in the future. So we are assuming all the time efficiency. So what we do is we extend the axioms of the original axioms by Shapley to this class of games, following what has been done in the literature with the games with externalities. Okay, so we define the addition of two games. In here, we will have the people in the present, people in the future, with one particular situation, and the people in the present and the same people in the future in another particular situation. One is V, one is V prime. So we can define the addition of these two games in the traditional way, and the multiplication by a scalar also in the typical way. If we multiply a game by a worth function by a scalar, we are multiplying the worth of both the people in the present and the people in the future by this scalar. Addition and multiplication give us is linearity. The permutation we also can define in a very similar way. So when we permute the players in the game, we permute the players in the present among themselves, and the players in the future among themselves. And when we permute the people in the present, we also take into account that affects the names of the people that will be in the partition. Okay, so it's a permutation. And we define what is a little bit more tricky, but it's also in the line of what it was done with partition function games, is the definition of null player. The players in the present, the players in N1, to be null, we ask two conditions. One is that they don't add anything to the coalitions in the present. So if you move, for example, if you move this player around, the value of the coalitions do not change. But in addition, to be a null player, we ask that when we move this player out of a coalition of the partition in the present, it does not affect the worth that the people in the future are obtaining. That means to be a null player, I has to be such that he does not generate any worth today and any externality tomorrow. Players in N2 have the traditional null player definition for no partition of the people in the past, for no history. Player J is null when he does, for any history, he does not generate any worth. So with that, we can define linearity. We can define a value is linear if you can if you add two games, the amount that the people get is the addition of what they get in the original game. same with multiplication by an scalar. Anonymity is satisfied in a game when if you do a permutation, then the new you gets the same as the old you get. I mean, it just depends on the worth you are generating in your how much you contribute, but not on your name. And null player asks for a null player either in the first period or in the second period. A null player will not get anything in the sharing of the servers. It's very easy to see that if there is no people in the present or there is nobody in the future, we are in classic characteristic function for games, and internal externalities. There are just two characteristic function for games with different people, but what we can prove, and it's also something that I have mentioned before, is that in this class of games, the externalities make a complication and make the situation much richer, and there are many things that satisfy, many sharing rules that satisfy linearity, anonymity, and null player, in addition with efficiency. But the solutions have all the same form. For the I are the people today, for the people in the present, what they get is the Shapley value plus something that depends on the externality they generated, and the people in the future get something that depends on their worth, but also the externality that is generated. And so is such that the people in the present get the Shapley value of a characteristic function from game, forgetting about the externality they generate in the future, and whatever is generated in the future is shared by the people in the present and the people in the future. All the solutions that satisfy linearity, anonymity, and null player get this form. What we propose is two values that I have begun a little bit late. I will try to be shorter, so I will skip some part of the presentation, but I will present at least the idea of two of the sharing rules that we have, that they are inspired in the expected contribution from random arrival processes. And we consider two of them. One is the arrival process in which all ordering of all the players from the present and the future are feasible. So today, randomly there is one present player or one future player who arrives, and it can be another future, then a present, then another from the future. The only thing is that when they enter the room, the people, they are like two tables in the room. When a person from the present enters, he sits or she sits in the table of the present, and when someone from the future enters the room, whatever the coalitions that are already formed or the organization of the tables will sit on the table of the future. Okay, and the other one is the situation in which all the players in the present by the temporal organization arrive first, so they will be randomly entering the room, but all the people from the present will enter first, and when all the people in the present are in the room, in whatever order, then the people in the future will enter the room. Okay, so the first one, the one in which all orderings are feasible, allow us to define what we call one coalition externality value, and we call it like that, but because in the partition that is considered for computing the contributions, the people in the present are always in a large coalition, and all the others that are outside the room and the table are singletons. So there is one coalition that is formed and that defines a value. That can be, I will skip that. And the other one, the way in which the people in the present enter the room first in any order, and then the people in the future enter. We call it the naive value, and is a value that, in particular, shares the amount of surplus that is generated in the present among the people in the present. They don't get anything, or they don't suffer any cost for the externalities they are exerting on the future. Whatever is generated in the future, more or less because the people in the present have helped to generate surplus, or because they have damaged whatever the environment, will be distributed or covered by the people in the future. Okay, that's why we call it that. These two values can also be characterized axiomatically. The one coalition value can be characterized by adding to the previous assumptions, to the previous properties that I have presented, linearity, anonymity, and null player. The one property that tries to ask that equally relevant players, to be defined in a moment, get the same amount. And to be equally relevant is a tricky definition. For the people in the future, that's part B, two players in the future are equally relevant. This is kind of anonymity, if they are the same in the sense of anonymity. For the people in the present, it's a little bit more convoluted, if not, but is to be equally relevant, two players need to do two things. One, to add the same to any coalition in the present, but in addition, they have also to generate in the partition, they have to generate in any partition the same externality. Okay? They have to contribute to the generation of externalities in the same way. But in addition to that, we need, as you see, part C, that is so A, in the definition, the first part concerns people in the present. The second part concerns people in the future. The third one compares or defines what is equally relevant in between some guy who is living today and someone who is living tomorrow, is in the future. And the idea of this equally relevant definition, this part in between someone in the present and someone in the future, is that in the future, that is the only time we can compare them, because in the present the players in N2 cannot create, don't affect anything. So, but in the present, in the future, what is important is in the future, the externality that the guy in the present is generating is equivalent to the contribution that the guy in the future is having. Okay, and if we have this definition of equally relevant, the only value satisfying linearity, anonymity, null player, and equal treatment is the one coalition value. We have another axiomatic characterization of the naive value that I will skip. I will just escape. I will just tell you that there is another way of defining unequal treatment, but this time is not of players, is of externalities, and in this case we can axiomatize the naive value. But you can think, I mean, since these are only two proposals, and two proposals of arrival of random arrivals to the to the game, but it's also two proposals of axioms about the players or the externalities. You can think on many others. For example, if you consider that the random arrival, that for us was less natural, but you think that the random arrival is that all the players in N2 in the future arrive first to the room and get seated randomly on this table and that table, and then the people in the present arrive, then the sharing rule will be someone in which the externalities will be, I don't know, enjoyed or suffered by the people in the present, and then instead of, it's just the opposite of the naive. But you can also consider different definition of the different axioms. For example, if we explore a little bit what is the definition of null player, or other solutions. If we have a strong null player definition, meaning that we define the null player in the game as someone that does not create value, does not create worth in the present, and we forget about whether the organization or the coalition he belongs to creates externalities on the future. So to be null player, it only matters whether you in the present, when you participate in the current game, you don't generate any worth. Then this strong null player, anonymity, linearity, give us also the naive value. But you can, there are many things that can be explored, and we plan to do some. But for example, if we take the nullifying player, and you have a definition like the one I have here, strong nullifying player, then you can extend the equal division sharing rule to this class of game on the linearity, anonymity, and strong nullifying player. The equal division sharing rule is the only rule that works, in which the people in the present share whatever they generate in the present, and the people in the future share what they generate in the future when the people in the present form the grand coalition. But there are many directions in which this can work. We think it may be interesting to consider this class of game because in fact we live in a situation where there is not only externalities but also people that are not now in the game, are not present now, but whatever we decide now will affect them. And considering this type of approach we have, they cannot agree on the axioms we will apply, the people in the future. But to understand what are the axioms that will give different solutions in this case of game, we think that is interesting. And I think I'm more or less in the official time. Thank you very much.
Professor, can you hear me? Professor Inés, Macho-Stadler, can you hear me?
I'm sorry, but I don't hear anything.
Oh. Okay, so we ended the invited session for today. The buses will pass in 15 minutes. And that's it for today, people. Thank you very much for your attention.